So during the next speaker prepares his laptop, so let me explain the next speaker. So next speaker is Jae-young Kim from UNIST. And so let me briefly explain his career. So he got his undergrad degree in the Korea University in 2007. And he got the PhD at KAIST with Professor Yong-Hoon Jo at 2014. And since then, he did some postdocs and then became the professor at UNIST from 2017. And currently, he's working on the generations, manipulations, and integration of the photonic and spin qubits from solid-state quantum emitters and their applications for the quantum information science. Is your laptop ready? Okay. So. And then today, I guess he's going to tell us about the versatile quantum playground with the solid-state quantum emitters. So let's welcome the speaker.
Yeah, thank you for introductions and inviting me in this nice conference. My name is Jae-young Kim from UNIST. I'm in the physics department. And today, I'm going to introduce about some work with the solid-state quantum emitter. The previous speaker, Professor Hong-Gun Park, already introduced very well about the solid-state quantum emitter with defect in crystal and 2D material as well. I may be more focused on the solid-state quantum emitter, which is a quantum dot. There are two types of quantum dot exist in this field. One is a gate quantum dot with electron confinement on silicon or gallium arsenide. This is not a gate quantum dot. This is a band gap confined electron and hole. Both they are neutral emitters, the quasi-particles, so extons. So it is also so called as an optical quantum dot. So it is artificial atoms. The interesting part of this quantum dot, it clearly shows the size indeed matter. Basically, the size is not a fundamental property of material, but actually size quite important in quantum physics. As you reduce the dimensions and size, you can easily see how the electronic band structure changes like this, and also it affects optical properties. Even the same materials, by reducing the size, you can change the optical properties affect a lot. Using these properties, nowadays we can easily find a commercialized product like quantum dot LED from Samsung. So, and this year, there were these three researchers won the Nobel Prize in chemistry with this effort in this development of the field. But today, the quantum dot I would like to introduce is not this kind of colloidal quantum dot, but epitaxially grown quantum dot. So it has mostly these MBE machines or MOCVD can be used for this. So epitaxial thin film can grow this kind of quantum dot self-assembled ones. And the advantage of these types of quantum dot is surrounded by host medium, so it's very stable. So it is very nice. And exton plays very important role in this quantum dot. Like it can confine single exton or multi-exton complexes. Like having the single exton in a single quantum dot, it serves two-level system, considering the spin is V-like structures with its spins. So this two-level system can emit single photons. And also it can have not single exton, but bi-extonic features, and their cascade process allows to generate entangled photon pairs. And this spin state is excited spin, so lifetime is very short, so quite difficult to use this. But the quantum dot can be also has excess charge even at the ground state. So having these ground state spins, we can use their spin properties, and we can optically control all these spin levels. So this is a way to use quantum dot as a quantum memories. So not only quantum dot, there is lots of different solid-state quantum emitter like the defect in crystal, the add atom nanocrystal, and 2D material will be the another ones. And previous speaker introduced very well. And all these kind of solid-state emitters can produce spin and photonic qubit. And using this fundamental building block, we can implement lots of quantum hardware like quantum light sources, memories, gate, and even this kind of spin photons single photon nonlinear devices. So this is very nice. And definitely this kind of emitter faces lots of challenges that would include some quantum needs. Like in terms of single photon sources, we may need high single photon purity and indistinctibilities. And in terms of performance, we may need high crystal qualities to suppress non-negative decay channels. And also we may need more efficient light extraction. Unfortunately, high refractive index of host mediums, we can only achieve only 1% or 2% of single photons from these quantum emitters. Even worse, the major challenges actually come from their inhomogeneities, like the spectra and spatial randomness. Unlike the rubidium atom in Korea, rubidium atom in the US, they are just identical, but that is not the case for solid-state quantum emitter. Just another quantum emitter nearby, they have different polarization, different frequencies, so they cannot interact to each other. So that is really problems. But so far, we studied this kind of quantum emitter, and overcome all these problems with several approaches. Like we need more coherent, not just single photons, more coherent single photon, but solid-state environment that induce lots of charge noise, charge fluctuations, so spectral jitters can be easily observed, and the phonon relaxation involve phonon couplings that broaden the line width, and that reduce the coherence time of the single photons. So we expect lifetime limited coherence time, but actually what we observe is the dephasing govern the line width. So natural line width by the lifetime, we expect less than 1 gigahertz, but actually what we observe even at low temperature like 4 Kelvin, we easily observe 10 gigahertz or even few hundred gigahertz. So spectral broadening induced by these charge and phonon interactions should be reduced or eliminated somehow. And one easiest way we can do that is instead of long-resonant pumping, long-resonant excitation, actually long-resonant excitation is a huge benefit of this kind of emitter, like the atoms. To excite atom, we need very precise laser system and phase locking techniques. So if you see the group with atoms, you can see the aura full of the optics and lasers. Laser preparation system is full of the optical table, but the quantum dot, you can just use this laser pointer to generate single photons. So that is advantage, but with such kind of excitation method, it strongly induces charge and phonon noises. So instead, we can just mimic the technique from the atomic community. So we can slightly control the excitation frequencies and resonantly excite this quantum emitter. Then we can reduce the phonon relaxation process, so have better coherence. And we can add some more electrical bias to stabilize the charge environment. Then eventually we will get lifetime limited coherence time. And this is one example. So same quantum dot, but with different excitation laser frequencies, you can see more single peak, and the liveness is also reduced a lot. And with this kind of techniques, just changing the excitation wavelengths, we can improve this HOMs stand for homomental interference and its visibilities. So that is related with indistinguishability and coherence time. So from the non-resonant pumping and quasi-resonant or resonant, we can improve the coherence property of this kind of single photon. And also, that doesn't kill the brightness of the single photons. That is very important. And with this quantumness, we can also improve their performance. So based on well-developed semiconductor technologies, we can make a variety of different cavity structure like pillar, photonic crystal, Bragg gratings. And by employing these kind of cavity structures, we can extract more single photons, and we can engineer their far field like the Gaussians. And possible enhancement may enable the more fast single photon generations. And actually, having the cavity, we can implement cavity QED the rhythm. So actually, we can add more quantum functionality like spin photon entanglement or spin photon the interfaces. So all these things possible with this kind of cavity integrations. And thanks to all these technologies and the effort of this field, nowadays, you can easily find good single photon sources from this quantum dot with high purity and high brightness, and also high indistinguishability and simultaneously high brightness for integral photon pairs, high fidelity, and with again with high efficiency. So this community they are developing the performance and quantum along these directions without clear. Fundamentally, there is no trade-off between the performance and quantumness. That is not the case with more conventional quantum light sources like the spontaneous down-convergent sources. It has inherent trade-off. So for these reasons, now the traditional quantum optics group start to have their interest in these new types of on-demand solid-state quantum light sources as an alternative of traditional SPDC sources. So this is nice. And also, nowadays you can easily find a very nice startup company like Sparrow Quantum. I'm not sure this company is still doing some stuff, but Quandela, they are hiring really many researchers, like over 100. So they are not just source of single photon, they are making photonic quantum computing and also software platforms. So they are doing really well. So with this kind of nice single photon sources, high performance and high quantumness, that is nice, but most unfortunately, just single photon emitter, single photon source is not enough for quantum application. Basically, we may need not just single photon, but we may need more multiple indistinguishable or multiple identical single photon sources. But that is quite challenging with these solid state emitters. Like as I said, this emitter may have different size, different shape and strength, different local field that lead to different frequency polarization and eventually different temporal and spatial wave packets. So these quantum dot and this quantum dot, they may not interact at all. But yeah, the advantage of solid state systems is we can actively engineer their electronic band structures. So we can apply the temperature, field, strain, that all tune the band structures. And we can, this is what we did before. So these two emitters initially had different frequencies, but we can make them the same frequency by locally tuning the temperatures or locally tuning the electric field and locally tuning the strain that we can engineer their frequency. This is not quantum dot, actually this is WSE to 2D material, so site frequency control was possible at this time. And by using this kind of frequency engineering techniques, now it is possible to generate two indistinguishable single photons at the same devices. They can interfere to each other, so we observe two photon interference on two distant quantum dots. And also not just photon-photon interference, the emitter, by coupling this emitter and this emitter at the same waveguide, we can generate the collective interaction between these two emitters that form the super-radiant state, and we observe their cooperativity behaviors. So beyond the single quantum emitter, single photon sources, the community can do better with more numbers. And nowadays, not only two, more than two. So this is group from UK, the Andrew J. Hill. They interface the really many quantum dots with each channel of this photonic circuit, and each channel has individual tuners, so they allow the quantum interference between multiple emitters. And collective behavior, not more than two. This group from the US Naval Research Lab, they did with 3 quantum dot stuff. So this is also nice. Now we can ready to scale up these systems. So we have nice quantum resources from these solid quantum emitters, like not only single photon and integral photon pair. Today I didn't have time to introduce this part, but yeah, there is lots of work with quantum memories and spin photon interfaces. And yet these quantum resources, there is a lot of demonstration of these quantum resources, but most of them were demonstrate on optical table. But eventually, we are quite ready to go to real-world platforms, not the labs. So the next stage will be integrating, having these resources on more practical real-world photonic platform like photonic integrated circuit and fiber optics. This is what we are doing these days. So first part will be how to integrate two dissimilar platforms accurately and efficiently. So there is a lots of way to integrate quantum emitter with these new platforms. If our emitter is nanocrystals or nanoparticles, we can just disperse them, although their coupling is random. Or we can consider to epitaxially grow our active medium onto these photonic platforms. This is nice and wafer scale growth, but unfortunately, growing the high crystal quality for both materials is quite difficult since they have quite different lattice constants. So growth itself is quite problematic. And so another approach will be just grow two material with a separate system, then bond together. Then there's no worry about crystal quality. But with this kind of wafer bonding technique, the design and dimension of that possible integrated devices will be quite limited by this technique. So one good alternative at the moment will be just making a quantum device at quantum wafer, photonic devices on a photonic integrated photonic wafers. And then we integrate both two devices integrate later at the device level, not wafer level. So that is so-called pick and place. We can do that using PDMS stamp or microproof. So I'll briefly introduce some work we did before. So for photonic integrated circuit integrations, the left shows the quantum dot device. Actually, quantum dot is everywhere here. So there's nanobeams. And this is simple photonic circuit, a silicon waveguide. And with pick and place, where is my? So we can transfer this kind of device in SEM machine, actually FIB. So with these micro tips, it can take it out, and basically we can place them anywhere we want to place. So it could be silicon waveguide or silicon nitride or lithium niobate. Anywhere we can integrate those devices with high accuracies. This is some example of integrated quantum and photonic devices. And the single photon from our quantum dot will be transferred onto the silicon waveguide with this kind of couplings. And in this case, the silicon waveguide has Y-shaped branches that act as a 50-50 beam splitters. So our coupler, it shows the quantum dot emission from these quantum dot devices. Bottoms, gratings also shows similar. This is 50-50 beams, it just shows similar the quantum dot peaks. So by filtering these single peaks, we could successfully observe the Hambrier-Brown trace measurements. So it is a good signal of the single photons. So this is nice. Now we can integrate our single photon sources, quantum resources, onto classical photonic waveguide. And one good thing here is the photonic integrated circuit part is we already have major techniques for waveguide and directional couplers or modulators with lots of a variety of material like silicon nitride, aluminum nitride, or lithium niobate. And also kind of fabrication technique like with ring resonators and tunings. We can make a frequency sorter, converter, or photon number filters. And for detections, we can detect the single photon from free space using grating couplers or fiber integrations. And these days, also the integrating SNSPD directly onto the waveguide is quite feasible. So basically, all the techniques toward fully integrated quantum photonic devices already exist. So from the source integrations, controlling the photons, and generating linear, nonlinear interactions, and photon detections. Definitely combining all these techniques in a single chip is still a challenging task, but yeah, the community heading to they put lots of effort toward to implement this kind of system. So that is kind of things what we are doing with hybrid integration with photonic integrated circuit. And actually these days we have more interest in fiber optics integrations. That is also very important, but also there is lots of challenges. One important challenge here is we do not have good interface between these two platforms. Again, the quantum dot, we can collect only few percent single photons, and far field is just these dipole emissions, while the single mode fiber, they can collect only few angled photon with very small NA. So if you just input this wafer onto the single mode fiber, you can collect like the single photon with 0.001%, something like that. So very inefficient systems. To improve single photon coupling efficiency, you can consider this kind of the nanophotonic device integrations. They can produce Gaussian mode, but this Gaussian mode is formed by high refractive index medium, while this Gaussian mode generated by small refractive index, the mode. So the two Gaussian mode has very different mode size, so coupling efficiency is still very bad. So somehow we need to improve, we need better interface between. So in this work, we recently developed newly designed circular Bragg grating structure, not ring-based, but hole-based, that give us lots of advantages. So considering the ring structures and their refractive index contrast along radial direction is matter-air. So there is a large index contrast that confine the mode in a small region, while these hole structures and their effective index along radial direction is something like that, right? So we can reduce the index contrast that enlarge the mode size that is more matched with a single mode fiber. Also, these ring structures, the control parameter only exists along radial directions, while these hole structure control parameter, the design parameters exist also axial directions, like the distance between these holes. So that allows us to further optimization of constructive and destructive interference. So we can suppress, this is a gratings, high order diffraction already exists, but we can suppress high order diffraction with this hole structure. As a result, this is far field patterns, this is ring structure and hole structures, so-called the bullseye structures. It is actually already good, Gaussian-like, very nice. But hole structure is even much better. So almost a vertical within his cross-section profile, within 5 degrees, and with suppressed higher the angles. So that gives us a very nice interface for single mode fiber couplings. So like the collection efficiency with our optic systems, the fiber is something like 0.14, something like that. So we can collect more than 60%, while the conventional design is below 20%. So okay, we have nice design, and then we can fabricate easily with semiconductor materials. So this is a fabricated Bragg grating structures, and PDMS micro stamp that size well matched with these devices, and approach this one here and take it out separate from original devices with target one. Then we can bring that to the single mode fibers and attach at the core of single mode fibers. So these red lights come from the opposite end of the fibers as a guide. Then we can integrate our device onto the core, at the core of single mode fiber with quite high accuracies. So now we have fiber integrated single photon sources, something like that. And in the simulation, we expect single photon fiber coupling efficiency more than 50%. And this is a schematic of all fiber connected quantum systems, including the laser, our source, and some optical part, the detectors. So all these optical parts are fiber connectorized. There is no optical alignment, you just need to plug in, then you will get single photon sources on demand. There is you need cryogenic temperature for these types of quantum dot, but like other emitter may not need to use the cryostation. And careful calculation, we estimate our single photon coupling efficiency in experiment around 8%. Actually, we do much better these days, more than 10%. Yet that number itself is less than our expectations, but actually the number itself is actually the record high at this wavelengths with the fiber coupled emissions. So this is a sign of single photons, and the most important part here is the stability is very nice over hour or over days or few thermal cycle, room temperature, low temperature, room temperature, low temperature. We don't lose the photon counter rate. That will be sent because there's no optical alignment part. There's no way to lose alignment. So that is why it can generate stable single photon emissions with time. And why not? If we can do the single photon coupling with a single mode fiber, we can array them. We can make array them. This is V-groove fiber arrays, and we can attach our single quantum dot device one by one. Here we integrate 4 devices, something like that, and each channel nicely shows the coupled quantum dot emissions. And you can see that although the wavelengths, the frequencies of each quantum dot is not that identical, and we may need some frequency tuning with these devices if you want certain frequencies. And these days we are developing some electron node onto these kind of devices for tunable multi-channel single photon arrays. So this is nice, and also can be very. There is a lot of the quantum application based on the fibers. So like QKD, quantum teleportations, and entanglement distributions. And here is this group demonstrate quantum interference over 300 kilometers. So all these groups use the quantum dot as a source of quantum light, but the coupling efficiency was not that great. But using our kind of the fiber integrated quantum dot devices will be very useful for these kind of applications. So I don't have much time, I guess. I don't know. So not only the quantum dot and single photon sources, we can definitely use the same technique for quantum sensors, like the not quantum dot but defect increaser. Here is the HBN. So the similar design and HBN structures, it has volume vacancies that is very useful to sensing the magnetic field. And these similar integrations, the HBN devices with this cavity and defect is inside. We are the visibility contrast is not that great, but this kind of fiber integrated quantum sensor can detect a magnetic field, and later can be useful with like this kind of diagnostic of some medical diagnostic or the industrial inspections of the magnetic field or the current, temperature, or strain, something like that. Okay, thank you.
Okay, any questions or comments from audience?
Thank you for a great talk. And I think it's very basic questions, but in your page, about two photon entanglement, there is two polarization. One was parallel, it's indistinguishable, and perpendicular is distinguishable. Could you explain about what it is, parallel and perpendicular?
Yeah, we did. So, okay. So we did two photon interference measurement with two distant quantum dot. So yeah, initially we intentionally designed something like that. Yeah, here we go.
Yeah, just a second. Yeah.
So we initially make a device with single photon generation here and there with orthogonal polarizations. But we collect a single photon from each devices with different paths, so we can independently control their polarizations with the halfway plate. So anyway, eventually these two single photon sources will meet at a 50-50 beam splitter with controlled polarizations. So by matching the polarization, we can we observe the indistinguishable single photon property, two photon interference with orthogonal polarization. They just behave as a independent quantum memory, independent the photon light sources. Yeah.
Okay. Any further comments or questions? Otherwise, okay. Yeah, there.
Thank you for your good talk. You state the whole structure to end of the fiber to enhance the collection
Right.
efficiency.
Right.
I wonder, is there any other method you thought to enhance collection efficiency?
Yes. Actually, another advantage of this whole design, we can make, at this study, we just use the whole array of, or the array of whole structure with fixed size, or so some part is fixed distance, but why not? We can make some variant of different whole size, some gradient change of whole size and their distance, and they will improve the collection efficiency more. And these days, there's lots of technical inverse design that is very useful for optimizing such a whole array, their distance size, even higher for higher collection efficiency. That is ongoing work these days.
Okay, so I think we are out of time. So, so we are going to have a coffee hours, and the speakers in the next sessions, please come down and check your slides. Okay, let's have a break. Yeah.
Thank you.
Thank the speakers. Yeah. 그 신혜득 교수님, 김동 a minute, so please take a seat. Okay, so let's slowly start. So in the second session of the morning, we are going to have two speakers. And the first speaker of the session is Professor Hee-Deuk Shin. And let me briefly introduce him. So he got his bachelor's degree in the Hanyang University in 2002. And then he got the PhD in the University of Rochester in the 2011 in the optical engineering. And then after that, he did some postdocs and also worked in the Sandia National Laboratories, and then became a professor at Postech from 2022. And yeah, so currently he's working on the applications of the photonic techniques to the quantum technologies. And I guess today he's going to tell us about photon-based quantum technologies using quantum frequency translations. So let's welcome the speaker.
Thank you. Thank you for the nice introduction, and thank you for the invitation. So it's my great honor to be here to give my recent results to you. And okay, again, my name is Hee-Deuk Shin at Postech, and today I'm going to talk about quantum frequency translation, which I believe will be really powerful tool for quantum, photon-based quantum technologies. So this is a schematic of a quantum photonic system, which consists of a quantum light source and a linear photonic circuits, aka interferometers, and single photon detectors. So there are some phase modulator and waveguides and so on. These should be either on chip or optical fiber and so on. So this one looks like a photonic quantum computing system, but it's not only quantum computing. It's also a system for quantum communications, or quantum sensing is also possible. So very similar. So all those kind of photon-based system has a quantum light source, linear photonic circuits, and detectors. Detector part is too difficult for me to study about it. So because it's all kind of materials, we need to know the basic materials and the electronics. So it's still too complicated for me. So I'm more focused on quantum light source part and linear photonic circuit part. So let's start with a quantum light source. So first, quantum light source that I'm going to talk about is a spontaneous parametric down conversion, which is a really well-known technique. So in a nonlinear crystal fiber, nonlinear crystal, if you shine a blue laser, there will be two red photons coming out of the crystal. So depending on the polarization, it's going to have a type 0 or type 1, type 1 or type 2. And recently we could get some efficient photon pair generation from lithium niobate waveguide without periodic polling structure. So simply pumping laser is at 775, and the photon pairs are generated at 1550. And at the time we use, because the pump laser is a TE02 mode, so we have some inverse designed mode converter. And using this inversely designed mode converter, we could enhance the photon pair generation rate significantly. So it's going to be submitted soon. And also the second quantum light source is a spontaneous foil mixing, which will be any material, like a fiber, optical fiber, or silicon waveguide. Any material can be used as a photon pair source for via spontaneous wave mixing. And in that case, we need a 2 pump photon excite the system, and it generates a signal and idler photons. So the advantage of this spontaneous wave mixing is a small volume, it has high efficiency, and it's also, we can integrate to optical fiber system or photonics, integrate photonic circuits. It's also possible. And recently we have shown that in a lossy waveguide, the photon pair generation has some kind of optimum condition for length. So the maximum brightness from a lossy waveguide can be achieved when the length of optical waveguide is proportional to the inverse of loss coefficient, 1 over alpha. So this one is also published. And third method is thanks to Professor Jae-Young Kim for his nice introduction, and single quantum emitter. It uses a spontaneous emission, so pumping up and reduce some energy and emit single photon. That's a basic mechanism for single photon emitter. From isolated one quantum dot or one defect center, it can generate single photons. This kind of experiments has been done, and more recently, people are so excited about the electrically driven single photon emitters, which is also possible, which is actually commercially available in many different countries, different companies, like Quendela, which is the most famous company. And using this kind of, so far I have shown that there are a couple of methods to generate quantum light source. First one is, these two are generating photon pairs, and third one is a single photon. And using this kind of different photon light source, what can we do? So of course we can do quantum computing using photonic system, and also people, but nowadays people are also interested in enhance or expand the quantum computing space using quantum nodes and nodes between them, and using a quantum computing network, and teleportation is also one of the interesting parts, and mostly also ultra long range of quantum key distribution using repeaters is also very interesting. But to use this kind of, for these kind of research, we need some kind of indistinguishable photon. So for example, yes, you need indistinguishable quantum light source. And distinguishable or indistinguishable for those who are new here, photons, in photons case, photon has many different types of properties, like wavelength, polarization, mode, phase, propagation direction is also one of the properties described a photon. If any of these properties are not same, then two photons are distinguishable, right? So for example, let's think about the quantum dot or photons from quantum dot. Thanks to the Jae-Young Kim's previous talk, it has its own wavelengths. Single quantum dot emits single photons at one wavelength. Another quantum dot emits at different wavelengths. The emission bandwidth of single photon, single quantum dot is 1 gigahertz, which is nearly narrow, let's assume that. But different quantum dot has a different emission wavelengths. And in ensemble, it will be really broad emission. So typically the ensemble emission bandwidth is 10 terahertz, which means statistically you need to check 10,000 quantum dots. You need to test the 10,000 quantum dots to have equal wavelengths. So that's going to be, I know there are some tricks to do that. So nowadays they are really test all the quantum dots really so fast. So practically it's not going to take that so long, but that's a company case, like a Quendela case. But think about students here. if you should test the 10,000 quantum dots, you're going to graduate maybe over more than 10 years, right? Okay, so we need to somehow to solve this kind of problems. So there is a there is a way to control the spectrum of a single photon emitted from a quantum dot or single photon emitter. Electric field can control the emission spectrum. One way is this one. Also, strain can control emission spectrum, or magnetic field can also control the emission spectrum, or strain or cavity is also possible. But here the thing is wavelength shift from this electric outer force is less than 1 nanometer. So if you wanna switch the wavelengths more than 1 nanometer, you need to find another way, right? Then what about letting the single quantum dot do what their job? So it continuously emits its own wave, continuous emitting as a single photon at its own wavelengths. Let them do it. And later, we change the frequency of that emitted light into one frequency. If we do that, that'll be much easier, right? Okay. So this kind of work, actually, I'm working with Professor Jae-young Kim for doing this kind of work. And also another interesting applications, if we can shift single photons wavelengths, is coupling quantum memories to fiber system. So far, the quantum memories are really good at like 800 nanometer or 900 nanometer in visible range is also pretty good because they use atomic ensemble system. But for long distance communication, we need optical fiber, right? So in such a short wavelengths, it's not gonna propagate very long through the optical fiber. So we need to somehow we need to convert visible range photons to near like 1.55 micron. And that can be done using periodical or some kind of nonlinear effect. Using a nonlinear effect, we can convert from short visible range to IR range. This diagram shows difference frequency generation. So strong pump beam and seed beam, or the single photon, comes in, and there will be an output photon which has a frequency 1 pump beam minus a single photon emission. In that case, we can have a strong frequency shifting. And using this kind of technique, they have demonstrated a quantum repeater. Also, okay, so in short, some and difference frequency generation can be one way to do quantum frequency translation. It has a large translation range, like more than 100 nanohertz is possible, high efficiency, commercially available. But it has a strong Raman noise and no fine tunability is possible. There are some weak points. And there is also another method for quantum frequency translation using an electro-optic effect. It's simply, you can think like a phase modulator. If you use a phase modulator and apply some RF voltage over here, the output would be original frequency components mode and original frequency plus minus RF frequency. Using this kind of scheme, that we can also do the single photon frequency translation. It is a low noise, okay efficiency, like a 10%-ish, commercially available, but it has a small translation range, which means from original frequency, we can tune like about 1 nanometer. and also the RF components are very expensive. So in summary, to shift single photon from one frequency to another frequency or one wavelength to another wavelength, we need an optical modulator, but this optical modulator can work only up to 1 nanometer. And some frequency and difference frequency generation can be done, but this one can be done, the translation is more than 100 nanometer. But we need to some method to somewhere between 1 nanometer to 100 nanometer to convert in that wavelength range. So in this case, we have a Bragg scattering wave mixing, another nonlinear effect, which will be explained in short. So in Bragg scattering, it has a pump 1 and pump 2. So pump 1 is here, pump 2 is here, is an energy diagram. And input single photon comes in and output single photon comes out. So pump 1 and pump 2, x-axis is a frequency domain, frequency. Pump 1 and pump 2 is here, and single photon comes in and single photon comes out. That's the Bragg scattering wave mixing. And for that, we need also phase matching condition, those kind of things. So using this, not only Bragg scattering, using all the some frequency generation, quantum frequency translation, what we can do is coupling quantum memories to fiber. And also, they have shown that through this frequency translation, the entanglement is also preserved. And frequency domain quantum interference has been done. And integration of 2 quantum dots is also possible. So they use a silicon nitride ring resonator for the Bragg scattering wave mixing. And using this kind of Bragg scattering wave mixing or some frequency generation, what we can do is a bright quantum light source. So at different wavelengths, they can shift its wavelengths to one wavelength, and they're gonna all the same wavelengths. And also, by tuning these wavelengths, what we can do is a tunable buffer or tunable delay. It's going to be really useful tool for quantum key distribution. So let's think about quantum light source, and let's think about quantum interference using quantum frequency translation. So that's a Hong-Mandel interference. Single photon comes in. When single photon comes in, it's going to be 50% reflected, 50% transmitted. And same thing, single photon comes in, 50% transmitted, 50% transmitted. There is some 90-degree phase shifting by when they reflected. So, and if we have 2 photon comes in, then 2 photon will come down or goes up. And the cases for 2 photon goes up, 1 photon up or 1 photon down will be canceled each other because of this minus sign. That's a Hong-Mandel interference. And so in experiment, what we are seeing is a sharp dip when there is over here we delayed its position of single photon, incoming single photon, and what we're seeing is a sharp dip as a function of a time delay. So first, we are going to do some experiment using this Hong-Mandel interference. So to do that, we need a 1-1 photon, which means a specially separated identical photons. So for spontaneous wave mixing, we can generate blue and red photons from optical fiber, and using a filter, we can separate them into 2 different paths. Okay, I'm going to skip that. And from here, so using spontaneous wave mixing, we generate photon pairs, which at 1 photon is at 1269.59 nanometer. Another one is at 1272.7 nanometer. And we use a filter to block one of the photon. And then we add them with a pump 1 and pump 2. and passing through the non-zero dispersion shifted fiber. And then there will be a shifted photons at 1272.7 nanometer, or something like that, and we detect the output. And there's a this single photon counts, and this one shows how efficiently we can convert the single photon from one wavelength to another wavelength. As you can see here, the input photon at this point, at this power, so with no pump power, all the photons are at this wavelength, and with the increasing the pump power, this photon goes down and this photon goes up. So almost more than 93% of a single photon is the wavelength is shifted into another wavelength. And also, one thing that I should mention is it has a really small Raman noise photons, about tens of hertz, really small, because we designed all those kind of things. So for quantum frequency translation, we need to consider Raman scattering. And that Raman scattering is this is a Raman scattering spectrum, and that's a pump wavelength. And if it's so near the pump wavelengths, there is a small Raman scattering, but at a certain wavelength range, it has a strong Raman scattering photons. And in our case, we are like a pump and signal photons are about 200 to 300 nanometers separated to each other. So we are somewhere here, so we have a very small Raman scattering. So using this kind of a quantum frequency translation, what we did is this way. So one is a signal photon is just same as this one, and idle photon we convert into 1272.7 nanometer, and we do Hong-Mandel interference. And we observe this nice sharp dip and visibility of 90%. And also we tune, it's a pump wavelength slightly, like a pump 1 and pump 2 is given like here. On pump 2, we shifted like from original wavelengths, we shift 90 gigahertz, and the Hong-Mandel dip decrease by shifting like 80 gigahertz. The Hong-Mandel is slight, we can see very small Hong-Mandel dip. So as a result, we can control the distinguishability of our single photons from photon pairs. Also, this one shows the two-photon joint spectral intensity. And oops. So this okay, I'm gonna skip it. So the second part is using this kind of, now we have a really efficient quantum frequency translation method, and now we are gonna use this one for another second experiment, which will generate a noon state, path number entanglement, or in short name, the noon state. This noon state can enhance this phase estimation over square root n times higher than classical case. And also Steinberg is here, who has done this n equals 3 noon states. And also I have done, about 10 years ago, I have done combining classical and quantum method. We could enhance like n times m sensitivity enhancement. This one has been done, and recently, so that's a typical noon state interferometer. So we use one beam splitter, a second beam splitter, moving the stage of a mirror. That's typical noon state interferometer setup. And in our case, we use this one. Frequency translation, quantum frequency translation. So blue and red, we shot into blue and red, which has an equal number. This one will go either blue or red, which is the same as here. That's a Hong-Mandel interference. And we use, over here, we use a mirror and going backward, and also pump going backward. And then it will be another beam splitter, which will be another quantum frequency translation stage. And then we're going to measure the interference pattern by sliding the position of this second quantum frequency translation. And that's our result, and it shows that's a class. This one is a classical interference, and that is a quantum interference. And as you can see here, quantum interference has a twice enhanced resolution than classical case. And also, since our system is all made with optical fiber, single mode fiber, it shows a really excellent stability. For sure, this measurement is done under the air conditioner, no blocking, no active temperature control, nothing, just on optical table. It has been done really, it shows a really great stability. So, also, okay, it's not our result, but they, in other group, they use Bragg-Skleton Fourier mixing, and they shows that they can convert from 1526 to 1408 nanometer, so which is more than 200 nanometer. They can translate the frequency. So it's of course, in that case, efficiency drops significantly, but still, they shows a possibility of making a wide range of translation. And also, recently I showed this talk from the Alex Gaeta's group. This one shows they use a 3 pump photon, and they want to try to mimic this 3-level atomic system using this quantum frequency translation. And I hope we can do similar things, but instead of mimicking atomic system, we are going to do multimode quantum interference using quantum frequency translation. So in conclusion, right, so that's our group photo, and that's Dongjin Lee, who has been most of this job, and really great, and thank you for your attention.
Okay, the session is open for questions or comments.
Thank you for a nice talk. So I have one question regarding maybe the almost last slide about ultra wide frequency conversion work. So in this kind of frequency conversion devices, what I don't know, what is the internal efficiency was around 10%, but total efficiency was below the one order lower, like 1%. What caused such lowering the efficiency for total?
Okay, thank you. Thank you for the question. So, internal conversion efficiency means let's assume everything in this photonic crystal fiber. From here to here, that's our internal conversion efficiency. But actually, there is a coupling. We should consider coupling between this part and to lens and lens. So if we consider all the losses, that would be the total conversion efficiency. So which means the transmission from here to here is only 10%. But in our case, the transmission is more than 50%. So in our system, we have really good total conversion efficiency. This one here, yes.
Okay, any more questions, comments? Otherwise, let's thank the speaker and move on to the next speaker. Okay, during the next speaker prepares, let me briefly explain his career. So the next speaker is Professor Dong-Won Kim, and he is currently the faculty member in our department. So he got the bachelor degree in Seoul National University in 1982, and he got the PhD at Princeton in the 89. So his research interest entails the ultra-fast optics, like the femtosecond and attosecond science applied to the atomic, molecular, and condensed matter systems. And I think he's currently the head of the attosecond centers in the Max Planck Institute in Postech. So he is going to tell us about the attosecond measurement and control of the quantum dynamics in atoms and solids under strong field today. So let's welcome the speaker.
Okay, thank you very much for introduction, Presider. Okay, I'm Dong Kim, and have been running the Max Planck Center for Attosecond Science in connection with the MPK, Max Planck Postech Research Initiative, during the last 10 years. So I'm very happy to share what I have done in terms of measuring ultra-fast phenomena in atoms and solid, namely electron dynamics, okay, on the strong field. So as we all know, okay, Nobel Prize in Physics this year awarded to these scientists and for their contribution to the attosecond technology. So I was very fortunate and have an honor to work with them, especially Ferenc Krauss. Okay, so this attosecond science technology, okay, so in my point of view, this is for controlling electron dynamics in quantum limits, in other words, atomic and molecular and nanoscopic system, okay? Hopefully, this technology will be used for quantum technology information in the years to come in 21st century. Okay, so as we all know, I mean, we have a laser developed in 1960s. Ever since that time, laser has impacted a lot in our lives and also in the science and technology. So in my view, there are two directions, okay, due to the development of laser, and then peak power tremendously increased over the last 60 years or so. And in the 90s, there was a big jump because new technology introduced, chopped pulse amplification. So because of this technology, the Nobel Prize was awarded a few years ago. And then also another pillar is for the developing the short pulse using the coherence of the laser light. So since developed the laser, the time resolution the human being has dramatically decreased, and entering into the 21st century, we break the femtosecond barrier, moving into attosecond regime in time. So also 2005, Nobel Prize was given to one of the basic technologies in dealing with this coherence, and based on which attosecond tolerance ever developed. Okay, so also Professor Hensch at MPQ was awarded for this work along with other scientists. Okay, so today I would like to introduce the basic technology of the attosecond science. I guess most of the audience may not know. Okay, so I introduced what is the CEP, carrier envelope phase, and how to control it. And then using it, how to generate isolate attosecond pulse, with which really you can follow the dynamics. Then I'll give you two examples, using them to follow the electron photo emission. So photo emission has been a very powerful tool to study the materials and so on of the band structure of the material, right? But up to now, we never think about the time, how long does it take to 1s electron or 2p electron being emitted from the system. Okay, now you have a tool to follow that. And also, okay, another example in the condensed matter, okay, you can manipulate electron motion attosecond time scale, not using isolate attosecond pulse. Okay, so let's start with the attosecond technology. Okay, so the CEP, carrier envelope phase, envelope phase. Okay, so this is envelope, and this is the center of the envelope. Okay, as you know, we have a light oscillating within the envelope. Okay, then we notice that peak of the electric field is slightly off the peak of the envelope. The difference is called like a CP. Okay, so to produce the femtosecond pulse, okay, we make an oscillator and to produce the femtosecond pulses, and then in this one we produce train of the femtosecond pulses. As the pulse is coming out, as you see before, and and each pulse has a different path length. So that, as you notice, that each pulse has a different phase. In other words, the CP slips, okay, automatically. So you need something to control it. Okay, so for that, Nobel Prize awarded about 10 years, 15 years, about 20 years ago. Okay, so so now why is the CP important? Okay, so I've shown you two electric fields. So envelope is the same, but as you notice that oscillation of the electric field is slightly different. Their phases are different. In fact, pi over 2 are different. Okay, suppose you have now you have a control so that every pulse from the oscillator has this phase or this phase. Okay, we have such a control. And suppose you do an experiment, you have done experiment with this kind of pulse. You have got the one result. And then you change the CP so that you have this kind of pulses coming out from your oscillator. Then you do experiment. And then you notice that their results are different. Okay, then that is due to the electron, how the electron feels electric field. Right? So electron fields, different fields, different electron fields, different field. Okay, to produce one result and second result. For example, for the light of 0.8 micron, the period is 2.7 femtosecond, half period is 1.3 femtosecond, quarter period is 0.6 femtosecond. So if you have a phase control less than quarter phase, okay, now you are entering into the attosecond time domain where you start controlling electron motion. Okay, people has done the experiment over the years. Okay, so take a C2H2 molecule, they shoot it, they try to find the yield of the dissociation. Then this is yield, and then the CP control. And notice that, okay, the yield is different for the phase. So basically, we have a control tool to direct the chemical reactions as you wish, and while it's really happening. So it's control of the reaction is totally different of what you have done before. So now, so how to generate the isolate attosecond pulse, okay? So very simple, geometry is very simple, okay? So you have this kind of high intensity laser. Okay? This is due to, this power becomes possible due to the CPA technology. And so then using this kind of intensity, we can go up to like a relativistic optics where the electron is accelerated too fast to like a speed of light. Of course, you need a little more intensity, but it's close. And anyway, we take such a laser focus into the noble gas like neon, argon, then you get the spectrum. Okay, so in 90s, people noticed this kind of spectrum. It's a highly modulated spectrum. So human being never seen this kind of spectrum before. So it was a big issue. Why is that so? Okay, over the 22 decades or so, people came to realize, okay, they can be explained in the semi-classical way. It's called the three-step model. So now we have atom here. Then you impose the, okay, so you have a Coulomb potential, you have electron cloud, okay, and you have electric field is imposed. And then, so this is the field strength, it is strong, and then you know that Coulomb potential is distorted. So we have a wall, then electron tunnels out. As soon as it tunnels out, you feel the field. Okay, it's a free electron, you feel the electric field, so it moves, accelerated, decelerated because of the field direction is changed, and then returning. Okay, so returning to the pair ion. okay, then colliding with it, it produces radiation. Okay, so it produces continuum radiation. Okay, so because the interaction is a Coulomb interaction between electrons and pair ions, and the maximum photon energy is determined by the maximum kinetic energy of the returning electrons and ionization potential, right? So let's consider like a multi-cycle laser. Okay, so the process I have described is happening every half cycle. So if you shoot this multi-cycle pulse into the gas medium, then basically in time domain, you have a train of the pulses. Basically, we know that this duration of each pulse is in attosecond time domain. Okay, so it's like we have a machine gun, like a brrr. Okay, now, so this is time domain. This is coherent event. So Fourier transformation will be, okay, this is highly modulated spectrum. Okay, now then how are you going to pick up the one pulse? Okay, so for that, okay, so we have a few cycle pulse. Okay, so this red one is filled, and then electron is ionized, and it going this way, coming back, hitting the parent time, produce radiation, and this electron is produced here, doing the same thing for the spectrum, and the electron is produced here doing this. It's just happening like this. So if you look at the low energy photon, then you usually recognize if the many events occurs. And because of that, then spectrum is highly modulated. But there is a situation, the one path, it produces highest energy. Okay, there is only one event. So this is high energy band, is continuum. Okay, you have a spectral filtering, you can pick it up, then you have a isolated attosecond pulse. This is a key technology. Okay, so this technology has been developed over the 20 years or so. Okay, now, so we have an isolated attosecond pulse. So then you're going to use it to emit to measure the photon emission. So I introduce attosecond streaking method. Okay, so let's consider you have a graphene, and then you shoot light. Okay, so whatever, and then we consider like electrons that comes out. It's a photo electron. So it's a 2s electron, 2p electron, right? And so, they are coming simultaneously. They're coming with a delay. If it is with a delay, then how much is the delay? Then can you measure it, right? So since this electron has a different angular momentum. Okay, so then electrons feel different centrifugal forces, and because of that, they have a phase delay. Okay, so you can estimate the phase delay, and since you have a phase delay in energy, then you can estimate time delay like this. So anyway, important message is, okay, the electron has a different angular momentum. They feel the different forces. Because of that, there is a phase, and then emission delay. So you can estimate and calculate. So about the 20 attosecond difference between two electrons. Okay, and also in graphene, so S electrons and P electrons are hybridized, right? And so they are anisotropic, not like carbon atom, isolated carbon atom, right? So that because of hybridization, there is anisotropy in potential. So like shown here, so this is potential, and this is rho direction in plane direction, and then this is G direction, is actual direction. Okay, so then because of this anisotropic potential, you can estimate the delay. Okay, so there is a delay between isotropic case and isotropic case. But in this case, the difference is very small. Okay, so in total, okay, we have a delay due to the potential anisotropy, and also due to the angular momentum difference between two electrons. Okay, so in total, it's around 20 attosecond or so. So can we measure it? Okay, so So you can do experiment like this. Okay, so you have a graphene target here, and then you send the isolated attosecond pulse and along with the light pulse. Okay, this mirror has two parts, inner part, outer part. They're moving independently so that you can sweep the isolated attosecond pulse across the IR. Okay, that is the situation. So attosecond pulse produce electrons. They're coming out at the time of attosecond pulse under the field, right? So it's this kind of situation, okay? You have attosecond pulse here, then you produce electrons. Then electron will fill this field, right? And then you move the isolated attosecond pulse, then you can produce electrons, and then you fill this field. Okay, so it's going on. So what will be the final momentum of the electron produced? Okay, so basically you deal with F equal ma equation. Okay, so electric field can be written with the vector potential like this. Okay, so at the end you can work it out. It's an easy one. So momentum change of electron is nothing but the vector potential at the time of photoionization. So suppose like you have a light field like here, then electron is produced, then the electron field this field. At the end, this electron will have an additional momentum like this much, which corresponding to vector potential at the time of birth. Okay, so I can sum it up like this. Okay, so I have a light field here, then I have attosecond pulse. We have attosecond electron pulse here. Okay, and then this electron will have a final momentum which corresponding to this vector potential. So at the final momentum will be like this. And if you have an electron pulse here, and then this final momentum, this electron pulse will be like this. Okay, if you consider scanning this one through the field, then you can notice this momentum space or energy space of electron is oscillating like this. Okay, you sweep this electron kinetic energy, you're sweeping the delay of the second pulse with this light field. Okay, you have this oscillation field. And basically, if you follow the centroid, and this is the vector potential of the light field. This is the first ever measurement, direct measurement of the vector potential in the human history. Okay, then you can make a derivative. This is a light field associated with it. Okay. Now, okay, you consider two events happening. Like 1s electron, 2s electron comes out, 2p electron comes out. So we have a one shot, we have two events happening. Okay? So one free electron comes out A state, like a 2s state, and the 2p state. Okay? So there is a time delay. Okay? So then you do the same thing. Then you'll have this kind of streaking. This is called attosecond streaking. Then you notice the time delay between two streaking. Okay, this time delay represents time delay between two electrons, right? So this is a real image of the apparatus. You have a time of flight spectrometer, attosecond pulse, and light fields come together, focused here, the graphene is here. So this is a measurement. Okay, so the two electron follow this streaking, 2s electron follow this streaking. So you do analysis, and then you notice the time delay of 20 attoseconds. So this is very close to the expectation. Okay, so basically, you have a tool to follow the electron dynamics in atomic system and nanoscopic system, and then we have a tool to control them. Okay, the second example is semi-metallization. Okay, so we're dealing with the genotunneling process in insulator. So you consider the insulator. So can you move the electron from valence band, conduction band in attosecond time domain? Okay, can you make insulator metal? Right. So this is a simple band diagram. Okay, so this is electric field, and this is x-axis is electric field. So without field, okay, you have band gap. That's the insulator. So as you all know, and also studied in the undergraduate, so when you apply the field, then the energy level is dispersed because the stock broadening and stock shift. Okay, there will be a critical field where a two band gap is with each other. In order, the band gaps collapse, right? So suppose if we have a few cycle pulse, as you notice, duration is so short, the variation of electric field within envelope is changing dramatically. Suppose this is a critical field, and then only this moment, okay, the band gap is closed, then there is a chance to electron move from bottom to the top, then current flow, right? So the question is, are really happening? If it happens, is how nonlinear it is. Okay, can you control with the CEP? Okay, can you switch the current flow direction? How fast can you do that? Okay, so we set up this kind of experiment. Okay, this is insulator, and then you put the electrode at gold. As an electrode, you put the ammeter to measure the current flowing between the two electrodes. Then you apply the CP control laser light. Okay, so that hoping that this medium becomes semi-metallization. So now you try to change the CP. So here's the example here. So this is CP, okay, there is a critical field like this. And then, okay, over this region and this one, we have a semi-metallization, current might flow. But you notice that it's asymmetric. So that we expect we have more current in this direction, right? And then this is a different CP, but they are symmetric. But direction is opposite. And effectively, we don't expect current. Okay, and then this is opposite to this one, so now you expect the current will flow this direction, right? So you expect as you change the CP, then current flow, what you measure here, will be different. So now we control the CP using this wedge of the prism, okay? You move in, and you measure it, you make a spot here, then move, then make another measurement, and then move another measurement for the current. Okay, so we expect the change of the current signal with respect to wedge position, meaning the CP. Okay, so this is a measurement. Okay, so we measured with the CP calcium fluoride. So then red one is when the light shined like this direction, then as you expected, the signal is changing dramatically up and down. And then you change the field parallel to the gap of the electrode. Okay, so basically most of the electron may not be collected by these two gold electrodes. So that you expect the signal will be very low, as it is. So then we know that this period of this signal is same as the CP control. And also the current, the signal is changing with change of the field direction. So we know that this current is field driven, not driven by the voltage due to the accumulated charges. Okay. So then the next one is what is the variation of the current charge transferred with the field strength? Okay, then you see the nonlinear increase as you expect Gino tunnel in case. And then try to set up the pump flow experiment to check how fast it can be switched. So here is one. We add another arm, okay, and so this arm is go to this direction, okay, with the time delay before, so that there are two poles. There is a time delay at the T here, and the first pulse is strong, so that but it's parallel to the electrode. So this one prepare the medium, okay, just ready to go to switched, okay. But the second pulse comes in with a weak pulse, but it's perpendicular to the gap, so that it will sweeping it. So that the the event is very instantaneous, so that we expect the signal will be follow the shape of the driving force. So you see this kind of thing. Okay. So we know we can measure the charge, absolute value. Then you can estimate considering geometry, we can estimate the resistivity like this. We noticed that this increased 17 orders of magnitude. This is really dramatic increase. And also, when you change the CP, you flip the field, okay, then current direction is flipped. So this proves that this is field driven, not current voltage driven. And then also, if you look at the time window, it's changing one direction to direction, it's changing within 1 femtosecond. So really, we have a control the current in attosecond time domain. So this plot shows you clock frequency, clock speed of our computers and handphone and so on. So we know that it's around the 3 gigahertz. This is around 3 gigahertz limit. And this one reached saturated around the beginning of the 21st century. Last 20 years, never increased because of the technological limit. But if you use this technology, okay, then you can make a device running in petahertz, like 1 million times faster. Of course, there are lots of has to be done to realize this one, but at least this gave us a vision to go that direction. Okay, this phenomena is universal, or only happening in the certain material. Okay, so we try out different samples. Like, so I show you the result in calcium fluoride. Okay, so then we try the silicon oxide because the band gap is different. So there maybe band gap somehow play some role. And then anyway, but you try to aluminum oxide, it's of a similar band gap, it's a different crystal structures. Okay, so basically we tried out these 3 samples and we repeated the same experiment. Like CEP versus charge and the electric field versus this one, the behavior is all same. Okay, so why they are same? This is interesting, intriguing question. So, but already in 1950s, we are very smart, and so Vanny and Stark already considered this situation. They solved the Schrödinger equation in periodic potential external field. They found out this is a solution, putting their solution, okay, and this is space, and they have a band, okay, with equal spacing. And then when you increase the field, okay, then this function becomes a delta function. In other words, electron wave function is confined, it's localized. It's called the Vanny-Stark localization. And so this is a rough estimate for the Vanny-Stark localization. So you put the numbers for different materials, and then you got this one. This is a less than lattice spacing. So even though we have a different structures, but this field is so strong, so that Vanny-Stark localization, so electron doesn't see long range order. So that's why we have observed the same phenomena. Okay, so let me conclude my talk. So I hope that I shared with you that CP is under control. And then because of this, we have isolated attosecond pulse available with which you can follow the electron dynamics and control in quantum limit. And so, this is fundamental processes happening in nature with their time scale. So this reason, we have still lots of fundamental processes happening, so we can follow their dynamics. So outlook, okay, so we need to current attosecond pulse is in XUV around 100 electron volt or so, a little higher, but to explore more, okay, so we need the hard X-ray in attosecond domain, even femtosecond pulses to follow the nuclear dynamics. Already, there are many ideas out there how to achieve that. So if you do that, And then really you can make a movie of the electron cloud. So basically, diffraction is due to the scattering from the electrons, right? If you have enough fast time to follow the motion of the electron cloud, then you have a movie, electron cloud movie. That will be holy grail of the X-ray scattering and diffraction. Okay, thank you very much for your attention.
Okay, the session is open for questions or comments.
Thank you for a nice talk. I have a simple question. So what is the average power of your attosecond lasers normally?
Oh, yes. Number of photon is very weak, okay? So kind of a picojoule per pulse. So in other words, like you have 10 to 6 or 10 to 7 photons per shot. It's very small. Yes. So, but such of, I mean, of course, you have more photons to have a better signal-to-noise ratio. Okay, of course, there is work going on to improve the photon numbers in isolated attosecond pulse. Okay, that's one direction to go. Basically, you need a higher power laser than what you have. But at the same time, you need to move on the energy of the attosecond pulse.
Thank you, Professor Kim, for your nice talk. I have a simple question. And when you choose the graphene, is there any special reason to observe the SNP orbital electrons motion?
No, I don't have any particular reason in material scientific point of view. This is graphene is popular, and one of my colleagues was doing calculation. Okay, so he is also a theorist interested in dynamics. So he had done calculation, then he approached me, can you measure it?
I see. Then
So we tried. But yeah, I mean, you're welcome your suggestion for trying out different material. I mean, I'm always open.
okay, then it means that there is no technical barriers to choose other materials instead of graphene.
I mean, the photon energy of the attosecond pulse is 100 electron volt or so. Okay, so I mean, so we need to see the things with that photon energy,
Okay.
right?
Yeah,
You can see the deeper inner electrons, right?
yeah, thank you.
Okay, any further questions, comments? Otherwise, let's thank the speaker. And for the lunch, as I announced in the morning, it's in the second floor, and the general participants, please go to the ballroom and invite the speakers to the Blue Hills. If you don't know where it is, you can just follow the organizer, Jaehoon Park, who is standing there.
lunch and coffee. So I'm Gil Ho Lee, chairing this session, and I'm very honored to introduce Professor Andrew Cleland from University of Chicago. So he's John A. McLean, Sir, Professor of Quantum Engineering Innovation at the University of Chicago. And he got BS, a bachelor's degree and PhD in UC Berkeley. And before joining the University of Chicago, he also served as a professor at UC Santa Barbara. And his research focuses on developing superconducting quantum circuits and the nanoscale optical and mechanical devices. So he's a word expert on the mechanical resonators and the low temperature and optical and mechanical devices. So let's welcome the speaker together.
Thank you, Professor Lee, for the kind introduction and also for all of your work in putting together this conference. It's been really nice. I'd also like to thank all of the organizers for putting together this wonderful conference and to the prior speakers for their really high quality talks that I've been enjoying. And I hope that I can just rise to the same level of performance here. So I'm going to be talking about a topic that's rather different from most of those that we've heard, quantum acoustics. I hope to introduce the subject to you in a fairly gentle way so that you can follow what my group has been doing in this area. I have also been playing around with machine learning systems, in particular ChatGPT and DALL-E. And so just as an example, I put up this image that was generated by DALL-E when I asked it what it thought two entangled phonons would look like. Furthermore, I put a copyright here for those of you who've been following the copyright issue with neural network systems. This is a controversial thing to put up. Okay. So basically what my group has been working on is exploring quantum acoustics, which is basically mechanical systems operating in the quantum regime. And we do this for a number of different reasons. One kind of basic reason is that many sensors that are used in science are fundamentally mechanical in their nature. And so that if you can explore mechanics at the quantum limit, then maybe you can perform sensing in the quantum limit. And I think, in fact, the next talk that's going to be given by Professor So will address one way to look at this particular problem. Another is that mechanical systems have been shown by a number of groups to be able to achieve extremely high mechanical quality factors, which means lifetimes for energy stored in mechanical systems. So that means that these provide an interesting possibility for storing quantum information if one can control these systems at the quantum limit. Another very interesting idea, which actually we've already heard about in some of the prior talks, is that you can use mechanics or phonons to link quantum systems together. And one area that my group is looking at is actually linking superconducting qubits to atomic-like systems, such as defects in diamond or defects in silicon carbide, because there are interesting opportunities, for instance, for microwave to optical transduction in the quantum limit. But really, what really drives my interest in the field of quantum acoustics is the applications and development of fundamental science, looking at quantum mechanics in the mechanical limit. And as you'll see when I get to the end of this talk, one very interesting question is, can phonons, which are of course the quanta of mechanical vibrations, can they serve as mobile qubits in a quantum computer? It's a very speculative question, but I think the level of speculation in this question has been reduced significantly, in part because of recent results from my group. So the kind of mechanical system that I'm going to describe to you today is something called a surface acoustic wave. These are excitations that you can generate on the surface of a solid And you can see an example of such an excitation here. This is a single frequency, single wavelength excitation seen in cross-section. And it comes about because you can actually linearly combine transverse bulk acoustic waves with longitudinal bulk acoustic waves, which travel at different velocities and normally don't interact at all. But when these hit the surface of a material, you can actually get them to interact and, in a way, combine into a new type of excitation that's called a surface acoustic wave, or more historically, a Rayleigh wave, named after Lord Rayleigh, who was the first person to realize that you could explain these excitations in this way. And of course, the sort of practical question is trying to understand earthquake waves that are basically surface acoustic waves on the surface of the Earth. Here, however, we're going to be talking about very high frequency surface acoustic wave excitations and the possibility of controlling these in the quantum limit. However, these were not originally developed for quantum applications. They've actually been used since sort of the 1960s in very practical room temperature applications, which I'll describe in a second. One reason that these are useful is that it's very easy to interact with these surface acoustic waves with electrical signals if the material that you're working with here is a piezoelectric material. So piezoelectric materials, very simply, are ones that generate an electric field if you strain them, in other words, if you distort them, or analogously, if you apply an electric field to a piezoelectric material, you can cause it to distort or strain. And one way to do that with a surface acoustic wave is to place metal electrodes on the surface of the material, here shown where the electrodes are spaced by half a wavelength, where if you apply one sign of an electrical voltage to all of, say, the yellow electrodes, and the opposite sign voltage to all of the green electrodes, then you will generate an electric field that has the same geometric pattern as the strain that's shown in the surface acoustic wave. So if you then oscillate those voltages at the right frequency, you can get very strong coupling between that electric field and the surface acoustic wave. By applying such a voltage, you can generate a surface acoustic wave. Or conversely, if you try to detect an electric field at the corresponding frequency and wavelength, you can thereby detect the surface acoustic wave, or in other words, transduce between electrical and mechanical signals. And that's the fundamental basis for how surface acoustic wave devices work. You can build structures that work from megahertz to gigahertz frequencies, and you can build devices that work at room temperature with quite good performance as what are called delay lines, acoustic resonators that give you a way to store electrical signals, and you can do pulse shaping and pulse compression with these types of structures. Now, we want to work with these in the quantum limit, so we want to work with phonons, which are single quanta of these types of excitations. But let me emphasize that for the experiments I'm going to be showing you, the excitations, the surface acoustic waves, even if they are at the level of a single phonon, still represent the mechanical motion of an enormous number of atoms. Okay, something for the devices we make on the order of 10 to the 15 atoms. And yet, as I hope to show to you, these phonons are really quantum objects. If you have one phonon in a surface acoustic wave, you can't divide it in two. Even though it represents the motion of a huge number of atoms, it is still a quantum object. And I still find this result kind of surprising. Now, in order to control and detect surface acoustic waves at the single phonon level, you need a quantum device, a way to quantum control these devices. And what we use are superconducting qubits, which I will show to you in a couple of slides. However, before I get into that, I want to describe to you a simple classical surface acoustic wave device, which was the first device that we tried to investigate at the quantum level. But you know, the basic idea of trying to do quantum mechanics with these types of devices, we were not the first group to do this. That honor, I think, really belongs to Per Delsing's group in Chalmers University, where they had the signature result with first author Martin Gustafsson published in Science in 2014, where they coupled a qubit here to a transducer, one of these interleaved metal finger structures, which are used to launch and detect surface acoustic waves. And by launching surface acoustic waves from this device, they showed that they could affect the behavior of the qubit in the quantum limit. There were then a number of other experiments that followed this from a number of different groups, but I'm only going to talk about the work that came out of my group. So the first structure that we looked at was the simplest kind of mechanical structure you can make, which is a harmonic oscillator. In this case, a surface acoustic wave resonator. So the device is shown here. I hope there's not a problem. The device is shown here. This was a device that my student Kevin Satzinger, who's now working at Google in Santa Barbara trying to build a quantum computer, this device was fabricated on a piezoelectric substrate. And this device, as with all the devices that I will show you, was fabricated on lithium niobate, which is a very strong piezoelectric. And very conveniently, you can buy it in single crystal form on highly polished wafers. So it's compatible with the kind of lithography that we use to make this structure. So at the center of the structure, there is a transducer. So these are interleaved metal fingers with a spacing of about 0.5 micron that corresponds to a frequency of about 4 gigahertz in lithium niobate. So that structure is used to launch and detect surface acoustic waves. When you excite a surface acoustic wave with this transducer, it will travel in both directions away from the transducer until it hits this structure here on both sides of the transducer. This is just a set of metal fingers that act as an acoustic mirror. Each finger, because it has some mass and it changes the electrical properties of the underlying substrate, reflects a small fraction of the incident wave, about 1%. And by spacing these fingers by 0.5 wavelength, you will get reflection from each finger that will add in a coherent fashion, such that when you've encountered roughly 100 of these fingers, you will completely reflect the wave back on itself. And that occurs on both sides of this structure. So what you now have is a Fabry-Perot resonator trapping the surface acoustic wave between the mirrors and interacting strongly with the transducer in the center. So this is just a Fabry-Perot acoustic resonator with a 4 gigahertz center frequency. Now, Kevin made this device, cooled it down on a dilution refrigerator, and measured it using a completely classical device, a vector network analyzer, where he measured the amplitude and phase of a microwave electrical signal sent from this bond pad to this bond pad. And this is what he measured. He can then fit this response by fitting geometric capacitance and stray inductance. That gives you these straight blue lines here that give you the overall broad frequency response. To get the finer frequency response, he used a standard model from surface acoustic wave theory, developed in the 1960s, called P-matrix theory, which has 4 adjustable parameters and gives you a very good agreement between P-matrix theory and the measured response. From the theory, you can then extract what is going on in the device. Each one of these sharp resonances is one Fabry-Perot mode trapped between the mirrors. You can extract the internal quality factor and the free spectral range, which are both pretty much what we expect. And interestingly, you can also explain why these series of resonances die out once you get about 50 megahertz on either side of the central resonance. That's because the mirrors which here and here rely on the phase coherent reflection of the incident acoustic wave in order to reflect it, that's when those phase coherent reflections come out of phase sufficiently that the mirror's effectiveness starts to fall. So this stop band of about 100 megahertz is exactly what you expect for this type of mirror structure on lithium niobate. And it means that you're really only trapping a finite number of modes in the mirror set. Okay, so the next experiment was to try to explore this device in the quantum limit, to try to couple superconducting qubit, which I will explain to you in the next slide, to one of these devices. We give you a very complicated response that's hard to understand. So in order to simplify that, what Kevin did is he took these mirrors and he brought them up as close as possible to the transducer, making the free spectral range of the resonator large enough that only a single mode would fit in the mirror stop band. So then it becomes a single mode resonator that's much easier to understand when you interact it with a superconducting qubit. But let me explain to you how a qubit works first, although admittedly this was extremely well described by Professor Oliver's presentation yesterday, so I will go through this very quickly. This is exactly the same type of qubit that Professor Oliver described yesterday. Two Josephson junctions connected in parallel, forming an inductor that is placed in parallel with a capacitor. This is an LC resonator in the standard electronic circuit, but the nonlinearity of the inductors means that the inductance in this LC circuit is dependent on how much current you flow through it, or in other words, how much energy you store in this resonant circuit. And that anharmonicity means that when you put one photon of microwave energy into the circuit, you get a different resonance frequency than if you put two photons, giving you this so-called electronic atom behavior. More formally, you can solve Schrödinger's equation, where the potential in the Hamiltonian has this cosinusoidal dependence instead of the harmonic oscillator dependence that you would get with a linear inductance, giving you a series of energy levels whose spacing is not the regular harmonic oscillator spacing, but instead has a few percent anharmonicity due to the nonlinearity of the inductor. So we make these devices to work somewhere in the range of 1 to 10 gigahertz. We typically only use the lowest two levels, which I label as G and E for ground and excited state. And sometimes we use the third level that we label as the F state. This is what one of these devices looks like. Again, Professor Oliver described this to us yesterday. This cross-shaped structure has a capacitance to the surrounding ground plane, that's the C, and then the two junctions at the base of the cross, here and here, are what give you the L, and you can tune the inductance of that L by coupling flux in from an external control line, the Z control line right here. You can also couple in microwaves through this XY control line to excite the qubit. This is what a Josephson junction looks like. And in general, if you're just dealing with the bottom two states, the ground and excited state in the qubit, you can write the quantum state of the qubit as a linear superposition of those two states with a relative amplitude that can be represented by the angle theta on the Bloch sphere and a relative phase between the ground and excited state that can be described by the azimuthal angle phi on the Bloch sphere. You can control the relative amplitudes of the ground and excited states by applying microwave pulses through the XY control line, and you can control the phase by changing the frequency of the qubit using a Z-control quasi-DC pulse. This gives you full vector control of the qubit, and then we measure it using this readout resonator, which has a different resonance frequency when the qubit is in the ground state compared to the excited state. So by applying a weak microwave pulse to a transmission line that's coupled to this resonator out of the frame of the photo, you can projectively measure the qubit state in the ground or excited state with quite high fidelity. In the best qubits that we make, we can get single qubit gate fidelities of about 4 nines, and our controlled Z gate, which is the simplest 2-qubit gate that you can get when you couple 2 of these qubits together. The best fidelities we've gotten are about 99.5%. And readout fidelities are typically around 95%, but those are not record-breaking. So what we do is we use these qubits to control the phonons in our acoustic devices. So going back to Kevin's surface acoustic wave resonator, here is the device that Kevin made, coupling this qubit to a surface acoustic wave resonator, here with the transducer right in the center and the 2 mirrors butted right up against that transducer. The coupling between the qubit and the resonator can be controlled using a tunable coupler that I can explain at the end of my talk if somebody wants to know more about it. But basically, we can use this externally controlled coupler to vary in the time domain the coupling strength between the qubit and the resonator, thus turning, if we want, the interaction off or turning it on with a coupling strength of a few megahertz, meaning that you can transfer a quantum of energy between the qubit and the resonator over a time scale of order a few nanoseconds. So what Kevin did is a number of different experiments. I'm just going to show you a couple of them. This is the major one. This shows a classic interaction between a 2-level system and a harmonic oscillator. Here, the qubit and the single mode in the Fabry-Perot acoustic resonator, where energy is being swapped between the qubit, whose probability of being measured in the excited scale, in the excited state is shown by the color scale right here, starting as a function of time in the excited state and then oscillating between ground and excited state as one quantum of energy is swapped back and forth between the qubit and the resonator. And this overall chevron pattern is the classic shape that you get for a 2-level system interacting with a harmonic oscillator. So this basically shows that we have quantum control over excitations in this acoustic resonator, and you can use the qubit further to do Wigner tomography of the quantum states in the acoustic resonator. I can again describe this at the end of the talk if someone wants to know more. Here shown tomographs in experiment and theory for 3 states in the resonator: ground state, 1 phonon Fock state, and a superposition of the ground and 1 phonon Fock states. So basically, this shows that we have quantum control of phonons in an acoustic resonator. This was sort of our first accomplishment in this direction. The next experiment we did was done by Audrey Bienfait, who's now a professor at École Normale Supérieure in Lyon. She took a device, an acoustic device, similar to Kevin's, fabricated again on lithium niobate, with an acoustic, a transducer in the center of the device, and then pulling the mirrors in Kevin's device very far away, such that the spacing between the mirrors was 2 millimeters. If you now excite momentarily the transducer, you can emit energy that will form pulses that travel in both directions away from the transducer, reflect from the mirrors, and then come back again, re-interacting with that transducer about half a microsecond later. Audrey coupled this device to 2 superconducting qubits, each coupled to the same transducer, where each qubit had a variable coupler so that we could control the coupling strength between the qubit and the acoustics. These devices were made on separate substrates. I forgot to mention this about Kevin's device, where the qubits were fabricated on a sapphire substrate. 1 qubit is right here, the other qubit here. The acoustics were fabricated on a chip of lithium niobate. This was then flip chip coupled to the sapphire chip, and the 2 attached together as shown in cross-section right here. Audrey did a number of experiments with this. I'm just going to describe 2 of them. So this first experiment is where she creates phonons with each qubit, launches them in the acoustic resonator, and catches that phonon, that 1 quantum of energy, with the other qubit. So here what I'm doing is I'm plotting the probability of measuring the qubits in the excited state as a function of time, starting with both qubits excited, releasing one phonon through a very carefully shaped release into the acoustic resonator, waiting some time and then doing the same thing with the other qubit, so that now you have two phonons traveling in a time bin encoded fashion. These are each pulses of energy representing a single quantum, traveling from the transducer to the mirrors and back again. She then waits the appropriate amount of time such that the phonon emitted by qubit 1 can be caught now by qubit 2, and she catches it with about 64% efficiency. So the other 36% of the energy in that phonon was lost, or more precisely, 36% of the time the phonon doesn't make it, okay? The other 64% of the time the phonon makes it. It's not a divisible object. And similarly, she catches the phonon released here by qubit 2 with qubit 1, catching it with the same efficiency. So this shows that you can transfer over some distance a quantum of energy in the form of a phonon. A kind of more interesting experiment is this one right here, in which Audrey only excited one of the qubits, qubit 1, carefully released a half phonon from that qubit. Again, these are not divisible objects. So what this means is that on half of the experiments, qubit 1 released a phonon. On the other half, it did not release. But we don't know that, of course, until we measure the qubit at the end of the process. That half phonon, which of course represents entanglement between the qubit 1 being in the excited state with no phonon in the acoustic device, superposed with qubit 1 being in the ground state, having released one phonon into the device. That phonon, then, or half phonon, travels in the device, and then we catch it with qubit 2 with, again, the same efficiency as the one phonon process. Transferring the entanglement here between qubit 1 and the phonon to now qubit 1 and qubit 2. If there was no phonon in the device, qubit 2 has nothing to catch, so it remains in the ground state. If there was a phonon in the device, qubit 2 catches it, and you now have a Bell state between the two qubits. So we can generate a quantum Bell state between the two qubits mediated by a phonon. So this shows you have a quantum coherent system, okay? And the fidelity for the Bell state is 86%. It's precisely the square root of the efficiency. So what we've shown here is we now have quantum coherence of mobile phonons. These are not phonons trapped in a resonator. These are really pulses of energy that are traveling along the device. Okay, the next slide, I'm going to show you basically a composite of two experiments. The first set of experiments done by Etienne Dumour, who's now a staff member at the CEA in Grenoble, and my graduate student, Hong Chiao. So the device that Etienne made is shown here. Again, a lithium niobate device, but now with two transducers separated by 2 millimeters, where these transducers are specially made so that they only emit in one direction. So they're unidirectional transducers. This transducer only emits acoustic energy to the right. This transducer only emits acoustic energy to the left. And of course, they can accept energy coming the opposite direction, okay? And each one of these transducers was coupled to a separate qubit, where again, the qubits are fabricated on a sapphire substrate and the acoustics on a lithium niobate substrate, and the two are flip chip bonded together. And again, we have these variable couplers that allow us to control the coupling strength. Okay, Etienne did a series of experiments basically reproducing the results that Audrey got. So showing that, for instance, you can send phonons from one qubit to the other in either direction. You can send a half phonon from one qubit to the other, generating an entanglement between the qubit and the phonon, which translates then, when the other qubit catches it, to a Bell state between the two qubits, getting the same fidelities as Audrey got. However, the really interesting thing to do here is to introduce a new element in the device, a beam splitter, okay? So this is a device that will, just like an optical beam splitter, split a phonon. But remember, phonons are supposed to be non-divisible quantum objects, even though they represent the motion, kind of unconstrained motion, of a huge number of atoms. So they're kind of quasi-particle. So are they really indivisible? Or is all this indivisibility that I've been talking about previously just because of the qubits? Well, here's the device, and this device was made by Hong Qiao. Here's a qubit, here's a qubit, here's a variable coupler, here's a variable coupler. Here's one of these unidirectional transducers, here's the other one, and here is the beam splitter in between the two transducers. But notice that the beam splitter has been intentionally positioned closer to this transducer than to this transducer, so that when signals are emitted from these transducers, they will not arrive at the beam splitter right in the middle, but instead we build in an asymmetry to make it easier to debug any problems. What does the beam splitter look like? Well, it's just a bad mirror. So it's a series of metal fingers that if you had enough of them would be a mirror, but here we kind of guesstimated how many fingers to put so that this beam splitter would reflect roughly half of the incident energy and transmit the other half. Turned out we guesstimated a little bit wrong. The beam splitter in this experiment was a 60% reflecting, 40% transmitting beam splitter, but that's okay. Okay, so what do you want to do with this? First you want to see, does this beam splitter work the way an optical beam splitter works? Where if you send one phonon into the beam splitter in the classical limit divides half the energy, but remember, phonons are supposed to be indivisible objects, so it should not be able to divide this phonon. Instead, what you should get out is an entangled state where either a phonon has been reflected from the beam splitter or it has been transmitted. So in other words, you generate entanglement, here representing these two output phonons in qubit notation, where you should get this basically entanglement for free, just from a bad mirror. This is, of course, the way optical beam splitters work, okay? And people rarely think about it, but I think they're, at their heart, they are fundamentally very, very intriguing devices that you get quantum entanglement just from a bad mirror, okay? Maybe a trivial observation, but I find it very, very intriguing. Okay, so of course the question here is, does this work with phonons? So here's the experiment. You take this device, you excite one qubit, well, we'll just show it for qubit 1. You do a timed release of one phonon from this transducer, so it will travel to the beam splitter. It will interact with the beam splitter and then hopefully divide 60% of the time reflected, 40% of the time transmitted. And then we can catch those split phonons with the 2 qubits. So here's the experiment, okay? We excite qubit 1. We carefully release a phonon from qubit 1. It interacts with the beam splitter right about here, is partly reflected back to qubit 1, and because it has a shorter distance to travel, that reflected signal interacts with qubit 1 first, okay, and we catch it. And then the remainder is transmitted to qubit 2 and is caught a little bit later because of the asymmetry in the device by qubit 2. And qubit 2 doesn't catch as much as qubit 1 because it's a 60-40 beam splitter. So you'd say, well, this experiment has failed. We've got 60% of the signal in qubit 1 and 40% of the signal in qubit 2, so the phonon was divided. But in fact, the real interesting data is the most boring data on this plot. I've got actually 3 lines plotted here: probability of qubit 1, probability of qubit 2, and PEE, which is the probability on any one of the repetitions of this experiment that both qubits were excited at the end of the process. And that very boring data is always 0. Okay, it starts over here because both qubits are not excited, just one of them is. It stays 0 once qubit 1 has emitted. It stays 0 when qubit 1 has caught its share of the phonon, and it stays 0 when qubit 2 has caught its share of the phonon. It's always 0. So in other words, you never see an instance in which both qubits are excited. It's either qubit 1 was excited or qubit 2 was excited, with roughly 60% of the time qubit 1 being excited, 40% of the time qubit 2 being excited, but never both. So the qubit cannot, the phonon cannot be divided. It is a quantum object, even though it reflects the motion of, 10 to the 15 atoms. I still find this kind of amazing, okay? The qubits here are kind of acting like photodetectors, but remember, they are quantum coherent. The coherence in the phonon is transferred to the qubits, unlike a photodetector, which produces a measurement. So we can actually continue to manipulate the phonon after it's been caught by the qubits. So what happens here is that you can measure the two qubits simultaneously and figure out what the density matrix of the final state is, okay? And that's shown here. So here is the density matrix for the final state, and what you see is that the qubits are in a Bell state as expected. The Bell state generated by the beam splitter is transferred to the qubits, okay? With the measured data, the solid bars here, and the expected result, including the measured loss in the device given by these dashed lines. So you see we have very good agreement, and the fidelity to an ideal Bell state is about 82%, okay? So this is really a signature result. We're really doing quantum manipulation of these phonons. Okay, so they're really true quantum particles. So now the next really interesting experiment is, of course, one of the most famous experiments in optics, the Hungo-Mandel effect, which we've already heard about in prior talks, where it's now just used as a kind of calibration technique. But here we want to provide the physics for it. Okay, so what I showed you already is if you send one phonon into the beam splitter, you get 2 half phonons out. The Hungo-Mandel effect is what happens when you send 2 particles. So Hungo-Mandel effect is, of course, for photons, but I'm going to talk about it in the language of phonons. You send 2 phonons into the beam splitter at the same time. You very carefully design these phonons to be as identical as possible. Same energy, same envelope, and you make sure they hit the beam splitter at exactly the same time. What does quantum mechanics say you should get out? It says that you should get out 2 phonons going the same direction, so you get a kind of bunching effect, but where the output is a superposition of both phonons going one way, superposed with both phonons going the other way. So in other words, this should be your output state, okay? That's the prediction from quantum mechanics. And this, of course, was famously done by Hungo and Mandel, published in 1987, one of the most famous results in quantum optics. So we did the same experiment using 2 phonons and trying to make them as identical as possible. And there's sort of 3 choices you can make as far as arrival time of these phonons. Once you've made the phonons be as identical as possible, meaning having the same energy and having the same wave shape, okay? And I'm just going to show you the data for the simultaneous arrival at the beam splitter. Okay, we have data for different arrival times as well. So here's that data. Here's probability of measuring the qubit in the excited state as a function of time, plotted for both qubits. So we excite both qubits, and I'm plotting both the qubit probabilities and the probability that they're both excited. So here they're both excited. Here we release from qubit 2 first, because remember qubit 2 is further from the beam splitter. And the probability that they're both excited goes down with the probability of qubit 2. Then a little bit later, we release from qubit 1, timed so that its phonon will hit the beam splitter at the same moment as qubit 2's. They now travel, they interact with the beam splitter, and now what we should get out is a superposition of 2 phonons going one way, 2 phonons going the other way. But remember, the qubits are anharmonic. They can only catch 1 quantum of energy. So if a 2 phonon state hits them, they'll catch one of those phonons, but not the other one. So what happens? So here we see qubit 1 gets excited, and because it's closer, and sometime later, qubit 2 gets excited, and they get excited at the same level. Okay, so it looks like we're getting signals out. How do we know that the Hungo-Mandel effect is working? How do we know that they're not each detecting a single phonon at the same time? Well, again, you look at the probability that they're both excited. which followed the probability of qubit 2, but when qubit 2 caught a phonon here, it only went up a very, very small amount. It didn't stay exactly 0, okay? But it's pretty close to 0. So the main result is yes. Either qubit 1 is catching one of its 2 phonons, or qubit 2 is catching one of its 2 phonons. And actually, we've done other experiments to show that the phonon that was not caught in either of those cases, it travels back to the beam splitter, gets split, and we can then catch that second phonon with the 2 qubits. And we have experiments showing that. But basically, this probability of both being excited staying very close to 0 shows that the Hungo-Mandel effect is working. And in fact, the reason that we get some slight excitation, some slight double excitation, we think is because we were not able to make the waveforms exactly the same. Because these are emitted by 2 different qubits, it's 2 different tune-ups, it's pretty hard to get them exactly the same, given our limited ability to measure those waveforms. So if we have slightly different arrival times, then you get incomplete interference as some double excitation. And if you have very different arrival times at the beam splitters, then both qubits get phonons. In other words, the phonons don't bunch. And that's shown by plotting the equivalent of the Hungo-Mandel dip, here plotting the probability that both qubits are excited as a function of the relative delay. And what you see is that once you've gotten outside the sort of time, the time duration of the pulses of these phonons, then you don't have any bunching, and both qubits catch single phonons. But when you get into the region where the waveforms are interacting, and in particular when they're as identical as possible, you get a very pronounced dip going almost all the way to 0. Where it doesn't quite get to 0, again, because I don't think we're able to get the waveforms exactly the same. Okay, and so basically this shows that phonons are bosonic particles, completely identical in every respect except for polarization to photons. Okay? And so this brings us to sort of the kind of really dramatic and I think very exciting possibility, which is you might be able to build a linear mechanical quantum computer where the mechanics here refers to phonons. So we've shown we have single phonon emitters and detectors. I didn't show you, but we do have phase control over the phonons. We've actually built single phonon interferometers using this phase control. I just didn't show that data. And now we've shown that we have a single phonon beam splitter that obeys the 2 phonon interference in the Hungo-Mandel effect. This 2 phonon interference, by the way, is the basis for a 2 phonon entangling gate, controlled phase gate, in linear optical quantum computing. So you have to have this to build a linear optical quantum computer. We've shown that we at least have the physics in order to try to build a linear mechanical 2 phonon gate. But we haven't demonstrated that gate yet. That would kind of be the next thing to try to do. But basically, we have a complete toolbox for trying to build a linear quantum computer based on mechanics. And that's, I think, kind of the next phase of this experimental effort. So I've shown you all these things. The biggest challenge for us as far as trying to build a mechanical quantum computer is our acoustics are kind of lossy. The effective lifetime of our phonons in these devices is a little bit over a microsecond. That's not long enough to do anything complicated. We think what we know, we understand where the primary loss channels are, and we think that these can be actually significantly reduced by not working with bulk lithium niobate, but going to other systems. But we haven't really started to do that. I don't really want to speculate, so I'm not going to give you too much more information. This is my group that did most of these experiments. And this is to show that we can have fun too. And now I'll take questions. Thank you.
Beautiful data and talk. Now the session is open to the question. Please.
That was a beautiful talk, by the way. A very naive question. Why do you need the Bragg reflectors? If you didn't have them, wouldn't the waves be reflected from the end of the arm?
In principle, you can get some reflection from the end of from the edge of the chip, for instance. The problem is what happens with, if you have a very, very nice cut, the surface acoustic wave will make a 90-degree bend, go down the thickness of the wafer, and go on the backside. We haven't actually observed that, but when we've let phonons just go, we only get a very small fraction of them back.
And then you just need to make a Mobius strip.
We've talked about it.
Just a quick follow-up for what you alluded to in the lifetime. Is that determined by scattering then into the bulk of phonons? You were saying already a little bit at the end that thickness may be going to.
Yeah, so lithium niobate is famous for having sort of pronounced scattering into the bulk compared to other piezoelectrics. A lot of it is related to the fact that it has a very high coupling strength, so it's pretty easy for just little asperities on the surface to cause scattering into the bulk. But in fact, you don't have to look very far to figure out where that scattering is. If you just build a finite element model that can handle piezoelectric materials, and you give it all the lithium niobate parameters, and then you simulate an acoustic resonator, you will see significant scattering into the bulk just from the electrodes. So the electrodes are sort of the primary source of loss in these devices. And we actually have data, if I can get my slides back.
Can you change the screen? Yeah.
This is data that Audrey Bienfait took, showing when she launches a phonon in her device, which had a central transducer and mirrors on either side, she could look at the signal on each bounce. So this is 1 bounce, 2 bounces, 3 bounces, 4 bounces. And basically, the amount of loss that we see in each bounce corresponds roughly with what we estimate from these finite element simulations. So we basically think our biggest loss is in the transducer elements, the mirror elements.
Okay, one again.
Thank you for the nice talk, and I have a question about how did you? I think if electronics was controlled by the room temp electronics, I think, and why there is no coherent state?
So in the very first experiment I showed you with the vector network analyzer, the classical microwave source, to measure the properties of our Fabry-Perot resonator. Those measurements were done with an average of 1 phonon in the device, but they were actually coherent states. So those are basically Glauber states of phonons. Okay, but here in the qubit controlled experiments, we're using a qubit to emit the energy in the form of a phonon, and the qubit only has 1 transition available to it from the excited to the ground state. And so just like an atom, it has to emit the energy as a single quantum. So you get 1 phonon outputs when you use a qubit, just as an atom emits a single photon.
Okay, thank you.
Yeah, Professor.
Yeah, thank you for your very interesting talk. And then I have a technical questions. When you transmit the qubit signal, when you convert the qubit signal to the phonons, and also the signal, cross over the interface between 2 different substrates, then what about the efficiency? How can you control it?
Yeah, I didn't explain very well how we do that. So we have typically 2 chips. Sapphire chip on which the qubits live. It's a very good substrate for the qubits because it has very little dielectric loss and it's not piezoelectric at all. So the qubits have the best lifetimes on sapphire, or people also use high purity silicon. We have a lithium niobate chip, a strong piezoelectric that's flip chipped on top of the sapphire chip. The lithium niobate chip has its own wiring. So for instance, the transducers and the mirrors and all those things are made on the lithium niobate. The electrical signals from the qubits are actually inductively coupled to through a mutual inductance that's patterned on each substrate. So half of that mutual inductance is on the sapphire, the other half is on the lithium niobate. And as long as we can properly align the substrates when we couple them together, we can get pretty strong inductive coupling between the wires on the two substrates. And those wires are superconducting wires. So there's very, very little loss other than acoustic loss once the signal is on the lithium niobate substrate. So one source of loss that we have is that the wires on lithium niobate, because they're carrying, you know, gigahertz frequency signals, they start to emit phonons in the lithium niobate. It's a pretty small loss because it's just a wire with some ground planes, but it is a not completely negligible amount of energy that's lost that way. But again, most of the signal loss is once we are in the acoustics and we're getting this bulk scattering that I described earlier.
Because of the time limit, I'm sorry, I cannot take more questions. So let's thanks the speaker again. Thank you.
Thank you.
Okay, so our next speaker is Junho Seo from Postech. So let me briefly introduce him. So he got a bachelor's degree in physics at Seoul National University and went to Caltech and get a PhD there at 2011, and also did some postdoc period for 3 years there in the same institute. And he came back to Korea to Korea Research Institute of Standard and Science, KRIS, which is in Daejeon. And he stayed as for 9 years, led team of hybrid quantum system, and this year he moved back. He moved to Pohang as a faculty member. Okay, so Professor Seo, let's welcome the speaker.
Thank you. Thanks for the very kind and warm introduction for me, Kilo. Yes, so I'm Junho, and I'm currently associate professor of physics at Postech here. And before I start my talk, I'd like to really thank the invited speakers and plenary speakers for coming here and giving a wonderful talk as one of the organizers. And it's been a great experience to, giving a little contribution to this wonderful event for me. And it's even better for me to having a chance having a chance to share my own research in front of you. Okay, so my device and my research is about cavity optomechanical devices, and I think Professor Cleland already has talked about this motivations and wonderful outcomes from these mechanical quantum devices, especially the surface acoustic wave devices. In his talk, if you remember, there's one big important motivation about studying mechanical oscillators in the quantum regime to use those devices of very precise and sensitive sensors in the quantum regime. And as I'll explain later, these mechanical devices especially suited for those quantum sensing applications. So, okay. So what are the cavity optomechanical systems? So if you have a mechanical mode, you can imagine a little bit of a compliant membrane or a cantilever, if you like. And then if you shine a laser light onto that device, the photon will carry momentum. So whenever that photon bounces off from a little mirror attached to this mechanical structure, it'll give the radiation pressure. So this is kind of a fundamental interaction between photons to the mechanical oscillator, and also, of course, the fundamental, quantum in the mechanical oscillator, which is phonon. So that determines the radiation pressure mediated interaction between the photons and phonons. And in some cases, you can actually use a microwave instead of a laser light. And if you want to use a microwave for cavity optomechanical system, you'd like to use something looking like an LC circuit instead of a ferrith-pair resonator like you would have with a laser-based cavity optomechanical system. In either case, what you arrive at is the radiation pressure interaction is, in detail, is somewhat different, but you can just assume that there's a certain amount of interaction between the photons and the phonons in the mechanical oscillator in this case. And so you can just succinctly describe the system with this type of Hamiltonian where you have photons, of course, and then phonons in the mechanical oscillator, and interaction between those two, again, via the radiation pressure, okay? Well, this simple-looking Hamiltonian, you have two oscillators coupled together some way. And in many cases, actually, this interaction Hamiltonian can be expanded to some linearized form, too. So, you know, in physics side, I think it's quite simple. But for me, what's exciting is that the simple Hamiltonian can be implemented in a variety of different forms in the physical systems. Like, you know, very small case, you can even see the experiments with the cold atom clouds where these trapped atoms are looking like, you know, mechanical oscillator interacting with cavity photons, constituting a nice cavity optical system. In the other side, you can even see that the kilogram size mirror suspended, you know, moving back and forth is interacting with a strong laser light inside the cavity, in the LIGO case, for instance. So you can see, you know, very different looking examples which are implementing the same Hamiltonian, seeing different aspects of the radiation pressure mediated interaction between photons and phonons. And there are a few examples that can show the quantum properties inside of this cavity optical system. I'll describe a little more detail about the quantum action evading measurement and quantum squeezing later in my own slides. And also there are you know, very great experiments of ground state cooling for the mechanical oscillator and also measuring the 0-point fluctuation of the motion of the mechanical oscillator itself. So that's that's how these cavity optical system works. So once you build a system and then, you know, operate it properly, you can get down to the regime where you can think of the mechanical oscillator as a phonon, the quantum oscillator. One of the necessary conditions, I think, is you have to achieve this type of thing. So usually these mechanical oscillators are heavy, constituted of like 10 to 15 atoms, for instance. Compared to photons, of course, it's a lot heavier. And also, usually lower in frequency compared to the lights, for instance. So in order to satisfy this condition, you have to achieve, you know, these type of criteria. For instance, if you have a gigahertz oscillator like Professor Clinton has described, you have to reach about, you know, 50 milliKW below temperature to reach the quantum ground state, to see some quantum effects, to start to see the signature of the quantum effects from the mechanical oscillator. And also, you'd like to have some way to measure this mechanical oscillator accurately enough, because the feature of a quantum in this type of a mechanical oscillator would occur when you see the device accurately enough to resolve the displacement in the dimensions of, like, 0-point fluctuation itself. This is kind of necessary condition you have to achieve to see the mechanical quantum oscillator in your device. And of course, using the superconducting qubits with a surface acoustic wave device, Professor Clinton actually showed a very nice example. My example would be a little different, based on the photon to phonon interaction via radiation pressure that I just showed to you. Okay, so why sensing? These mechanical oscillators are actually really great classical sensors already. And you can see nice examples in scientific world. You can see, like single quanta detection, mechanical sensors detecting electron spins, charge, and some atomic mass or protein mass, for instance. So these microscale or nanoscale MEMS or NIM sensors can detect forces from single quanta or can detect mass of a single atom or molecule. Very sensitive detectors in the classical domain, completely classical. Some of them are actually so useful. So there are industrial applications of these mechanical oscillators that we're using for detecting something. These devices are usually better suited for measuring forces, of course. The mechanical oscillators, responding to the external forces. And one of the examples is a hemispherical resonator gyroscope, HRG. Which are commercially available, which measure the Coriolis force from the rotation of this device. So it's a very, very accurate angular momentum sensor. And also there are, these are kind of everywhere these days. These MEMS accelerometer can measure the inertial force from acceleration. So these small scale mechanical sensors are great classical sensors. And once you have a high enough frequency and a low enough temperature, you have to consider the quantum nature of these mechanical oscillators. And of course, because everybody knows that once you get down to the quantum ground state, the noise is still there. There's always 0-point fluctuation. So you could imagine that there's going to be some ultimate sensitivity limit given by the quantum mechanics itself, which is defined as a 0-point fluctuation for these devices. And the rest of my talk is how to detect that kind of a 0-point fluctuation effect, and also how to manipulate it. Okay, so that's the motivation of looking into the mechanical oscillators as quantum sensors. And these motivations are shared by many people in our community. And I think Chris again listed up nice examples of quantum sensors based upon very different physical systems, and optomechanics is one of them, of course. And as I told you, that these sensors are well suited for detecting forces. And I think for detecting accelerations and some of the force-related quantities, I think the mechanical oscillators are kind of the at least one of the best candidates for quantum sensors. Okay. So cavity optical system, which are simple but can be implemented in a very different way. Can get down to the quantum limit, detection limit, and can be used as a quantum sensor for measuring forces very sensitive, with a very high sensitivity. And I'll give you some more detailed examples from now on. All right, so what happens in the cavity optical system once you have this photon-phonon coupling via radiation pressure? So this is the so-called cavity, the resonant mode for the photon. Okay, there's this curve. And let's imagine there's a light or a microwave which is resonating with this resonator, okay? And then, because there's the coupling, which actually tells you that whenever there's a movement from the mechanical oscillator, the resonant frequency of this cavity would change. Like you should imagine that this curve is moving back and forth. This is a frequency axis, by the way. And what you get is either of these two effects. One is there's a photon coming in and loses some amount of energy, which corresponds to the energy of one phonon, and emits one phonon. That corresponds to the kind of a heating effect with respect to the mechanical oscillator. Mechanical oscillator is getting phonons from this interaction, okay? And the other process would be one photon coming in, absorbing the energy from the mechanical oscillator, absorbing one phonon from the mechanical oscillator, and gets higher in frequency. So there are two frequency conversion processes. This is, you can think of it as a simple, in a classical picture too. But these two processes actually can happen in a very, in a quantum mechanical way. These look like Raman-like. So once these two processes happen, you will see two side bands because of the frequency conversion of the incoming photons. One would be Stokes sideband, lower in frequency. While the other is anti-Stokes sideband, higher in frequency. These are looking like some sort of a Raman processes, so that's why we call these as a Stokes and anti-Stokes. And these sidebands are proportional to the phonon occupation. If there's a more motion, you'll have more sidebands. So just looking at these sidebands carefully enough, you can make it as a quantum limit detection for the mechanical motion of a oscillation of a mechanical oscillator. So, and the point is, all these processes can be done very close to the ideal limit for many of these optomechanical systems. So I'll show you one of those examples. Once you have all that, you have to think about what really limits of our detection sensitivity. So what we're doing is we devise a cavity optical system which has this photon-phonon interaction. We shine the light into the system and measure the light coming out of it. Okay, and what you want to do is measuring those sidebands to figure out how much movement this mechanical oscillator has. Okay. So that's the job. So you can imagine that whenever we have a higher number of photons, we're going to have more photons coming out of the system. So I'll have a better signal-to-noise ratio. I have more signal, right? So that's what this means. So the imprecision for the uncertainty of a mechanical motion that I measure from the system, which comes from the photon shot noise. The photon has a random shot noise, of course, so that gives me this amount of uncertainty about the mechanical oscillator motion. On the other hand, whenever there's a interaction of the photon to the mechanical oscillator, because this is the radiation pressure effect. So the random arrival of the photon on the mechanical oscillator, which gives me the information of the mechanical oscillator movement, which also generates a random force onto the mechanical oscillator. So that's what's called back action. So there's a random back action force because of my detecting photons onto the mechanical oscillator. So those two actually compete each other, and there's some kind of a optimal point. So let me say that's optimal number of photons for this detection scheme. And then if you just run the simple, basic quantum mechanics onto this coupled system, what you arrive at is actually the total measurement noise gets minimized at this optimal number of photons. And the total measurement noise, which is the uncertainty of mechanical oscillator motion from this type of a measurement, exactly equals the 0-point fluctuation of the mechanical oscillator itself. Okay. This type of a thing, it looks like rather theoretical, and until recently, it hasn't been possible to really measure this type of effect in the laboratory. But even in 70s, Kipthorne and other guys actually published this paper describing that back in the 70s, the gravitational wave detection community was thinking about this resonant type of a detector, which is like 1 ton scale aluminum bar, freely suspended, which can resonate with the gravitational wave from the outside universe, can generate the little mechanical vibration due to the gravitational wave coming into the massive detector. So that's kind of a resonant gravitational wave detector. And once they considered this type of a thought experiment, they concluded that for detectors of reasonable mass, the signal is below the quantum limit. So so I think these guys actually were smart enough to think about the really fundamental limit of gravitational wave detection within their kind of the possible ways of realizing the mechanical oscillator detection. And they arrived at this conclusion, which is kind of dismal, but they were smart enough to get around that, get around this fundamental limit, which is actually not looking at the usual position of a mechanical oscillator. If you decompose into the mechanical oscillator into two components, which are I'm going to call quadratures of motion, which is simply cosine, the components of oscillation in terms of cosine and sine part, just like the IQ components of a microwave. Okay, if you decompose this displacement, the oscillation of a mechanical oscillator into these two components, what you realize is that these are actually the constants of motion of harmonic oscillator. You can actually prove that, and that means that they can be measured with no back action. So this is different from positional momentum, which are not commuting variable with the harmonic oscillator Hamiltonian itself. So whenever you measure positional momentum, the Heisenberg principle tells you that there's going to be some amount of back action into the system, so you cannot measure below the quantum limit that I just showed you, which equals to the 0-point fluctuation at the optimal number of photons. But the back action can be avoided, sort of evaded, if you just look at these quadratures instead of position and momentum. In that case, the back action goes actually into the unseen quadrature. If you measure the x1 quadrature, say cosine quadrature, the back action of that measurement would go into the sine quadrature, the other quadrature. So the back action of the current measurement at t equals 0 won't affect the measurement at the later time, which is quite different from positional momentum, which will give you the standard quantum limit for the mechanical oscillator detection. So that was a theoretical kind of a proposal, initiated by this theoretical estimate of gravitational wave detection, but hasn't been realized in the laboratory since then for some amount of time, for decades. And I think we're one of the first that actually demonstrated that these ideas can be implemented in a device scale, and actually these type of physics actually works. So that's the story that I'm going to tell you in a few slides later. So in order to devise this type of a particular type of a measurement, if you want to make your detector sensitive to only one of these two quadratures, not both, and then what you want to do, these are what's suggested in these theoretical papers in the 70s, that what you want to do is actually modulate the laser light or microwave into the cavity, which actually coincides with mechanical resonant frequency itself. So in frequency domain, it looks like this. So instead of having one single light or one frequency, single frequency microwave that I just showed you, you have two. Okay, simple. Two instead one, and then you can do this. So now you see that my cavity field, the electric field inside the cavity now has the time dependence which coincides with the mechanical resonance itself. So the detector has some dependence with respect to the phase of a mechanical motion. Okay, and I think that's why the Hamiltonian, you can calculate this interaction Hamiltonian yourself. At the end, in the long time limit, if you integrate all these terms, you see that the effective interaction Hamiltonian between photons and phonons in this case actually is only proportional to one quadrature. In this case, x1. I chose cosine instead of sine. Of course, you can choose sine for this envelope, and you will have a detector which is sensitive to x2. Okay, so that's the idea. Oops, that's a bummer. Okay. So this back-action evading measurement idea was implemented with a microwave cavity optomechanical system. And in this case, we have about 5 gigahertz photons and 4 megahertz phonons. The interaction is small, but we can still amplify this effect by applying many photons inside a cavity. I think we applied about 10^4 to 10^6 number of photons in our real experiment. The phonon has a 0-point fluctuation of 2 femtometers, so measuring these type of effects means that mechanical oscillator can be resolved down into that tiny amount of motion. Okay. So we could demonstrate experimentally, that indeed the back action goes onto the one quadrature. So if we measure one quadrature, x1 quadrature, the x1 quadrature does not feel the back action, but the other quadrature actually feels the back action from the measurement of x1 quadrature. And also we quantify how much back action is happening in the system. We confirm that the back action of the measurement in our real experiment, the back action is actually 8.5 dB smaller than what's expected from the quantum back action. So that was the point. Okay, so a little tweak from this sort of a two-tone measurement. You can actually squeeze the mechanical motion. Squeezing, by squeezing, I mean that we could reduce the amount of quantum noise on one quadrature from these either x1 or x2 quadrature below 0-point fluctuations. And the scheme is quite simple, actually. Smart theorist we worked with actually gave us this beautiful idea. Instead of having two equal power, why don't you have just one big power on the red side? And then that actually gives this a nice squeezing effect. Theoretically, this is very interesting. If you're interested, I would recommend to look into this paper. This is about so if you do this experiment, if you make these system, and then the mechanical oscillator sees kind of a squeezed path. So that's the point. Anyway, so experimentally, what we saw is actually squeezing more than 3 dB below 0-point fluctuation was possible. Well, from then on, I have about 3 minutes. I think I have enough time to describe the recent work. So all the work that I just showed you about the quantum limits of the mechanical motion and how to evade the quantum fluctuations in this type of cavity optomechanical system was done on aluminum devices. And if you want to do real quantum sensing with these devices, we're going to have to solve another hurdle, which is about the material property of the aluminum itself. Okay, so aluminum is a good spot conductor, which has a quite low loss for the microwave photons that really suits for the cavity microwave optomechanics. But unfortunately, it has a relatively low critical temperature and relatively low critical magnetic field. So for sort of a wider application range for quantum sensing with these devices, that limits quite a few, that generates quite a few problems. Especially, we thought that if you want to use this detector for detecting a force from a single spin, the spin experiment usually requires a magnetic field. So the aluminum device won't work on the magnetic field. That is a problem. So that's why we look into other material systems, which we chose as niobium. And this Dr. Jinung Cha at CRISP currently actually made this device work. I'll just skip the devices, but I'll just show you this data. So different from aluminum, previous aluminum devices, These niobium devices can do the optomechanical experiments on the magnetic field up to about 0.8 Tesla. We confirmed that the small g, the coupling coupling rate between the photon to phonon, given by the geometry of the device, is actually conserved even under the magnetic field. So that means there's a possibility of using these devices for some spin-related effect. And also, these niobium devices can sustain more magnetic microwave field, which means that because niobium can withstand higher magnetic field, so that means when there's RF current, there's RF magnetic field. These devices will have, we can withstand more RF current, which means more RF photons inside the system. So that gave us a little opportunity to explore some nonlinear physics with that. And then the most important data is that we could see that once we're in above some critical number of microwave photons, we saw some frequency comb effect, which was, at the end, we fear that this is related to the nature of the Hamiltonian interaction term and the equation of motion, which is basically the radiation pressure. So this is kind of the outcome of the radiation pressure mediated effect. Okay. And the last part is, instead of using all superconductors, in one way, we thought it would be interesting to add some dissipation in a controllable way and figure out how to use it. And actually, this is quite an interesting experiment for me. Dr. Jiwon Kim, currently at ADD, actually did this experiment. He inserted resistive semiconductor nanowire inside of a coplanar waveguide resonator. So in this case, it's not all superconducting. It has a dissipator in this case. And we placed the dissipator, which is quite close to the voltage antinode, so that the microwave field could dissipate mostly inside of the small volume of the nanowire. So what we saw is when we pumped the system with the microwave photons, the mechanical resonant frequency, which was observed by the sidebands of the cavity optical system, in this case, actually shows interesting behavior with respect to the power and the frequency of the microwave excitation, which is actually, we figure that this is because the microwave power dissipated in the system raises up the nanowire. So the temperature of the nanowire actually changes. That gave us this type of interesting behavior. All right, so that ended up we call it nanomechanical microwave bolometry. We concluded that our noise equivalent power is not, not that the best in the world. It's only about picowatts level, but the good news is that you can actually detect nanowatts power instead of femtowatts power that can be detected with world best Johnson bolometer. So it could be a little, nice complementary way of measuring microwave power from the quantum devices at low temperature. Okay, so for the future work, we think it'll be interesting to think about using these mechanical oscillators as entangled force sensors. There are a few reports from NIST and also Aalto University in Finland where you could actually entangle these membrane devices, membrane mechanical oscillators within one cavity optomechanical system. It would be interesting to think it as kind of a test bed for force sensing with the entangled mechanical oscillators. And also, Professor Clinton already pointed out that these mechanical devices can be used for measuring the hybrid systems, quantum hybrid systems, with quantum transducers and more applications. And we are also interested in using these mechanical quantum sensors for new physics. So I started the lab in Postech since last March. I was very lucky to have these students already. So next time when we meet, and then I hope that I can update you with more interesting new data. Thank you very much.
Thank you very much for interesting talk. So questions or comments? Yes.
Thank you very much for very nice talk. I have questions on this niobium mechanical oscillator.
Yes.
Under the magnetic field, there might be the vortex kind of thread into this mechanical oscillator that hamper your Q values of the oscillator. Have you seen those kind of things?
The quality factor of the microwave resonator is affected quite a bit by the magnetic field. Our point of that device, that work, was that even though the quality factor for the microwave resonator degrades, the mechanical oscillator still survives, and its quality factor is not affected that much. Although there's an interesting point, because we definitely saw some interesting effects of a mechanical oscillator. The frequency of a mechanical oscillator can shift quite a bit during the experiments. I didn't show that data in the slides, but we think that is related to the vortex motion, maybe. So maybe this is something that can be used for studying that type of things too. Thanks for your comment.
Okay. Mic is just
fair, because it's a question about a quote that you gave in your talk.
Okay.
So basically the quote from Brzezinski, it seemed to imply that it's impossible to do gravity wave detection without some kind of quantum techniques. But I was wondering, was that quote in relation to a Weber bar detector?
Indeed, yes.
Yeah, so instead of, so LIGO got around this problem.
No, the broadband detector is outside of this, outside of this scope.
Yeah,
This is all about resonant detector.
Okay.
Back in the old days, people thought that's the best way, but the technology advances, and
Okay,
we know better
thank you.
than that. Yeah, thank you.
okay. Okay, so if there's no more question, let's thank the speaker again.
Thank you very much.
And so we're gonna have some coffee break until 3 o'clock. Okay, see you soon. And by the way, for the speakers who need some assistance for booking trains or buses or flight back to Seoul, please let us know. Thank you.
Okay, so I guess we can slowly start as people walk in. Good afternoon, everyone. I hope that you're enjoying the wonderful talks and the discussions that follow afterwards here at the Postech Signature Conference. My name is Ji-woo Park, and I'll be the chair for this session. So this session has 4 speakers who will cover the broad aspects of quantum science and technologies that are based on cold atoms. We'll have 2 talks in the first half, and then we'll take a short coffee break and then return for 2 more talks. As in the other sessions, the plenary talks are 50 minutes long, and the invited talks are 30 minutes long. Okay, so as we wait for more people to come in, please allow me to introduce our first speaker, Professor Emanuel Bloch. Professor Bloch is a professor at the Ludwig Maximilians University in Munich, and he is also the scientific director at the Max Planck Institute for Quantum Optics in Garching. He completed his PhD at LMU in the group of Professor Theodor Hensch, and after starting his professorship at the University of Mainz in 2003, he returned to Munich as a faculty member in 2009 and has stayed there since. As many of you already know, Professor Bloch is a pioneer in the study of quantum many-body physics with ultra-cold atoms and molecules, especially in optical lattices. And for many of his contributions, he has won numerous prestigious awards. I think the list is too long for me to quote. And one, including the European Science Prize. And most recently, he was named as one of the Clairviet Citation Laureate in year 2022 for his pioneering work on quantum simulation. Please welcome Professor Emanuel Bloch.
Yeah, thank you very much for the kind introduction, and really a big thanks for the invitation. It's been really a wonderful conference so far, and I've learned a lot here, exciting talks. Learning a lot about the science here in Korea on quantum, which is really amazing, and thank you also for the great hospitality, everybody. So I'd like to use the opportunity today to talk about a few topics connected to quantum simulations. I think I'll skip the polar molecule part, but if you're interested in polar molecules, talk to me about some of the latest results. But I'd like to give you an introduction into the field, what we're doing, tell you about our system, our probing techniques, and then really dive into applications, right? Because I think that's what we're most interested in. How can we use these novel systems, quantum computers, quantum simulators, really to explore new science, and which is the most exciting part for me, at least. So we'll talk about these 2 parts here, about strongly correlated electron physics and non-equilibrium dynamics. And actually something I'd like to connect in the last part is something a little bit connected to what Hong Kong Park was talking about in the morning, about new quantum optical interfaces using sub-wavelength arrays of emitter, which I think is a very nice, actually, quantum optics topic you might not have heard about before. So as I said, one of the biggest challenges for us is really to use these quantum devices, find application actually for these quantum devices. And lo and behold, maybe in contrast to what you've been hearing so far, there aren't actually so many applications for quantum computers. That's actually one of the biggest problems, that we don't know exactly, we don't have so many quantum advantages for a lot of problems that are relevant to society. But we do know there are pretty sure quantum advantages when we deal with problems coming out of physics or chemistry, where actually quantum is really at the heart of the problem. So it's very natural to use these systems in that context, and I think it really offers not only to extend our understanding of known phases of matter to new regimes, but also really to explore quantum matter in new regimes, and as was said by Irfan Siddiqui on his talk, really maybe realize new forms of active quantum matter, completely new forms of quantum matter that we can realize in these devices. So we've heard about 2 approaches to deal with this problem. One is this quantum simulation approach, which we sometimes also call an analog quantum computing mode, where you try to directly implement in your system the model Hamiltonian that you want to study, for example, the one of strongly correlated electrons in a lattice, in a specific lattice geometry, and then you can look, for example, at the time evolution of the system and do measurements on it. That's a very powerful approach. I think it leads to brings us closest to the regime of quantum advantage, to those kind of relevant problems in physics and chemistry, but it has the disadvantage that it usually is non-universal, meaning that you can only, of course, study what you can really implement in those systems. You've heard about the other approach, of quantum computing is building up these Hamiltonians out of a discrete gate set of elementary operations, single or 2-qubit operations, which in the end, build up the entire Hamiltonian evolution, for example, here in this trotterized fashion. This is, of course, very nice because you can basically realize all kinds of Hamiltonians through this elementary gate sets. However, when I say in principle, that's of course a caveat to that because it's typically very resource hungry. So, how far you can get with this approach, at least on these devices that we have today, can be much more limiting than in the analog mode that we have here. And of course, basically, when I write digital here, it's also not quite true because that's also analog at this point because there's no error correction, right? Everything is analog in a sense of what we're doing so far on these NISQ devices. But I think it's still useful to have this distinction, but keep that in mind. So the system we're working with is ultra-cold atoms in lattices or tweezers. And here's a nice picture from Ted Hensch of such an optical lattice realized by interfering 5 laser beams. So this is a real picture of this quasi-crystal in this case that you see emerging through the interference of the laser beams. And you see this is a perfect crystal structure without any defects in it. And if we make the atoms cold enough, we can trap them in these light fields in vacuum chambers. And if we can then, in addition, have spins, for example, hyperfine states or electronic states, which can be very long-lived, like a clock transition, for example, in strontium, then we can add spin degrees of freedom to the problem, and we can either freeze out the particles in these lattices to trap them, or we can also let them move around in these lattices, tunnel from lattice side to lattice side, and then realize not only static systems, but also itinerant systems. So typically, you'll see in this talk system sizes of up to a few thousand particles. The interesting thing, I think, to note here is that we can work with either fermions, bosons, or mixtures of both. And at least for fermions, that's a big advantage because if you want to study strongly correlated electron phenomena on a quantum computer, then mapping this problem onto the quantum computer carries an overhead, and we can save this overhead, of course, if we directly work with fermions in the first place. So this whole field kind of started, or at least for me it started when I read this pioneering paper from Ignacio Cirac and Peter Zoller in 1998, where they proposed for the first time to use ultra-cold atoms to do quantum simulations of lattice models of simulating the phase transition from a superfluid to a very strongly interacting, strongly correlated phase of matter of a so-called Mott insulator. This goes back to earlier work from Matthew Fisher in 1989. And for me, that really was my jump start into the field of quantum simulation. And I think it's fair to say, looking back now, it's almost 20 years since this paper was published. And recently, together with Markus Greiner in Harvard, we had a historic review back on this phase, this exciting time 20 years ago. I think it really is fair to say that it's really stimulated tremendously this entire field of quantum simulation. And we see this now happening across all kinds of platforms, ion traps, Rydberg tweezers, superconducting devices. We've heard a lot about the exciting results there. Hong Kong Park even told us about using these TMD devices for quantum simulation. So it's really become, I think, actually, I would say the major application field for these quantum devices that we have today. So for the lattices, coming back to the lattices, let me tell you a little bit about the parameters so you know a little bit about the system. So since we create them through interference, the spacings between lattice sites are typically fractions of the optical wavelength. So typically between 250 nanometer and 1 micron. So we can very nicely resolve these with good optical microscopes. The tunneling rates when you hop from one lattice site to the other lattice site is between 100 hertz and 5 kilohertz. And wave functions, if you're in the lowest energy band of the system, so in the lowest harmonic oscillator state on a lattice site, typically is confined to sizes of 10 to 100 nanometers in the system. Now, for some time, we thought that whenever you want to realize different lattices, like a square lattice, hexagonal lattice, triangular lattice, Kagome lattice, or Leap lattice, you would have to synthesize this by shining in the laser under new angles under different regimes. And that's, of course, very painful. Okay, as a supervisor, it's easy to say, let's switch from this lattice to that lattice, and then the students will shout, oh no, yeah, this is like not a good idea, this will cost me another half a year of my thesis. But now, actually, we found a very nice way, and this is, I think, going to be used a lot in the future, which we published just this year in PhysRef X, how you can realize all these different lattice structures using just one laser setup. I won't go in details how this is done, but you can read about it in this paper. I just say it's immediately been picked up by a lot of groups in the field. So Wasim Bakr in Princeton, for example, has used that to a great extent already, and I think we're going to see more. But this is nice because it really means, at a push of a button, you can switch between these lattice geometries. And of course, that's very important when you want to study the effects of these geometries on the behavior of the particles. Now, how do we observe these atoms? So there's the other technique. What we use is called quantum gas microscopy, which was pioneered by Marco's group in Harvard and our team in Munich. And actually, I show a very nice picture, and Jae-yoon maybe is going to show you even nicer ones from his group here in Korea. Beautiful pictures of lithium atoms observed with this quantum gas microscope, and you can really beautifully see that if you use fluorescence imaging together with a high-resolution microscope, you can really see the atoms on those lattice sites with very, very good signal-to-noise ratio. So you can tell whether there's an atom on a given lattice site or not, and that's a very, very powerful technique, as I'll show you in a second, to detect the atoms. Then we can, of course, confine them. So another toolbox we've been bringing into the game is use optical potentials, shaping these optical potentials in interesting ways, like a box or two reservoirs connected by a quantum wire, exotic lattice structures, to really enhance also on top of that how these atoms are confined. And then on top of that, we can add single-site addressing. We can focus laser beams onto individual atoms on these different sites and, for example, flip the spin of a certain atom on a certain site. Now, I should say this is harder for us than in, for example, optical tweezer or ion trap experiments, because there the separations between ions and atoms is typically on the order of 5 micrometer. For us, it's about a factor 10 lower, and that makes it just optically harder to do the same thing with high fidelity. Here are some pictures of that. So we're of Mott insulating phases, for example, that you can see here, where you have exactly one atom per lattice site filling those cases. Forget this cloud surrounding that here. These are just thermal reservoir atoms. This core here is a very nice unit-filled system on the lattice, about 2,000 atoms here, and we can reach filling factors of up to 98% regularly in these systems. And the remaining defect, why is it not 100%? That's just residual thermal entropy in the system, thermal defects that occur. So keep in mind that this arrangement of the atoms on the lattice, that's not done by hand. It really is the physics of Mott insulators, the physics of strong correlations, which turns this system into this homogeneously filled system that you can see here. All right, so one additional tool that we need for electron, when we want to study strongly correlated electron physics, is that we need to be able to actually distinguish 4 states that can occur on the lattice site. Imagine you have a spin-up electron, a spin-down electron. So you have to distinguish whether on a site there's a spin-up or a spin-down. But you also have to distinguish, if there's no atom or if a spin-up and spin-down atom are on a site. So there are actually 4 states that you want to distinguish: no atom, 2 electrons, or spin up and spin down atoms in our case that mimic the electrons. So the way how we do that is the following, actually employing some nice topological physics in this. Imagine you have this physical layer. This is the single layer here, which presents the system where you're studying the physics you want to study, for example, of these electrons on a lattice. Then what we do is a Stern-Gerlach separation, a splitting of this single layer into 2 layers, where we move the spin-up atoms into the upper layer and the spin-down atoms into the lower layer. And then using a Thouless charge pump, we actually separate those layers over large distances. So now the spin-ups and spin-downs are separated by about 20 micron. And now we can take 2 separate images, one of the spin-downs and one of the spin-ups, and then combine those images to give you a full reconstruction of the occupation of the atoms on the lattice sites. So thereby you can fully see in that shot of the experiment what the occupation was for this large system. So in terms of what we're measuring, keep in mind that we're dealing with this many-body wave function, or a many-body density matrix, but in the wave function it's simpler to explain, which is a superposition of different configurations of occupations of those particles. And when we do this fluorescence detection, we actually make a strong measurement in the occupation basis, which means that we're going to collapse this wave function onto one of those configurations. Onto which one it collapses is completely random. We don't know. It just happens by chance. I'm omitting the prefactors here, the complex prefactors with, of course, the probabilities which are given by these prefactors squared in the system. okay? So imagine you measure, for example, in one experimental run, you measure this state, and you see the occupation. Then you'd go in the experiment, repeat, recreate psi, measure again, you get another state, and you do this thousands of times in the experiment. Yeah? And after doing this thousands or tens of thousands of times, you get probability distributions of configurations, of these configurations. And from this probability distribution of configurations, you can actually calculate correlation functions, which is, of course, the physical thing we want to compare to in the theories. Now, the nice thing is when you have access to this single snapshot is that you're not confined to two-point correlators. Yeah, like in standard condensed matter experiments. You can ask questions like, look at 3, 4, 5-point correlators, and I'll give you examples of that, and I'll also try to convince you that for a lot of the physics we're looking at, these are not minor, corrections, these are actually containing the major physical problem what we're trying to solve in these systems. So looking at these higher order correlations is really a unique asset that we have with these quantum simulators. All right, having introduced the system, let me jump into a few examples. And the most famous one is, of course, the Fermi-Hubbard model, which describes the hopping of fermions on this lattice. It has this hopping term. It has an interaction term, which we call an on-site interaction term. When two particles come together, they interact, have an interaction energy U, which could be positive or negative. Typically, in our case, it will be repulsive. So U is positive. It costs you energy to put two particles on the same side. We also know that in this model, at half filling, for strong and repulsive interaction, the system forms a Mott insulating state with one atom per side. But if you go to low enough temperatures, lower than the super exchange energy scale, then actually this system will order antiferromagnetically. It's a Heisenberg antiferromagnet and show antiferromagnetic ordering at these low enough temperatures when KBT becomes smaller than this exchange coupling scale J that you can see here. And now to connect to the phase diagram of the cuprates, what is interesting now is that at zero doping, we know this is a nice antiferromagnet. And then when we increase the doping in the system, we get all these zoo of phases that people are trying to make sense of, the pseudo gap, the strange metal, and potentially a D-wave superconducting phase here. And if you ask what is the essential physics you're trying to understand in this problem, if you try to boil it down to a single question, the question really is, how do whole motion compete with magnetic ordering in the system? So how do the holes that move there compete with the fact that you want to have the system order antiferromagnetically compete? And I'll show you examples of that in a second. And here's, of course, nice one where we can bring in this new approach of quantum simulation to throw a new light onto this aspect and study the system under new conditions. All right, so let me show you first that we really make nice antiferromagnets in the system. So here I'm showing you how we prepare the system. So we have a very nicely shaped light potential that you can see here. So this is the physical region here. This flat region, that's the physics. That's the region where we do physics. And by tuning the offset, the potential of this offset, this is like tuning the chemical potential. So by just tuning there the depth of this light potential, I can tune the chemical potential in my system. It's like applying a voltage, to your real material. And then it's surrounded by a reservoir which acts as a cooling reservoir of the central physical region. And for example, if we do things right, if we load with the right chemical potential, you can see that we get a nice Mott insulating state in the core with an average density fixed exactly to 1. You actually see nicely, if you go to the outer ring, the reservoir, that's a metallic regime, so it has lower density. And if you look at the fluctuations, the particle number fluctuations, you really beautifully see how in the Mott insulating state, the particle number fluctuations are suppressed, but only at the rim of the system, where there's a metallic ring surrounding this Mott insulator, you see that particle number fluctuation are actually enhanced on a scale of a single lattice side. So this is really at which you can resolve this here. Okay, but then let's go and measure the spin. I told you we can measure spin, so we can also measure for the, let's say here, undoped system spin-spin correlations. And if we do that, you see we find very nice antiferromagnetic ordering over the entire system here. And if we plot the antiferromagnetic order, the SZ-SZ correlator as a function of distance, these are our data points. And now we can ask colleagues like Lode Paulet in Munich, who is one of the world-leading expert in quantum Monte Carlo simulations, to do the corresponding simulation, which is the dashed line here. And from that, we can very precisely extract the temperature of the system. We know it's in thermal equilibrium, and we can extract the temperature. So in this case, the temperature in units of the hopping is about 0.25, and for the experts, we're working in a regime interaction strength over tunneling 6.5, which puts basically the tunneling and super exchange coupling on the same energy scale. So they're not so different actually for this parameter regime. All right, so now the first testing you can ask, how do holes, as I said, holes move in this antiferromagnetic background? And this is actually a question that has been asked by, through the last, 30, 40 years in condensed matter physics by some of the greatest minds, starting with Steve Trugman in the 88s, Bob Schrieffer, Xiaogang Wen, Shuzheng Zhang, Charlie Kane, Patrick Lee, Nick Reed, many, many more that have devoted a lot of their work to this question. And what happens, of course, when we in this cartoon picture, if we would move a hole around in this antiferromagnet, which I just draw as a classical antiferromagnet, then you see if this hole moves here, then this green atom moves here. And if the hole keeps on moving further, then this red atom moves there. And what you see is left behind with the hole moving is a string of flipped spins, but these are ferromagnetically aligned. You see, every time the hole moves, it leaves behind ferromagnetic spins, but that's not good. Remember, from a magnetic point of view, the system would like to favor antiferromagnetic correlation. So this clearly is going to cost energy. The further this particle moves, the more spinons it leaves behind, the more energy it has to pay, and this leads basically to a linear confining potential between the separation of the spinon and the hole in the system. And this linear confining potential is pretty much like what you get in partons in nuclear physics, where you also have confinement, where these spins are bound to the hole in the system. And this analogy has been recently used again very much by Fabian Grust and Eugene Demler, but was already discovered in much earlier work by Mike Gunn and Benjamin Simons in the 90s, making this analogy that really the particles that are formed then can be seen as mesons, for example, in nuclear physics. And the particle that forms also is what we call a polaron. Hong Kong showed you this morning the polaron in real space. This is a spin-back polaron, so there's a spin distortion around that impurity that forms, and whenever this hole moves, it has to carry this spin distortion around together with it. And now for the first time, we can really measure this polaron in real space. So here's a picture of this polaron. Let me walk you through this. It looks complicated. So this is actually a 3-point correlation function that we're measuring, so something that's not accessible already in condensed matter experiments. So what we're asking is, how are two spins correlated, for example, this spin here correlated with this spin, conditioned on having a dopant, here it's a doublon, or you can think of a hole, at the center position. So when you have a hole in the center, how are the spins correlated around that hole? So this is a 3-point correlator, because you need to correlate spins around knowing where the position of the hole is. And you can see, actually, this is what I'm plotting here is the so-called connected correlator. So it tells you the difference to the background correlations of the undoped signal. So all the structure that you see here, all the colors, is basically the polaron, the spin distortion, directly surrounding that mobile impurity. And you can already see traces of this spinon attached to the holon here. If you look at the spins, when the hole has come from the left, for example, and leaves this spinons behind it, those spins should be more ferromagnetically correlated relative to the background. But that's precisely what we see. If you look at these vertical spins here, they have positive signatures, so they're more ferromagnetically correlated corresponding to the background, compared to the background. Same thing from the top, from the right, from the bottom. You can see very nicely the structure of the polaron emerging from this spinon picture attached to the holon in the system. Now, what's interesting, of course, what you want to know is when you dope the system more, increase the doping, you see actually how this polaron completely dissolves. Actually, we can look at many of these microscopic quantities, and I don't have time to go in detail, but if you were interested, we can talk about it. We can see basically how you're transitioning from a strange metal polaronic of where the charge carriers are the polarons, to a Fermi liquid when you have strong doping. And now with this quantum simulation approach, you can fully resolve the microscopic quantities across this crossover, precisely telling you that around 20% doping, most of the change from the strange metal phase to the standard metal actually occurs in the system. So let me just turn this up a bit more and ask, can we have more direct evidence of this string picture, of these spinons attached to holes in the system? And for that, let me just give you a brief reminder of correlation functions. When we measure generally correlation functions, we like to actually say how much of the higher order correlation functions that we could measure can be expressed in terms of lower order correlations. So imagine you have a 3-point correlator, x1, x2, x3 of 3 observables, and now you want to measure how much genuine 3-point correlations are in this correlation function. Then you have to subtract all the lower order correlations, the 2-point and 1-point correlation functions. And if that thing is non-zero, this connected correlator tells you you have genuine higher order correlations, 3-point correlations in the system. Okay? Now typically, when we look at phases of matter, this is what we would do in a mean field product ansatz. Gaussian states, you would only have 2-point correlations that become relevant. Or then if you go to higher order correlators, connected correlators, we typically find a hierarchy that higher order connected correlators are less important than lower order ones, meaning that typical phases of matter, these low order correlations capture the main behavior of the system, and the higher order are just corrections basically to the behavior of the system. So I want to show you that this is not the case here. I want to show you that an example here where actually the 5th order correlations become dominant over all other lower order correlations in this picture of the polaron that we see here. And this actually in this cartoon picture easy to understand. Imagine we measure a system, a hole here, and we know the hole could have come from the right, from the left, from the top, or from the bottom. We don't know where the hole came from. It had 4 possibilities to move to its position. So it has 4 possibilities to leave these flipped strings behind it, right? And since we don't know which of those configurations sorry, we went through, then we have in general a superposition state of all of those 4. Now look at this lower order 3-point correlator. If I just ask now how is this whole correlator here correlated with the 2 spins on the diagonal for these 4 configurations, then you find in the first case you get -1, second case +1, third case -1, fourth case +1. If you add all the probabilities, it turns out to be 0. So it gives you actually a very small 3rd order correlation function, low order correlation function. Now look at this correlator, the 5-point correlator, which is the diamond correlating the spins in this diamond fashion around this hole. There you see all of them have the same sign, and they would add up to -1, showing you that, at least in this cartoon picture, you would have a situation where low order correlations become vanishingly small, and 5th order correlations become the dominant quantity in your system. Actually, for the experts of you in quantum simulations, this is actually very reminiscent to quantum field theories, to actually conservation laws in, for example, lattice gauge theories, where, for example, divergence of E = 0 would be implemented in exactly such a similar fashion. So we can do that. We can calculate the connected correlator for our 5-point correlation function in our experimental system, and we can look at the disconnected one, the ones that can be described through lower order correlations. And you can indeed see here that for reasonable dopings, these connected correlations become about 3 times larger than what we have for the disconnected correlators. So we are really in a situation where these higher order correlations are dominant correlations, and from a theory point of view, this of course means if you're a theorist, your theory should be able to describe that, should be able to handle this 5th order correlation functions and predict that correctly, and cannot be a simple mean field or Gaussian ansatz which would not give rise to these higher order correlations. Let me just quickly say that, if we're looking where we are right now in this regime, so we've reached temperatures here of 0.25 in terms of the hopping. This is just the onset of the pseudo-gap regime. And I think what I want to conjecture, and we will see in the next year or so if that's really true, pseudo-gap has been such a big mystery in high TC materials. What is this pseudo-gap phase actually? And let me speculate a bit. Maybe a lot of this mystery has come from the fact that we only had 2-point correlations to probe this phase. And maybe in order to understand this phase truly from its microscopic origin, we need higher order correlations to understand it. And this would be, of course, a fantastic thing if we could explain the pseudo-gap phase better using these higher order correlations. All right, one final thing I want to explain for the electronic systems is I want to give you an example how we can actually predict new binding mechanisms. So of course, when you talk about high TC, you want to boost the critical temperature, you want to boost the pairing energy to have as high as possible binding or highest possible critical temperatures. And in order first to understand, we need to understand how we could boost that, we need to understand where this binding comes from in the first place, of for example, holes binding into Cooper pairs in such materials. And it's a bit puzzling because initially in the Hubbard model, all the interactions are repulsive. Everything in the Hubbard model is repulsive. There's no attractive interaction in the Hubbard model, at least for our U. Okay, so how come holes bind together? And the reason is because of the magnetic correlations in the system. And this is easiest to see in this case where you have, for example, two holes next to each other here on such a ladder where you have strong antiferromagnetic coupling along the rungs here. And imagine now one of the particles would move, then you see it would destroy those singlet bonds, and that would cost us a lot of magnetic energy. So that's not good. But if the other hole follows in pursuit, then it can undo the damage the first hole did. And by undoing the damage, it can lower the energy again, and this leads to a binding of those holes here together. Now we're missing one thing, one essential thing. Actually, it's not like that. One thing we're missing is that this is right from a magnetic energy point of view, but from a kinetic energy point of view, it's actually not good to have holes next to each other, because then one hole cannot delocalize onto the other side. It cannot minimize its kinetic energy. Remember, for kinetic energy, we want to delocalize particles to minimize the energy. And this, in fact, gives rise to the situation that on ladders you have bound hole pairs, but the binding energy is very, very small. So the critical temperature would be extremely small for superconductivity in these systems. So how can you boost that? Well, let's just get rid of this kinetic energy cost. Let's just stay with the magnetic energy favor that we have. And one way to do that is to go to mixed dimensions, is to go to a situation where you just allow the holes to only move in 1D, but the spins to interact entirely in 2D. Then you remove this kinetic energy cost, and suddenly you can see that, for example, in the experimental correlation signal, where we look at the hole-hole correlations as a function of the distance of the two holes on the ladder, for the standard situation, the holes are anti-correlated on the same rung. As I told you, they're very weakly bound. But when we go to the mixed dimensions, we actually see this positive signal showing us now we have very tightly bound hole pairs, and with the binding energy that is actually a factor of 15 times larger than the original binding energy that we had before. So more than an order of magnitude boost in the binding energy of the pairs. Now, you might say, well, is a very exotic situation. Is that really relevant for any material that we look at today? Actually, there's been exciting developments. I don't know how much you followed this. So I'm not talking about LK99, a new superconductor. This is the nickelate superconductor, which has been found to have superconductivity at 18 Kelvin. And apparently it made a big splash. It was just published, as you can see here. I didn't even know this existed in Nature, accelerated article preview. But anyway, but then there were also these colleagues from China which read our paper on the boosted pairing energies in these mixed dimensions. And then they looked at the band structure of these nickelates, and they find precisely a similar situation that I showed to you before, mixed dimensional situation, where you can have in-plane hopping of the holes only, but not hopping of the holes across the planes. So the holes, in exactly the same fashion I explained to you before, will bind into tightly bound Cooper pairs and lead to high Tc temperatures that I showed you before. I think it's a very nice example because it's maybe one of the first examples where cold atoms were the first to predict something, and now we see this finds applications in real materials. For the end of this part, let me just briefly mention the beautiful work on Fermi-Hubbard systems from my colleagues in Harvard and MIT. There's really great work from Martin Svirlein's group in MIT on looking at very similar physics on the attractive side of the Hubbard model. And in Marco's group, they've been using also similar lattice techniques that I showed you before to have tunable frustrations, to tune from square lattices to triangular lattices and observe the effects of this frustration. And that's, of course, very nice for the future research, as I explained to you. All right, let me jump topics. I'm not going to talk. Let me talk about the quantum optics one. I don't want to spend this time here. Let me talk about this part, I think. All right, let me talk about the sub-wavelength array. So connect to something a little bit, maybe at least in spirit, to what Hong Kong was telling you in the morning. And go back to the, I'm from a quantum optics institute, so this is what we study all the time. So we want to have strong interaction between light and single quantum emitters, in our case atoms. And if you look at the probability of interaction between your quantum emitter, in our case the atom, is basically a scattering cross-section given by the wavelength squared, and then the ratio of how tightly we can focus a laser beam, this gives us the ratio, or the probability of interaction in these systems. And typically this is small. This is not large. So we don't have very strong coupling regime in these situations. So there are two ways how you can enhance this interaction probability. One is to work with atomic ensembles. You just put n atoms in there, enhance the probability of interactions. Or you work with cavities where you just let the light bounce back and forth many, many times. So then you enhance this interaction probability by the number of round trips of the light that the light makes in the cavity. And this is basically what we call the cooperativity of this cavity, right? So there's been another field in classical optics which has been finding a lot of applications is optical metasurfaces. And I'll connect to that in a second, where people have been using nanostructured, nanotextured surfaces to make optical elements like lenses, gratings in very compact fashions by using sub-wavelength kind of structures and arranging them in particular ways to reach these desired effects to shape the phase fronts of classical optical fields. So what I want to talk about now is the field of sub-wavelength arrays of these quantum emitters. So I want to consider a situation where you place quantum emitters, in our case the atoms, on a grid array, and the spacing of the atoms on this array is smaller than the wavelength of light. Okay, that's what we call a sub-wavelength array. Okay, and if we go back to our two-level atom and ask what happens when you couple such a two-level atom to the electromagnetic vacuum, you remember from your quantum cavity QED course that it gives us two things. It makes the atom decay, so the excited state will become unstable. It can decay to the ground state with the rate gamma, and the energy separation between G and E will be changed. This is what we call the lamp shift. Okay, it's a dispersive effect and a dissipative effect that we have because of the coupling to the electromagnetic vacuum. Now let's do the same thing with the sub-wavelength array and couple that to the electromagnetic vacuum. And what I'm going to show you that this sub-wavelength array is going to act like a new object, like a new cooperative object with new collective quantities. Collective quantities in the sense of collective decay rates, which now depend on which mode we're talking to of this array, and also different lamp shifts, also depending on the mode we're talking to in the array. So, but really think of it as not just an array of atoms, but really a new object we're coupling to with new radiation properties that we can tailor, that we can shape. Okay? All right, let's start with the simplest example when we have two atoms or n atoms and we just place them just very, very close together, much smaller than the wavelength of light. Then if you have two dipoles that are radiating in phase, then you have enhanced spontaneous emission. This is what we call superradiance. And if the two dipoles would radiate out of phase, then they can have destructive interference and not radiate at all, even though they could be partially, in the excited states. Then the decay rate is zero, and this is what we call subradiance. And this is what happens when typically you put n atoms to distances much smaller than lambda. But now I'm asking, what about our extended structures, where the array itself can be huge, much larger than lambda? It's just that the spacing between our emitters is smaller than lambda. Okay, that's a different situation we're talking about here. So from a quantum optics or many-body point of view, you can view this when light is propagating in this sub-wavelength array basically as a long-range interacting XY model where the coupling strengths, these JIJs, are given by the propagator of the electromagnetic radiation field. So basically what happens, you have a photon stored here. The photon can hop from one side to the next side with a coupling strength JIJ that you can see here. And these can be long-range couplings depending now on the propagator of your electromagnetic field, the free space propagator. So that's the many-body Hamiltonian that we have, a long-range interacting XY model, which describes these photons hopping around in this array. So let's not look at the many-body problem, because this is actually really hard. a many-body XY model. Let's just look at the single excitation regime. Let's just put a single quantum of excitation in this model and ask what are the ground states. Well, the ground state, that's just going to be Bloch waves, like the ones we know from standard condensed matter physics, because the S pluses minus operator is just like a dagger A kinetic energy operator. So you will basically find that the eigenstates are just delocalized photons that are delocalized over the array with these phase factors given here by this specific wave number Q, which lives in the Brion zone of your system. So you can really think of these as standard Bloch waves that we excite where only one of those atoms is excited, but this one is in a superposition of different positions. Now, let's start with shining light now onto this array. And let's send a laser beam onto this array. And first, we're in a regime where d is large compared to lambda. And then what's going to happen is, of course, that you're going to get the 0th diffraction order, the plus minus 1 diffraction orders according to Bragg law. But now, when you go to the case where d is smaller than lambda, remember the only way to fulfill Bragg's law is actually to only have the 0 diffraction order. All the higher order diffraction orders go away. So that's the first important message. You're only talking to one mode which can either be reflected or transmitted in the system, okay? It turns out that if you do the calculation, and this is from Susanne Yellin actually in Harvard with Effie Chamon, that if you do the calculation, you find for these sub-wavelength arrays on resonance, for this cooperative resonance, you find perfect reflectivity, R equals 1, okay? You have perfect reflectivity in those cases for this cooperative response of the array. The second exciting thing is that you can actually have non-radiative states in this array where the atom cannot decay. Okay, how can that happen? Imagine here's our Brion zone of the sub-wavelength array, and here I'm sketching the maximum wave vector that's possible in free space for radiation of a frequency omega. Okay, so this is the maximum k I can have in free space. But remember, in the array, I can have wave vectors which are larger than that. So imagine I prepare a Bloch wave which lies outside of this radiation cone, for example here, then I will have an excited atom which cannot decay, okay? So even though it's there in its excited state, it will have highly suppressed radiation. For an infinite array, actually the radiation decay would go to 0. If you have a finite array, it can radiate still through the edges of the system, but that's still dramatically suppressed, like the size of the ray to the cube power or to the 6th power, depending on the Q state you're talking to. So let's say you have an array of only 100 particles, right? Only 100 particles, this can suppress the lifetime by a factor of 10 to the 6 at least. Okay, so that is really dramatic, and there's no cavities, nothing around. It's just this array of sub-wavelength emitters. And that's, of course, nice for quantum memories. We'll talk about that in the end briefly. All right, so let me show you some results on that. So here's the sub-wavelength array. In our case, our mod insulator that I showed you before. It has a spacing of 532 nanometers. Rubidium has a resonant wavelength of 780 nanometers. So this puts us in the sub-wavelength regime A over lambda 0.68. So this is a sub-wavelength array of these atoms, of these quantum emitters. The light cone looks like this, so we would have a hard time storing light here because there's only this tiny corner where these non-radiative states live, at least for the separations that we can assess so far. So now let's look at the radiation, the cooperative response, the cooperative decay rate as a function of the spacing in the array. And here I'm plotting the gamma of the cooperative response relative to the free space gamma naught of our single atoms. And so the thing that you should recover easily is if you go to 0 spacing of all the atoms, when they all lump together, then your decay rate will be just n times gamma. It's just super radiance. So you have this very strong enhancement. In the other cases, you have to really solve the equations that couple those dipoles to determine what the collective decay rate is. In our case here, for this 0.68, we actually find that the array is subradiant with a line width smaller than the natural line width by about 40%. Okay? And now we can do 2 experiments. We can just shine light onto the array, monitor the transmission, or reflect light from the array and monitor the reflectance, and do that as a function of detuning and just measure this cooperative response. Okay? So here's the ordered array looking at the transmission signal and the reflection signal. And you can see that you get actually a very nice reflection, in this case 60%, and we maybe should talk why it's not 1. We know pretty exactly why it's not 1 in this case, but you nicely see the cooperative response is actually, here's the natural line width of the rubidium atom, this dashed line, and we indeed find about 40% smaller line width as we would expect from the calculation. If you disorder the array, and this is maybe an important take-home message, for this ordered arrays, for the sub-wavelength arrays to work, you need to precisely position your emitters because it's an interference effect you're relying on to generate the strong cooperative response. If you disorder the atoms only a little bit, then this cooperative response dramatically breaks down. And we showed that here by just disordering in the z direction a little bit, and you see how this reflection peak actually breaks down completely, and you lose the cooperative properties of the array. So really needs precise positioning of your quantum emitters to generate this strong cooperative response. Here I'm just showing that, as a function of the filling fraction in the system, how the cooperative response becomes stronger and stronger. We're getting more and more subline width, and we can also measure the lamp shift of the system. You can see we can nicely also get this cooperative lamp shift, measure the dispersive properties of the array. Maybe one final thing I want to say that, one thing that's beautiful here is that you can switch the mirror now with single atoms. You have now something where you can place an emitter into this array, which controls the reflectance properties of the entire array. And the way this is done is, for example, to take this array, make it, first of all, transparent by using so-called EIT transparency. So this is the light where we probe the transition on, and then we shine in another laser here to a Rydberg transition. And this 3-level coupling results in basically making this mirror transparent, so it doesn't reflect anymore. But now you can place a single quantum emitter in the center of the array, a single Rydberg atom, right? And this Rydberg atom will interact so strongly with the neighboring atoms that it breaks the EIT condition. And breaking the EIT condition means that you restore reflectivity. And you can see here within the blockade radius, within the radius where this Rydberg atoms affects the other atoms, you restore reflectivity of the array again. And this, is thinking a little bit in the future, very nice, because it could bring us to something like a quantum spatial light modulator. You all know spatial light modulators, but now you could really think of sub-pixel arrays here, that form these mirrors that are controlled by individual atoms, which could be in superposition states even, to really bring this to the regime of a quantum metasurface. This is also a great system for quantum memories. It has much lower infidelities than what you have in ensembles, for example. You can even think about making cavities out of this. So it's really become a beautiful new research field. Let me just say, for those of you who want to connect this to cavity QED, how strong is our cooperativity actually? This is often what I get asked. Remember, cooperativity for a cavity tells us how much of the light is scattered into the desired mode of the cavity relative to light that's scattered outside of the cavity into undesired modes. That's what this C parameter tells us. For our array, we can also, the reflectivity tells us how much of the light is scattered into the array relative to everything, all the scattering inside and outside of the array, and that basically is just also the cooperativity divided by 1 plus C. So we can connect the reflectivity, the reflectance, to the cooperativity, and what we had so far was a reflectance for the amplitude field of 80%, which is a moderate cooperativity of about 4 to 5. But we're setting up a new experiment. We're going to remove the deficiencies of the present one, where I think very readily we'll be able to go to stronger cooperativities of 20 with about 95, 96% of reflectivities of this array. All right, where next? It's been exciting, journey in this field of quantum simulation. Just, I think one thing I find particularly exciting is marrying this world of optical tweezers with optical lattices. This is something that Adam Kaufman has pioneered a lot in Boulder, in Gila. And here I'm leaving you with this picture of one of our latest results in the lab. There's an array of single atoms in this lattice of about 30,000 atoms, okay? And now we're combining that with the optical tweezers to move these atoms in this lattice around, really with large-scale systems, bringing everything together that I told you before. And this is nice for the quantum optics application, for the quantum simulation applications in many body systems. I think this will open entirely new fields. All right, I should give credit to the people who did the experiments. This is the Fermion team, where the work on the whole pairing was the PhD thesis of Zara. And David actually was the key driver in the mirror experiment, in the sub-wavelength experiment. So he's actually just finished his PhD. The cesium experiment I didn't have time to talk about, so I'll just leave you with this nice picture from Munich. Thank you very much for your attention.
Thank you, Professor Block, for the amazing talk. I'll open the session for maybe one or two questions.
Emmanuel, thank you for a very nice talk. And I have two questions. You showed some kinetic-induced polaron, and then depending on the doping concentration. Usually, polaron is formed in very low temperature. So what is the temperature range about your kinetic-induced polaron? This is my first question. Second question is you show the superconducting dome, and then also show the polaron depending on the doping concentration. And also you show the strange metal phase. The strange metal phase is one of the big mysteries in superconductivity. So your polaron picture can we connect to the some strange metal phase to explain the mysteries?
Yes, so at least maybe I start with the last question. So at least I can give you the full microscopic picture, or what I mean with full microscopic picture, how the polaron is dissolved into basically just a Pauli hole with a standard Fermi liquid. So I have the full, and now we have to, it's now the theory that has to give an explanation for this, but we have basically a nice microscopic picture of new quantities that people have never looked at before that we can check on. So in terms of temperature, as I showed you, we're right now at 0.25. Maybe the lower was 0.2, T over T, so temperature in units of the hopping. So that's the polaron is very stable there. The next thing would be to see if even at those temperatures you get polaron-polaron interactions and maybe already binding of these whole pairs in the standard 2D scenario without mixed dimensions. What we know at 0.15 should be very interesting, because then on the BCS side at least you get basically condensation, and in the repulsive side you would get basically XY magnetism for magnetized samples. So there are a few interesting benchmarks now to hit. Whether we'll reach I think by now from the Simons collaboration, if I trust their results, we don't believe that in the standard Hubbard model there will be superconductivity in the square lattice one. Although I would say for higher doping it's not ruled out yet. But what we think that's going to happen is that stripe phases emerge. So out of these polarons, bound polarons, stripes will emerge, and that's what we should be seeing.
Okay, in the interest of time, I think we'll have to stop here. Let's thank the speaker, Professor Block, once more. Further questions can be discussed during the coffee hour after the following talk. Okay, so while things are getting set up, let me introduce the second speaker of this session, who is Professor Jae-yoon Choi from KAIST. So Professor Choi did his PhD work at the Seoul National University in the group of Professor Yong-il Shin, and actually joined Professor Block's group at LMU for his postdoctoral research. He then returned to Korea and joined KAIST as a faculty member in 2017. His talk will be about quantum simulation of non-equilibrium dynamics and measuring non-local order in 2 dimensions. Please welcome Professor Choi.
All right, first of all, I'd like to thank to the organizers in inviting this wonderful workshop, to see the nice peoples and also my old colleagues. It's a very wonderful chance to see here. And today, I'm not sure I can cover all the topics, but I'll try to deliver 2 key messages that we recently carried out on the name of quantum simulations, how the quantum simulation can carry out some non-trivial problems that happens in non-equilibrium system. That will be the first topics. And the second time, if the time allows, I also like to introduce our recent result that has been collaborated with Professor Ki-kyung Cho at Postech that measure the non-local order parameters in 2-dimensional system. Right, before starting, I'd like to thank to my team members and collaborators. These are the students, which are a bit outdated. And also I'd like to thank the theory collaborator that is related to bulk gases, without lattice system. And also, as I said briefly, I also thank to the Professor Ki Young-jo's group that is related to the second part of this talk. All right. Let me give you for the first talk, the non-equivalent system, and the basic motivation is as follows. Imagine that you have some kind of quantum system and closed quantum system, and you bring the system far from equilibriums. And the fate of far from equilibrium system, naively you can say there are many scenarios can be happens, like non-summarized and summarized in one time scale and two time scales. But the central idea and central question that I have interested in is, can we somehow classify and find some universal behavior on the ways toward finding summarization or toward equilibrium phases? And that is actually possible, for example, in the classical cases, and the famous example like coarsening, although it happens quite not very far from equilibriums. It happens with a thermal bath, and therefore it's like classical system. But we know that we have to classify this coarsening dynamics by looking at, for example, the gross dynamics of the characteristic lengths. And we have like bunches of different models and classifications. And so you can ask the question, can you do the same thing in the quantum system? And the answer is yes, at least in theoretically, there are some proposals that if you bring your system very far from equilibrium, there is so-called non-thermal fixed point theory, which is analogous to fixed point theory in phase transition, such that your initial condition, no matter what you have, as they're passing through this fixed point, it follows a kind of universal scaling, the dynamic scaling over the space. And there are bunches of experiments has been done by the Heidelberg groups and the Cambridge groups and also Vienna groups. And they are different systems, spins and both gases and 2Ds and very different system. But all they have find out this kind of nice collapse behavior of spatial temporal scaling behaviors. And also, more recently, we have find out some evidence of the so-called emergent hydrodynamics, which means that by stating the microscopic Hamiltonian, for example, the XXZ Heisenberg models, can we predict or can we incorporate predictions of these time evolution dynamics with the hydrodynamic equation that governs with large scale dynamics? And that has been also nicely demonstrated by the Professor Luke's group and also others, where these KPZ universality classes actually conjectured in the XXZ Heisenberg model, which has been recently demonstrated. And going back into our motivations, my talk would be focused on how we can then, if we can classify the universality classes, then what would be the role of the symmetry of the Hamiltonians? And the key messages of this first talk is the symmetry of the Hamiltonian can actually important as far as the relevant topological excitations are mattered. All right, so this is main result for the first talk. We have the results you can find in the archive. We have accepted Nature Physics just a week ago. And here is the contents for that. This is our machines. We usually deal with the atoms collecting in the vacuum chamber. And in the collector, we trap the atoms in the dipole trap. And the atoms have some fine structures. And we use low hyperfine spin state and call them as 1 and -1 and spin 0 state. And that is our quantum sample. You have quantum sample, but not spin half, but spin 1 system. And that is the basic our ranking Hamiltonians. The key thing is these terms, the F dot A means just like ferromagnetic interactions, it actually tells you the kind of spin exchange interactions. Remember that we are actually dealing with spin 1 system, such that if the two atoms in a spin 0 state can collide, they can also produce spin up and down state, and vice versa. This can be happens. That is our key ingredient in the system. And another ingredient in our system, we apply the magnetic fields, then the trivial effect is the Zeeman effect. And the Zeeman effect, we have linear Zeeman effect. Besides this one, we also have a quadratic Zeeman effect, which means if you apply your magnetic fields, you have spin 0 state I favored over spin up and spin down state. So these are the two key ingredients in our Hamiltonian, such that you can writing down your phase diagram or mean field energies as like this one. The first one is the spin-dependent interaction terms, and that one is like, the quadratic Zeeman energy. And in our cases, we use lithium-7 atoms. I'm not not going to talk about the detail, but we are using the ferromagnetic spin interaction such that C2, these coefficients become positive, which means in usual cases, the F value is trying to maximize to 1 in our cases. However, remember that the second part in here, which is quadratic Zeeman energies, and I told you before that is Q, higher Q favors spin 0 state. So if Q is very large, then you can imagine it will have spin 0 state, right? Like this, all the spin components are localized in the spin 0 state, while on this part, like Q, for example, Q equal negative or Q equal 0, then your ground state is just ferromagnetic phase. Of course, it depends on the types of which Q values are resident in. And some extreme cases where this, the sign is reversed, then you can imagine the ground state is this spin down or spin 1 state. Okay? And getting knowledge of this phase diagram, you can actually carry out some kind of mental or Gedanken experiment. I mean, I'm saying that our interested in the far-from equilibrium dynamics, how the system find on the way is thermal equilibriums. So usually what we do is we first prepare some initial state. Well-defined initial state will be some ground state just like in a polar phase. So all spins are populated in the 0 spin components. And then we can imagine 2 different phases that, for example, like Q equal negative, then as I said, the spin up and spin downs are the order parameter symmetries, or in other words, it's these 2 symmetries. And we're also interested in the cases with Q equal exactly the 0. And if the Q equal exactly the 0, then you look at this Hamiltonian. This one is only have these F and F can pointing in any arbitrary space. It does not have pointing to any specific point directions. So these are the 2 target state that we can study. What I mean is, I will show you the 2 different experiments. By starting from the polar phase, we crunch a so-called Q value very rapidly into the regions of here, where Q is negative, that favors the spin up and down part, or we crunch the system into Q equals 0, where the Hamiltonian has like this SO3 symmetry. And also, this cartoon picture just represents the associated topological defect, like the domain walls and the spin vortices that is allowed to form these order parameter symmetries. All right, yeah, that's the experimental result. At the beginning, we've prepared all the atoms in the spin 0 state, and we crunch the system to have Q equal negative. And Q equal negative means this becomes no longer a ground state. So it becomes very highly excited state. And you see, as a function of time, what's going on. And at the beginning of this crunch, we see the spin 1 and minus 1 populated just because of the dynamic instability, just like it is. You falls off these balls on the top of the hill, it just that these very small quantum fluctuations amplify the populations in the spin 1 minus 1 state. And after some time, we find that all the spin 0 components are washed away, and minus 1 and plus 1 remains. However, the dynamics still goes on, as you can see in this picture, such that if we plot these magnetization densities, you can see the domain size that actually grows over this time. Okay? To characterize the domain growth, we analyze these correlation functions of these magnetization densities in 2-dimensional one, and it's quite symmetric, so we take larger averages of these spin correlation functions, then that's the result for that. And the negative sign, of course, means there is anti-correlations at some distance. And we just perform and analyze these correlation functions at just different time, for whole time. And to find whether this follows the universal scaling, we set some characteristic domain lengths where these correlation functions first meet these at 0 values in here, right? Then after the rescaling these radial positions, we find that all these correlation functions at different whole time beautifully collapse into a single curve. We do not actually do anything post-imaging processing here. We just take the images and analyze and averaging out, and then rescale this function, we find a beautiful collapse onto a single curve. And more on that, we find that the numerical simulation also perfectly agree on the top of our experimental result. And then the next part is then what is the universality class belongs to this dynamics. And in order to do that, we have to analyze the growth dynamics of the domain lengths. And this is the result of the domain lengths as a function of whole time. And again, plotting the result on the top of the theory is also find a good agreement with it. And yes, the quick question is what is the dynamical exponent? I mean, 1 over z. And to get this one, we take the logarithmic plots to get the exponent, which have around 0.6. And this value is actually consistent with the numeric simulations. However, it is not consistent with the previous result, which is done by the Blakey's group in PRL. They find out this is about 0.66. And that is actually comes from, if you analyze your superfluid dynamics, I mean gross type equations, and with suitable manipulation, you will find out it kind of follows hydrodynamic equation in terms of superfluidities. And if you have the zero viscosities, then what does the hydrodynamic equation predicts is actually the inertial hydrodynamics that has exponents of 2/3, which is a bit larger than our experimental results. So what's going on? And we guess that it is actually comes from the finite size effect, because here this simulation is kind of infinite system size, while we have always finite size limited. Put some numbers our experiment, we find that our window, I mean time and spatial window, is at the beginning of these universal regions, such that there's also some studies that what is the dynamical exponents will varies across the different system size. Okay, putting our numbers in here like 30, we can extrapolate that here, which is a bit around 0.6, right? So it does not sound so bad, right? However, somehow the referee does not satisfy by this argument, so we have to carry out additional numerical simulation with large system size, and indeed we find that as you increase the atom number, we find the exponents are actually approached to the thermodynamic limit, which is to 0.66. This is again is not experimental simulation, but the numerical simulation with large particle atom numbers. All right, and what else? Yes, we have to test the different initial state, because we may have some very lucky state to display these special exponents. Well, it's not true, because we have various like spin 1 and minus initial state, or quenching into different quadratic Zeeman energies, or we perturb the system, or more dramatically, to inject vortices in the system. And no matter what we have, we always find the same lower universal function that we already find out, and also the scaling exponents also scatter around 0.6 in here, which is clearly distinct away from viscous and diffusive hydrodynamic equations. And in that sense, we are pretty sure that this dynamics is quite well agrees with binary fluid inertial hydrodynamic universality classes. Oops, 10 minutes. Okay. Okay, sounds good. And then, yeah, as I said, we can actually change the tune, the symmetry of the Hamiltonian. And that is actually one of the nice things in our system, because just by tuning the quadratic Zeeman energy from negative value to the z value, you can actually tune your symmetry of your Hamiltonians, right? And see how the systems react. And basically, the experiment is really the same, but only the different thing is, because in these cases, q equals 0, your spin vector can point in arbitrary vectors. In previous cases, you have only up and down state, but in these cases, you have measuring the x-axis and z-axis, always so very similar behavior over the whole time. And again, yeah, I'm not going to repeat the same pictures, but both result refers to the spin correlation function along the vertical axis or the x-axis. They are all agree with in a single curve. And also the exponents, we clearly see a distinctive exponent from the Z2 symmetry cases. And again, it's smaller than this infinite size numerical theory because of the, I guess, finite size of the system. And furthermore, what is important in these cases, the presence of spin vortices. The questions about these implications for this, smaller scaling exponents is actually the fact that these vortices, the dynamics of vortices actually mediate the annihilation dynamics of the vortices actually mediate these growth and coarsening dynamics. And we try to investigate the evidence of these vortices here, which is written in terms of wave functions like this one. And each component, you can see this one as spin 1, 0, and -1, such that if you just imagine, if you have one spin vortices in the condensate, then you can say it's a superpositions of this kind of state. And we wanted to measure this kind of relative phases. How we can do that? We can just simply apply the RF pulse. You can apply RF pulses, then you can mix all the spin state such that after the interferences of this each spin state, then you can read out the relative phases of the state. And to enhance the visibilities, we apply a linear gradients along some certain directions. And this gradient, you can just understand like the rulers of the phase, that in each color change, it means that accumulations of two phase windings. And in these cases, you see two bright spots across it, which means that 4 pi across. But in this case, you have 3 times across a bright spot, which means you have 6 pi. So you have 2 pi phase winding around these defects. And that's the result. That's the result where we apply the RA pulse and take the pictures. And you can clearly see there is kind of joint 2-to-1 Y-shaped patterns appearing here. Or sometimes you have some Y-shaped that appear at the same time, which implies these plus and minus spin vortices are actually seen in here. And indeed, as a function of different hold time, we also see that the number of vortices is actually decreasing as you increase the hold time. And from these knowledges, we can actually get the relative distance between the spin vortices and the number, such that it actually follows this predicted scaling, so to say, that is given by domain Melk laws. So in that case, we are quite confident that this domain coarsening is associated with the annihilation of spin vortices. So the first part, I could conclude that we are able to tune these symmetry of Hamiltonian by quadratic demand energies and observe that each cases, the dynamic scaling are well represented with different and distinctive scaling exponents, such that it can classify the model H or the ON Hamiltonian in terms of non-summer fixed point theory. And again, the key message is the symmetry is quite important, and also the relevant topological excitations. Okay, how many time I can have? 7? Whole time? Okay. All right, sounds good. Maybe I can jump into the second part of this talk, which is also very pleasure to introduce in here, because this is especially joint collaboration with group with Postech. And the motivation is, as this says in the main text and the title, we are interested in non-local measurement, non-local order measurement. And usually, physics law is like local, so as you might know, phases of matter is usually can be characterized by this kind of local order parameters, like the BCs. However, we have witnesses that it is not enough, right? We have some cases that topological orders matters, and the celebrated example is like this Haldane spin 1 Heisenberg models. And yeah, this is a properties that the ground-state gap state. And, you know, especially for these modifications of Haldane models, which is the AKLT models, it had exact solutions, which is like alternating kind of spin correlation. So it does not seem to be manifest in these pictures. However, if you just delete this as zero spin component, you will find out that plus and minus are actually alternating to each other, which means somehow these antiferromagnetic spin orders are being hidden, such that you need to measure this kind of non-local order parameter to really characterize those kind of state. And this is going to be very similar happens in the Mott insulator state. Mott insulator state, in the very, very deep cases without any hoppings, you can imagine this kind of Fock state, which is product state. By the way, this yellow spot is just the atoms that occupy the lattice side. However, with a finite tunneling, you can imagine there is a tunneling between the next side, and therefore we can imagine the kind of particle hole pairs that can be generated. And these particle hole pairs, or string correlators, can be captured by these kind of string correlators, and delta K means just, the deviation from the mean occupation, such that if there is a hole, it becomes a -1, and if there is a particle, it becomes a +1. In other way, it gives a minus sign. But the key idea is by multiplying this minus sign together between them, so they are being cancelled out to each other and gives a sign of +1. And this kind of business has been well demonstrated in our community, especially the blocks group, like Mott insulator in one-dimensional system, and also in the Fermi-Hubbard models. And more recently, Rydberg arrays also using this kind of product of these operators, string operators, string operator to characterize these non-local orders. And the motivation for this work is can we have something higher versions of these kind of non-local orders, right? In previous case, you just multiply operators for this product state, but in this case, can we introduce some kind of high order non-local order parameters questions? And of course, it is not so trivial, but on the other hand, it is so trivial because the case is 0. And the reasoning is, as represented in this article, is if you just multiply this parity operators just like before, it turns out that it's actually exponentially decaying or more than in higher dimensional system. And the reason is quite straightforward to see in this picture, because every time you cut your domain in here, then maybe inside of this particle Hall pair, it have minus and minus, so it becomes cancels out. But at the boundary, it can randomly have -1 and +1. In other words, the number of domain cut through this boundary determines the expectation values of these parameters. It can be -1, +1, and in randomly, and therefore you get the 0. However, very recently there is a kind of remedies made it, such that if you have some kind of clever ideas that somehow project this kind of lattices with m column into a spin with effective spins with lengths of 2m+1, they can also introduce those kind of correlators such that even if it is two-dimensional system, still can find a non-zero values at all. And more precisely, I can argue that this is basically the main part of these messages for them, which is this O is just parity operators, or the number operator that I told you before, and they just taking some powers on that. And these powers on this one is scales of something like this system's dimensions in here. And the reason here why it works about alpha is larger than 1/2 is just because in the marginalizing phase, this operator is approximately mapped into the number of fluctuation in the system, such that the number of fluctuations, as you can see in this picture, is usually proportional to the boundary of the system. And therefore, if the alpha is larger than 1/2, and therefore it gives a finite values. Yeah, and here's the result. And run out of time, so I don't know how to end this one, but let me continue. This is our microscope images, and this is our Martin slaters. And this is our Martin slater images. You zoom in. Of course, you can do. I mean, you can just making a product of parity operators. By the way, there is a similar work that done by Bloch's group, as he briefly mentions, which he has implemented like tunable optical lattice system. And I would say this is not of order parameters, but still it's very good parameter, because one can actually characterize roughly the superfluid and margin fluid system in a finite system size, which also show all the different lattice system can also predict this kind of phase transition-like behaviors, right? However, as I said, it cannot be on order parameters, because as the size increases, as the system size increases, then it goes away. So what's the problem? There are actually one, but yeah, I only show the key ideas, so sorry. There is actually two problems in here. The first one is, this is kind of light-assisted collision processes. Bloch group has like the fantastic techniques that can measure like doubly occupied site, but usually, if you do not have this one, what we measure is not the site occupation, but the parity of the site. In other words, if you have two atoms, then the lights scattered out 2 atoms away, such that you can only measure the parity. And just like in these pictures in here, you have 2 holes in the side here, 2 holes and 2 holes in here. And maybe these mud insulators, these pairs could be correlated particle pairs, and highly likely to be, if we believe that it's our physics. And those holes actually can be uncorrelated thermal holes or the imaging loss processes. And in these cases, our number of fluctuations in here not scaled with L, but L scale, just because we do not know, actually precisely know what is the site occupations, right? So then can we distinguish those particle pairs and those uncorrelated pairs? And that is our many motivations to do that. Okay, time is really up. Okay, sorry. I only explained the key ideas on that. The key idea is that it's as follows. Yeah, let me imagine you have situations like this one, right? You have particle pairs in here, and you have some atom losses like the imaging losses or the thermal holes. And this is what you see. We do not know whether this particle hole pairs in there and there, right? And you want to distinguish whether this one is really the free hole or uncorrelated hole. And then you will going to imagine some kind of probabilities between 2 pairs, right? These guys will pair in here and there and there. And we know what is the error rate. We know. By measuring very deep Martin-Slater result, we know what is the error rate. It's usually order of 3%. And then the idea is, when you calculate somehow, in some method, when you calculate the probabilities of these pairs to be pairs, like two holes, and the maximum of these guys, all the pairs, is smaller than this error rate scale, then it's not correlated, right? We can assign them as a uncorrelated one. And the key idea is how to calculate this PIJ. Of course, if you're using the sticking on the Bose-Hubbard model, it will be no gain at all. So our colleagues developed a very genius idea that it can be mapped into, the parity project of this system can be mapped onto the Ising models such that if you're taking this ansatz in here, right, this guy's exponentials of beta, effective temperatures of two spin correlators, spin X correlators, and for example, this case is all the spin down particles. With this operator, you can imagine two particles are flipped up. And just like the particle-hole pairs in the Bose-Hubbard models. And of course, the higher temperature, the flip pairs can be a longer distance, such that they can have a longer distance particle pairs, just like in here. Okay, and the key messages is this probability can be easily calculable in the Ising error models, such that we can distinguish what is the holes and what is the particle pairs. And skipping this one, yeah, that's the key result for this one. And this open symbol is just raw data of these parity correlators, about 100 lattice size. We have no clear data, and this dashed line is zero error limit. There's no defects and no imaging errors, only particle pairs. However, our AC, the error correction here, again, error correction does not mean the quantum error corrections, right? Just correcting the uncorrelated ones, can dramatically improve these kind of correlated signals that it can actually comparable to the defect-free limits. Okay, so yeah, because of the time limit, I think I have to conclude this one. Yeah, we can further measure this fractional Brand correlator such that it has literally no domain length, the system size dependence entire like over 100 lattice sites. Yeah. All right, to that, let me conclude. We are still want to explore some universal dynamics in far-from equilibriums, like in 1D XX model, or like in two-dimensional XXZ spin high-cycle models. All right, thank you for your attentions, and apologize for the delay.
Last talk before coffee break, so I think we can take one or two questions.
Yeah, thank you so much for the great talk. So I'm not sure I 100% understood what you talked about the last part, but so I guess you did some mapping between both Hubbard Hamiltonian and some Ising-like model, and like I'm wondering how did you deal with the Hilbert space in both Hubbard that cannot be mapped into Ising model, because there could be, for example, three particles in one.
That's okay. Very good questions. We are actually not doing exact mapping between both Hubbard model to the Ising models, because it's not possible, as you pointed out, right? What we map is like take an analogy is a parity project, because in that cases you can only have parities only 1 or 0, which is in terms of space can be also mapped into the Ising model. So we do not actually precisely mapping the Bose-Hubbard model to the Ising, only the image itself.
Thank you.
Yeah.
Are there other questions from the audience?
Thank you for a nice talk. And actually, I want a mode transition part. And actually, this kind of mode transition have studied in the, of course, very much studies. But you seeing this correlator, what is new things we can learn from the experiments? Actually, like maybe you little bit showed like a domain wall size or such correlation. Yeah, I want to know that.
Yeah, that's very good questions. Yeah, that is also my question too. I mean, but this motivators is like can we measure this kind of highly non-local order parameters in higher dimensions? This is the main motivation. And of course, the next question would be, what would be the new and something G9 features when using these parameters?
Is there, for example, like you consider more doping and seeing the like pseudo gap or strange metal-like phase and to figure out something, or is it possible, or do you try, or?
Well, first of all, this using this parameter would not work because it's actually targeting balls of the model, not the Fermi of the model. So you need a bit more twist because you have spin up and down spin state. And that's also our question.
I see, okay.
Thanks.
Yeah, thanks so much.
Okay, so I think we can, if there are further questions, I think we can take it during the coffee break. Let's thank the speaker once more. And we can reconvene at 4:40 for the second half. Okay, so as people are coming in, we can slowly start the second half of the session. So the first speaker for the second part of today's session is Professor Abraham Steinberg from University of Toronto. Actually, Professor Steinberg also serves as the director of the Quantum Information Science program at the Canadian Institute for Advanced Research. And Professor Steinberg received his PhD from Berkeley and the group of Professor Raymond Chow. And afterwards, he worked with a number of renowned researchers, one of which is Professor Bill Phillips at NIST, before joining the University of Toronto as a faculty member in 1996. Professor Steinberg's research focuses on the intersection of entangled photons and ultra-cold atoms to study the foundations of quantum physics. And for his contributions, he has won many prestigious awards and is also the fellow of the Royal Society of Canada. Please welcome Professor Steinberg with a warm round of applause.
Well, thank you very much for the kind introduction. And again, I want to echo all of the other speakers in thanking the organizers for having us here and for putting together such a remarkable program. It's really been a pleasure listening to these extremely high quality talks and getting to hear so much about so many different fields. So today, I want to tell you about something kind of fundamental, about really trying to think about what's going on inside the box of a quantum system, what I like to call quantum archaeology, trying to look at the footsteps of some creature and figure out what it is. Before I do that, though, I have a few practical things that I want to stress. Like many people these days, we're looking for new, bright, young folk to work with, and also bright, not as young folk to work with. In particular, I'm, as usual, looking for a postdoc. If anyone is looking for a postdoc position or knows people who might be, especially on the quantum optics side of things, please let them know to contact me. Also, our center, the Center for Quantum Information and Quantum Control at the University of Toronto, runs a prized postdoctoral fellowship program. So not just I, but dozens of other researchers are looking, and I encourage you all to take a look at the website, think about applying. Also, like many other places, we're looking for somewhat older people. At the moment, we have a search for a senior professor, either at the full professor or associate level in quantum information science, extremely broadly defined. So please, if you're interested or know people who are, the applications close in a few months. All right. It's a nice place to come, by the way. That's the view from my office window. And these are the names of the people who've contributed to the research over the years. I've highlighted in red the names of the people, whoops, I went too far. The names of the people who've been most instrumental in what I want to tell you about today. So we have a Bose condensate effort, another cold atoms effort on quantum atom-photon interactions, and one more on photons and foundations. I'll be discussing the first two today. And our work studying tunneling times using the Bose-Einstein condensate was led over the years by many different people, but most recently, Ramon Ramos and where is he? David Spearings and Isabelle Hassicot did the work that I'll talk about a bit. And that's been taken over since then by Joseph McGowan, Nick Mantella, and Harshil Neeraj. The work that I'll tell you about for the second half of my talk was really pioneered by Josiah Sinclair and is now being led up by Daniela Angulo Murcio, along with Kyle Thompson, Vita Michelle Nixon, and Andy Zhao. We also had a lot of theoretical help from Grace Lee, Howard Wiseman, and most recently we're collaborating with Joseph Tywison on some of the atoms experiments. So here's where I'm going to try to take you. I'm going to begin by just sort of giving you the big picture of what our interests or our obsessions are, what we're trying to study, what I mean by the histories of quantum systems. And then I'll tell you about two different experiments. The first one is a little bit older, so I'll try to go through it kind of quickly and give you basically an advertisement for our work on atoms in light, studying how long an atom spends tunneling through a forbidden potential, tunneling through a laser beam in particular. And I'll mention some of our current and future plans for what to do next with that experiment. But then what I really want to tell you about is our newest results, both experiment and theory, on a kind of complementary question: what is light doing inside atoms? And in particular, the question I want you to think about is when a photon is traversing an atom cloud or any other kind of dielectric, how much time should I think of that photon spending as an excitation trapped inside the cloud? And then I'll have a little summary. All right, so here's the question in the background. Quantum archaeology, by that I mean, is the wave function really the whole story, the way that we're taught in quantum mechanics? Or is there something else I could measure now that would tell me something I didn't know yet? Could I, by making additional observations, learn more about the quantum system than I knew from just the way that I prepared it? And, well, all right, I'll show you on the next slide what I really mean by that. We're all taught that in quantum mechanics, I can't look at a present observation, like where did a particle land on a screen in an interferometer, and use that to draw conclusions about the past. I can't ask which slit did the particle take to get to the screen. And of course, this is very different from our everyday experience or from classical physics or from other fields of science, such as paleontology, where we dig up a bone and we draw conclusions about what was going on 65 million years ago from the condition of that bone. And the point that I really want to stress is that as far as we know, the entire universe is quantum mechanical, and that includes the dinosaurs. So when we look at that bone, or we look at the cosmic microwave background radiation, or we look at spilled coffee on the floor, we are drawing conclusions about the history of quantum systems. So the question is not, are we not allowed to do that? The question is, what are the limitations? Just as the uncertainty principle limits how much we can say about the future, there are going to be limits on how much we can say about the past. But I argue that we do learn about the history of quantum systems from our present observations. And I have a favorite example of this. It's due to Aharonov and his collaborators. I don't know if the same game is played in Korea. When I was growing up in New York, this is how we like to cheat the tourists. We would put some money under one of 3 shells and scramble them around, and the person who gambled with us could never find the right shell. So Yakir made this even more complicated when he offered a quantum version. He said, what if I put the money in a superposition of 2 different boxes? I'll put it in A plus B over root 2. Well, obviously, you're not going to be able to predict with certainty where you'd find the money. And he said, that's okay. I'll give you an extra hint. I promise you that later on, I'm going to find the money, but I'm going to find it in a different superposition. I'm going to find it in B plus C over root 2. And I won't take the time to quiz the audience. I've done this a lot. My usual experience is that physicists say, this is meaningless, you can't answer it, you have no information, blah, blah, blah. Non-physicists guess the correct answer, in my opinion, right away, because they haven't been overeducated. So what are the odds that the particle was in one box or another after I prepared it, but before I make this subsequent measurement? The answer by Yakir Aharonov's formalism is that it had to be in B with 100% certainty. And the non-physicist gets that right away because they don't really know what plus and root 2 mean, but they get the idea that this means it was either in A or B, and this means it was either in B or C, and the only thing consistent with both is B. And physicists say, well, you can't really reason that way. Well, if you think about it, how would I do the experiment? I would put, let's say, a photon in a superposition of box A and B with a beam splitter, and then I would detect it in a superposition of box B and C with another beam splitter and a detector over here. And I think we all agree that if I sent photons from this detector and found them over here, we would conclude that they had taken path B, not paths A and C, right? Drawn that way, it seems obvious. So I don't mean to trivialize the thing, because the point of this formalism, what Aharonov calls the weak measurement formalism, is for any situation, you can calculate the, what he calls weak value, the sort of conditional expectation value of any observable. Even if you make this complicated interferometer with different phase shifters, I could ask, when a particle comes in a particular port and exits a particular port, what would the effect of that particle have been on a probe sitting near any one of these boxes? And we really can answer questions like that. And I won't go into the details. That one's a little bit controversial. What really got me excited about this formalism was when I started working on the question of the tunneling time many, many years ago. And I realized this would probably be the right way to answer some of the deep questions. So you all know about the familiar tunneling experiment illustrated by the coyote up there. On the other hand, you probably also realize that when we do this as undergraduates, we're taught how to calculate the transmission probability, but we're not taught how long it takes to get to the other side. And it's certainly not because no one ever asked themselves that question. All right, people started asking that question at the latest 1932, 6 years after the first discussion of tunneling. My guess is they were asking it from 1926, but they didn't publish their answers because they didn't make sense to them. But starting in the 30s, people began to answer this question. And of course, from a semi-classical viewpoint, it's a little confusing because as I lower the energy towards the top of the barrier, the kinetic energy, E minus V naught, goes down, the velocity goes down, and the time goes up until it diverges when you're right on top of the barrier. And if you go any further than that, you have negative kinetic energy, which would seem to imply an imaginary velocity. And we don't really know what to do with that, but these imaginary numbers are going to come back in a while. Well, of course, that's not the right way to solve the problem. And we all know, hopefully, how to calculate the motion of wave packets and the group velocity or the group delay. You don't need to anymore. You can just program a simulation of the Schrodinger equation on the computer. In fact, you don't need to do that. You can just go to Wikipedia and download the simulation of a tunneling wave packet. And you could look at when the incident peak is coming in and when the transmitted peak is going out and take the difference. And you'd get an answer. There's a problem, though. This is described by the stationary phase approach, the way we usually calculate group velocity. And that involves looking at the phase. But we also know that while the incoming wave packet picks up phase, it looks like e to the ikx times some envelope, and so does the outgoing wave packet. Inside the tunnel region, we just have real exponential decay. There's no phase accumulation. So the consequence of that is that the phase at the output becomes nearly independent of the thickness of the barrier. And the time delay that you get from stationary phase, since you calculate it by looking at the phase, also becomes essentially independent of the barrier thickness. Well, why is that a problem? Eventually, the barrier can get so thick that this constant time is less than d over c. So it seems to contradict relativity. And this disturbed people right away. You might argue, oh, it's the Schrodinger equation, it's non-relativistic. That's not the problem. You can redo it with Maxwell's or Dirac's equations, fully relativistic, and you get the same result. You could say that the stationary phase approximation just breaks down, but it turns out that it doesn't. And 20 or 30 years ago, our group and a bunch of others did experiments verifying this really is the behavior of the peak of the envelope of the wave packet. It is described by the group delay, and there's no conflict with relativity. There are some subtleties thinking about it, but don't worry. I'm not arguing that either information or energy travels faster than light. My question is really what was going on as it got there? How did it get from one end to the other? Not the peak of the wave packet, which is just sort of a motion of effects, it's an interference pattern, but an individual particle. Where was it spending its time? Should I really think of all the particles as being spread out in the whole wave packet until the moment of collapse when most of the wave packet disappears? Or as in the case of my ABC interferometer, should I think that when I see a transmitted particle, I learn more about what it was doing beforehand? That's the question that kind of obsesses me. How much can we retrodict by seeing whether the particle was transmitted or reflected? And that's what that weak measurement formalism is useful for. As just a historical note, I'll mention there have been many other studies of tunneling times, many different definitions. Some of you might be familiar with the really old experiments on essentially the ancestor of superconducting qubits by Daniel Esteve's group. Many of you are probably familiar with Ursula Keller's work and competing work from a number of other groups, most recently Igor Litvinuk's on what's known as the Atto clock. Most of these measure things that are quite different to what I'm going to discuss. So I'm going to leave them aside and just move on to our experiment. And I'm going to talk about weakly measuring how much time an atom really spends inside the barrier. Not just what its average arrival time is, but what it was doing. And the reason I say weakly is because we want to probe things gently without collapsing them by interacting with too strong a probe. So my favorite version of how one might do this is usually attributed to Marcus Büdeker. He and Landauer in the 1980s really revived this problem of tunneling times and invented a lot of interesting formalism and made some important observations. But Büdeker in 1983 wrote a paper about what's come to be known as the Larmor clock, and it actually goes back earlier. It was originally proposed by Bass and Rybachenko in the 1960s. And the idea is beautifully simple. It says, imagine a particle with spin tunneling through a barrier. Let's say we have an electron, and it begins polarized along the x direction. If inside the barrier region, here I've just drawn a rectangular barrier, or someone else has and I stole their figure, honestly. If inside that barrier region we have a magnetic field along the z direction, then while the electron is in the barrier, it will precess about z at the Larmor frequency, which we know. And when it's outside, it will not precess. So if we look at the transmitted particle, we can measure the precession angle phi, divide by the Larmor frequency, and we have a time. So there's a concrete way to operationally define how long the particle spent in here. And interestingly, you could do it either on the transmitted or on a reflected particle separately. So you really could ask the question independently for those two sub-ensembles. And for a while in the 80s, that had been controversial. People just said, you can't ask both questions. How much time did you spend, and were you transmitted or reflected? But operationally, you clearly can. There is a confusion, and this is what Boedeker really pointed out in '83, which is the way to understand this X-polarized particle, if I have a magnetic field along Z, is to decompose it into a spin up plus spin down. Those are the eigenstates of the problem. But of course, the spin up is aligned with the field and therefore sees a slightly lower energy than the spin down, which is anti-aligned with the field. But the transmission probability is exponentially sensitive to the energy in the barrier region. So what that means is that the spin up is going to be more likely to be transmitted than the spin down. And in fact, when you look at the transmitted electron, you'll mostly see something that has just sort of tilted up towards the z-axis. Not because there's any torque in that direction, but just because you're preferentially transmitting the spin up portion. Now, Bas and Rybachenko seem to think that you could get rid of the effect on the probability by just taking the limit as b goes to 0, do a very gentle measurement, and if this time is well defined in that limit, then that works. What Boedeker noticed is that both the precession about the z-axis and the tendency to align with the z-axis are first order in B. So taking the limit doesn't change anything. And in fact, in most regimes of interest, you're dominated by that alignment, not by the other one. He didn't really know what to do with that. He just added the squares of those two components and said that was a good definition. Interestingly, there was another very mathematical approach about Feynman path integrals that gave a complex number, so had been largely ignored at the time. But the real and imaginary parts of those complex numbers turned out to correspond to the two angles that you see here, the in-plane precession and the out-of-plane alignment. And this weak measurement formalism I was describing, which is specifically designed to ask what happens when you post-select on either transmission or reflection or something like that. It was invented 5 years after Boedeker's paper, but it turns out that this Larmor clock is exactly an example of a weak measurement, and the weak value formalism quite generally gives you complex results, but we understand how to interpret the real and the imaginary parts. So in my mind, that's a way of unifying all of this. We think of this as a kind of weak measurement. We can measure two components, but they have physically distinct meanings. All right, so how do we do this experimentally? I spent years flailing around for the right system to do it in, and then my students spent even more years actually getting the system to work well enough. It's a truly heroic experiment. Whoops, going too fast. We begin with a Bose condensate of rubidium-87 at a few hundred nanokelvin. We then cool it even further. We cool it to about 1 nanokelvin. We have a few thousand atoms at 1 nanokelvin, which means that they have a coherence length of about 4 microns. And the nice thing is that you can build potentials for atoms out of light, which you can focus to less than 1 micron. So with that coherence length, we can begin looking at quantum effects like tunneling. So we trap the atoms at first in a pair of red detuned beams that attract them. And then we turn one of them off so they're just sort of in a waveguide. They can propagate freely left and right until they hit a blue detuned beam, a focused beam at 420 nanometers that acts as a repulsive barrier for the atoms. And by adjusting the intensity, we can change the height of that barrier. We adjust it to be about 150 nanokelvin, which is much higher than the 1 nanokelvin temperature of the atoms. In real terms, what that corresponds to is a critical incident velocity of 4 or 5 millimeters per second. When we push the atoms towards this barrier with a little magnetic field gradient, if we push them at 6 millimeters a second, they're 100% transmitted. If we push them at 3 millimeters per second, they're 100% reflected. And in between, we get to observe tunneling. So that's just a nice movie that we have in a slightly different geometry, but that's of atoms trapped on top of this plane of light that acts as a barrier, and we watch them fall through if they have high enough energy, and otherwise just spill off the sides of the table. A few of them, I suppose, are tunneling all the time, but in this experiment, we weren't able to resolve that yet. All right, we also need the magnetic field. And the reason that we decided to go with atoms is because I didn't know how to localize a magnetic field to a small enough region that it was just, the tunnel barrier for particles, although there is a neutron experiment that claims to have done something much like that. Instead, we decided to use a pseudomagnetic field, to use a Raman transition. Any coherent coupling of a two-level system is equivalent to a magnetic field. And we can couple two of the hyperfine states of rubidium, in particular the two m=0 states that are mostly insensitive to magnetic fields and therefore used in atomic clocks, used in cesium to define the second. And we could couple them with a 6.8 gigahertz microwave, but we can't focus that down to 1 micron. If we instead couple them with two different laser beams with a difference frequency of 6.8 gigahertz, those can be focused down pretty tightly. Excuse me. Well, in practice, we worked as hard as we could to focus our 420 nanometer beam in this complicated optical system to about 1 micron. So we can't yet make a second probe beam more tightly focused. Instead, what we did is we just modulate that barrier beam at 6.8 gigahertz to create an extra sideband. And the beam and its sideband act together as this Raman probe. So anywhere within our barrier, which is made of a laser beam, there's also this effective coupling that acts like a magnetic field. So I'm going to skip the details of the experiment. You can read the paper. You can ask me about it later. I just want to show you some results. As a function of velocity here for a barrier tuned to 5.1 millimeters a second, we see these two different times. This real part, the in-plane precession, that I think really describes what you expect this measurement to do. I think of that as the real time. And it begins to grow as 1 over v when you're far above the barrier. But when you reach the height of the barrier, it doesn't diverge like this Büdeker-Landau or semi-classical time. Obviously, things don't usually really diverge in physics. Instead, it reaches a maximum, and it looks like it's beginning to come back down. And I'll talk more about that in a second. And then there's this other time, this imaginary part. And what you see is it basically doesn't exist in the classical regime. It is a sign of quantum measurement back action, and therefore it only shows up when you get down into the tunneling regime. All right, more recent data, we were able to lower the error bars and also lower our velocity width so we could go further below the barrier. And we did this for two different barrier heights. In red is a high barrier, 4.7 millimeters a second. In blue, a low barrier at 4.1. And what I find really dramatic is if you just follow the red dots, as you lower the velocity, the time starts to go back down. Lower energy atoms tunnel more quickly than higher energy atoms. And you can also compare the red and the blue dots, and you see if you lower the barrier, it takes longer for the atoms to tunnel. So I call this the red light effect. You're unlikely to cross the street when the light is red, but if you do, you cross the street even more quickly than you would when the light is green. All right, so the forbidden particles get through really quickly. So there are a few more experiments that we're planning on. What I'm really excited about is to learn how to focus a probe somewhere inside the barrier so we could measure not just how long did it spend in the barrier, but where did it spend its time, in which part of the barrier. And our predictions so that in this case there'll be a big distinction between the reflected particle shown in red. Here the probability just looks like psi squared because the reflected particles are 99% of the particles, so it's basically the same as the expectation value. And for the transmitted particles, you see a symmetry that reflects the time symmetry of the Schrodinger equation. It reflects the fact that we know the particles came in from the left, but we also know that they exited on the right. And the equations prove to be completely symmetric, within a complex conjugate. So we expect an exponential decay on the left and an exponential rise on the right, and almost no time in the center of the barrier, whether you're transmitted or reflected. So that's something that we really want to demonstrate looking forward. We also want to compare reflection and transmission. And we started doing that, and this is just a shout out to people interested in the many-body physics and the interacting systems, because we were completely surprised to discover that in reflection, you see spin textures that are actually driven by the interactions, the collisions between these rubidium atoms. And it's funny because rubidium-87 is known to have essentially spin-independent interactions. So the only reason for this residual effect is a kind of identical spin effect due to quantum statistics. So we recently submitted a paper with Joseph Tywissen talking about why that's going on. And finally, we want to know whether looking at the atoms affects them. Does the act of measurement really disturb the system? Well, we know it does. So this actually begins with a question that I was asked the first time I came to Korea 25 years ago. I talked about this as just a crazy proposal for the future. And Bill Phillips said, why bother with the weak measurements? Why not measure strongly whether it's in the barrier or not? And my attempt to answer him was eventually published in the Journal of the Korean Physical Society. And a few years ago, we realized that it was wrong. It's the only paper I've ever published there, and it's wrong. But the idea is that if you were probing the atoms, then once in a while, this probe, let's say a photon, would scatter off an atom in the barrier, and you'd get an image on the screen. If you knew that the atom was in the barrier, you would then collapse it to be inside the barrier region, which would automatically give it enough energy to be there. It would have energy at least equal to V naught once it collapsed there. And the question is how exactly this happened. So we now have a scheme where we think we can do this experimentally. And what we realized is that whether or not you collapse the atom and change the tunneling characteristics by giving it that extra energy depends on the speed with which you make the measurement. If you make this measurement too slowly, then you can't learn that the atom was inside the barrier at any particular instant. And right now we have numerical calculations and some analytical work, but no deep understanding yet for what that critical timescale is. Basically, how long does an atom linger inside the barrier if I do a slow measurement and I see that it was in the barrier at some point? So we're planning ahead to experiments on that as well. All right. Take a breath. As I said, I wanted that to be an advertisement, and now I want to move on to our most recent work, which we thought was completely different, and then somehow it just became similar after all. What I'm really interested in now is this question of how long photons spend inside atoms. So we have this picture of photons being, absorbed and electrons moving up to another orbit and then being re-emitted when the electron falls back down. And I really want to just evaluate how seriously we should take that. I'll say that that's not how this experiment started. This actually began as our sort of most applied experiment when we really wanted to learn how to make photons interact efficiently with one another, how to make quantum logic gates. And in particular, there's a brilliant proposal by Kai Nemoto and Bill Munro about turning even pretty weak nonlinearities into deterministic optical quantum computers. And we were seeing how far we could push those nonlinearities to make one photon control the behavior of a second photon. And you can read some of our older work over there on that. But along the way, we got confused by a basic science question. And that's always been my passion. So we followed that for a while. Fortunately, my student felt the same way. And the question is this, as I said before, while a photon traverses a dielectric, and this could be glass, it could be atoms, where does it spend its time? And sometimes the picture that you hear is the reason that light slows down in glass is because even though it's very far from any of the resonances in glass, it doesn't know that right away. There's a sort of energy time uncertainty principle. And you can excite some atom or molecule for a little bit of time, just, delta T smaller than h bar over delta E, until it figures out, oh no, I'm not allowed to absorb that, and it gives the photon back. And somehow that time spent in the atom or in the molecule would explain why things slow down. And I've heard people tell me, never repeat that. That's just a nonsense story we tell our undergrads, and it's not serious. And I've heard other people say, why do you describe it as approximate or hand waving? That's exact. It's rigorous. So I'm still a little confused about the status of this. But it's not as crazy as it might sound. If you think about the index of refraction, just a normal Lorentz profile, far from resonance, it actually does fall off as 1 over the detuning. So it's sort of consistent with that picture, that when you're far away, the time you can spend in the atom goes as 1 over that energy deficit. That sort of makes sense. Obviously, you don't get a divergence on resonance. And on resonance, you're not really violating energy conservation, so you don't expect it. I'm not sure what to expect, except that, there you have dissipation. You might think it would just saturate at the spontaneous lifetime of the atom, 1 over the line width of this transition, or maybe the whole picture breaks down. It was really never clear to me in the past. Well, actually, the situation's worse than that, because the propagation of a photon through an atom cloud is not just given by the index of refraction, but by the group velocity, the group delay. And due to the large slope of n of omega near resonance, that does something very strange. It actually goes negative right on resonance. And that's something that's been confirmed experimentally, including by Steve Chu and Stephen Wang. And it seems really hard to use this picture over there. So you kind of think, at best, that's a picture that maybe works far away, or maybe it just doesn't make a lot of sense. I can give you something a little bit rigorous, though, or at least I'll jump through it kind of quickly, which is we can define what I mean by how long the photon spends inside the atom by just calculating the probability of an atom being in the excited state. That's easy to calculate. In the low intensity limit, it's proportional to the intensity of the light. It's a semi-classical calculation. And if we multiply that by the number of atoms, then we get an average number of excited atoms at any point in time. If I only sent in one photon, I guess that'll be less than one. And this exists at every time. If I integrate that over time, then I'm going to get something with the units of time that we call the average amount of time atoms spent in the excited state. Now, I won't go through the math of it, but basically this probability is just the intensity measured in units of the saturation intensity. The saturation intensity is related to the spontaneous lifetime and to the absorption cross-section, but the absorption probability is also just related to the absorption cross-section and the density of the atoms. When you put it all together, you find what I've written in red here. The excitation time works out just to be the absorption probability times the spontaneous lifetime of the atom. Well, that's an interesting and simple formula, right? Simple formulas always push you to ask, what's the simple story? The simple story would be this. Some fraction of the photons get absorbed in any given sample. And after they get absorbed, there's spontaneous emission. They're just going to get scattered to the side. But that'll take a time, on average, equal to the lifetime of the atom, the spontaneous emission lifetime. And the rest of the photons are just the lucky ones. They didn't get absorbed. They didn't hit any of the atoms, so to speak. They got transmitted, and they caused atoms to spend 0 time in the excited state. So the total time is just the number that got absorbed, the probability of absorption, times the spontaneous lifetime. And that's what my student Josiah Sinclair, who originally prompted this problem, and I both thought. But he decided to do the experiment. And the idea here is to probe the amount of time atoms spend in the excited state. We do that with a second optical beam. And this comes back to that switch we were originally trying to design. It's known as a Kerr nonlinearity. And the idea is very simple in this case. If you do this on resonance, which is normally a bad idea, but it's what we wanted to do in this case, then the photons you send in, what I call the pump beam, can get absorbed, putting atoms in the excited state. But if I put atoms in the excited state instead of the ground state, that changes the index of refraction for the system. So a second beam, which we call a probe beam, will see that. In particular, we had this Lorentz profile. If you have everything in the ground state, it looks like that. But if you have 0 population inversion, equal numbers of atoms in excited and ground state, n just goes to 1 everywhere. And in fact, if you had a population inversion, it would flip sign. So even if we just put a few of the atoms in the excited state, or even 1 atom in the excited state, there'll be a small change from the solid line to the dashed line. And our question was, if I sent in 1 photon at a time, would I only see that phase shift on the probe when the photon was actually absorbed and then spontaneously emitted, and see 0 phase shift for the transmitted atoms? So here's how we do the experiment. We're going to take a sample of atoms. We're going to send in a pump photon, but we'll also send in this probe beam to do a phase measurement. And again, we're going to define our time by looking at the phase shift here, and we think of that as being the time integral of the average number of excited atoms. But then we'll let the pump photon propagate on to an avalanche photodiode, which will either click or not click. But we can condition the phase measurement on whether it clicked or not. Again, this post-selection, what's the final state of the system? And ask, does it depend on the fate of that photon? So this builds on earlier work that we had done. The earlier experiments are published here. Most recently with Howard Wiseman, we published some theory backing up our previous unsupported assertions. But the experiment looks like this. We make a magneto-optic trap of rubidium-85, and we focus both a signal and a probe through that trap, counter-propagating with one another. As I said, the signal goes to a photon detector, the probe goes to a frequency domain phase shift measurement, and we can then correlate these things. And in particular, what we proved is that if you look at the difference between the phase shift when this detector fires and when it doesn't, it really tells you how much phase shift is due to an individual photon. That's even though we don't actually use single photons for this signal. We had a single photon source we'd built for this purpose. It wasn't bright enough. So we do this with a coherent state, and we use this trickery instead to extract the single photon behavior. Well, it's still difficult. The phase shift we expect is on the order of 10 microradians. It lasts for 10 nanoseconds or a few tens of nanoseconds. And there's a lot of background classical noise. As anything else fluctuates, frequency, a magnetic field, the atomic density, the linear phase our light picks up can also change. So for 34 photon pulses, about 20 nanoseconds in full width half max, here's the classical cross phase shift that we see, the curve phase shift. We verified it for 2 different detunings, just as an additional sanity check that we were looking at the right effect. So that we could measure pretty reasonably. But now when we look for the effect of 1 photon, we take traces like this, and we subtract all the traces when a detector clicked from all the traces when it didn't. And it's pretty hard to see anything. But fortunately, we already knew the shape we were looking for, or at least we thought we did. So we fit to a slowly varying noise function, just a cubic, plus this shape rescaled arbitrarily. And I think you can kind of be convinced by some of these that there's statistical significance to this. There's some additional effect when the detector fires. And we analyzed all that. We were able to pull a number out. The number is shown over here. And most importantly, it's not 0. It's not equal to the spontaneous lifetime either, but it's not equal to 0. There are a lot of curves here that were attempts we made at the time to come up with a theory explaining why it wasn't 0. At the moment, we don't think any of those theories are correct, so don't pay too much attention to them. But it raised an interesting problem for us. If you go back and you remember that the total time spent in the excited state is given by the loss probability times the spontaneous lifetime. Well, I can expand this also as the weighted average of the time transmitted photons cause the atoms to spend in the excited state, weighted by the transmission probability, and the time lost photons, absorbed photons, cause the atoms to spend in the excited state, weighted by the loss probability. But I think you immediately see that if tau t is non-zero, tau L must be less than the spontaneous lifetime. So this is telling us 2 things. It's telling us not only that the transmitted photons did cause atoms to spend time in the excited state, but that when photons were lost, the atom spent less than a lifetime before spontaneously emitting, which seemed very strange to us. And in the end, some of the experts may have figured out what we missed. Part of this should have been obvious to us. And in particular, we were working with very short pulses to try to distinguish our signal from the slower noise. Those short pulses have very large bandwidths. They had an RMS width of about 10 nanoseconds compared to the 26 nanosecond rubidium lifetime. So what happens is that propagates through a dense medium, is that it picks up complicated phase shifts and very quickly evolves into a wave function that actually has a phase flip in the middle. Well, if you think about the dynamics of the atoms, after the light looks like this and is propagating through, in the first part of the pulse, it's rotating up the Bloch sphere, but after you get a shift in the sign, a flip in the sign, it begins rotating the atoms back down the Bloch sphere. So in fact, that's a clear mechanism for coherent emission of radiation back into the forward mode, implying that sure, an atom could spend some time in the excited state, and then instead of spontaneously emitting, re-emit into the forward mode. We were originally misled because we said if we're really doing this 1 photon at a time, there's no stimulated emission, how would it know to go in the forward mode? But actually this is very analogous to what happens in quantum memories and things like that. Merely the coherence is enough to give you that effect. This also explains why the lost photons cause the atom to spend less than a lifetime in the excited state. It's because there's this competing process pulling the atoms back out of the excited state before they have a chance to spontaneously emit. Well, whoops. That's a nice picture, but it doesn't give us a quantitative answer. Because remember, what we're asking about here is on an individual event where 1 photon goes there or goes there, how much time did the atom spend in the excited state? And I can't go from those pictures to a whole trajectory of how long each atom spent in the excited state. In particular, we're really asking about entanglement here. We're saying 1 photon either went there or went there, and some other optical beam has a phase that depends on which of those occurred. There's no way our Maxwell-Bloch equations, our semi-classical theories, are going to answer that question. We need a quantum model for that. And it took us another year before we got it. And this was really thanks to Howard Wiseman that we were able to do this stuff. And it did a lot of what we wanted. We kept hoping, well, look, if only we went to smaller optical depths, there wouldn't be time to pick up the phase flip. So this weird thing wouldn't happen. We wouldn't get a time. It would go to 0. If only we'd been able to use a longer pulse, a more narrow band pulse, right on resonance, we wouldn't have had the same funny dynamics, and we would have just gotten 0. So it looked like that was working here. This is the time versus OD for our 10 nanosecond RMS pulse. But then we redid it for the narrow band pulses, and we saw that, yeah, although it goes to 0, it goes negative first. And honestly, I saw this, and I just told my students, all right, go back, you made a sign error in your code, it's numerical problems. One of them, Grace Lee, very quickly showed me that she could analytically take the limit of Howard's formula and prove that it really was negative as OD goes to 0. So it wasn't the coding. So then I yelled at Howard and said he made a mistake, but Howard doesn't make a lot of mistakes, and it turns out his theory was right. So we were stuck with this for a little bit. But we noticed something funny, which is the slope here was kind of familiar. As the OD approaches 0, the time just approached minus the OD times the spontaneous lifetime. In sort of natural units, this just has a slope of -1. And that's when I remembered that the group velocity on resonance not only is negative, but that's exactly the delay that it gives you. It gives you 1 negative spontaneous lifetime per optical depth. So somehow they seem to be starting to agree with the group delay, that negative thing that I didn't know how to describe intuitively before. And in fact, Grace and Kyle were able to go on and prove analytically that even though Howard's formula was this complicated set of integrals, it really was exactly equal to the group delay weighted by the appropriate transmitted spectrum. And the reason we didn't see a negative number in our original experiment is just because we had such a broadband pulse that after you travel through 4 optical depths, all the resonant component has been absorbed, and the only thing that you're seeing in transmission is the off-resonant light, which has a positive group delay, and it's that weighted group delay that you end up measuring. This has an extra funny problem. Remember again that weighted average. Well, now we have the opposite problem. If tau t is less than 0, then that implies that tau l must be greater than a spontaneous lifetime. So now I have a situation where before the atoms are scattered, before the photons are scattered, the atoms spend more than a spontaneous lifetime in the excited state. And that confused us. It still confuses me, honestly. But it turns out to be related to something that was previously known, which is, again, a propagation time, just the delay time for scattered light, which is known as the Wigner time. And Antoine Poiret's group measured that a few years back. And I remember reading about this ages ago, and I don't know, there's some formula, but the important thing is it goes as 1 over gamma. Of course it goes as 1 over gamma. What else could it do? Dimensional analysis, I walked away. I didn't pay attention to the 2. The spontaneous lifetime is 1 over gamma, and the Wigner time is 2 over gamma. So mathematically, it was already known that the time it takes to scatter off of a center is twice the inverse line width for some strange reason. And that turns out to be consistent with our measurements. What we find is as a function of OD, you end up with a time for the scattered light that starts at twice this 26 nanosecond lifetime. And then as you increase the depth, it drops down, goes below the lifetime, and then climbs asymptotically back to the lifetime, which is the result we'd originally expected. And that turns out only to be true in the asymptotic regime. So a lot of strange stuff to unpack there. I'll just say we're currently finalizing an experimental paper. Daniela managed to get her last data recently, and this shows for a number of different ODs versus the RMS width of the pulse, what time we see in dimensionless units. But the important takeaway message here is you really do see this transition from positive times to negative times as you go from broadband to narrow band. So it really does seem to confirm that theory. Before I stop, I'll just say, what do I think the message of this is? I mean, we already knew the group delay. This says something about conditional nonlinearities that's kind of funny. The sign of this optical nonlinearity that we see can change depending on whether the photon is transmitted or scattered, and depending on the line width and all of these other properties. But it changes the way we think about it. It really says, by this definition, the extra delay time of the photon is equal to the amount of time that the atoms spend in the excited state, even if the delay time is negative, that there's some measurable sense in which the system acts as though the atom spent a negative amount of time in the excited state. And coincidentally, right around the same time, there were experiments from Near Davidson and from Bob Boyd looking at something known as the transverse piezo-drag effect. And maybe most of you have heard of piezo-drag experiments, but you probably forgot. It's just the observation that if you have light moving through a fluid and the fluid is moving, that changes the effective index of refraction. If you boost into the stationary frame of the fluid and you boost back, you'll see that you get a change in the velocity. And these were important experiments in the early history of special relativity. Until 2 or 3 years ago, it never occurred to me that there was a transverse version. You send light through a fluid, but you have the fluid propagating perpendicular to the light. And it turns out that when the light comes out, it's translated a little bit to the side. And you can work this out pretty easily, as a matter of fact, a few lines, and you can show that the expected shift is essentially equal to the group delay for the light going through the fluid times the velocity of the fluid. So it's really consistent with this idea that the extra group delay is because the light is trapped in the water molecules, or what have you, and they're moving, and it just co-moves with the water while it's trapped. Well, recently what people observed is that's true even when the group velocity is negative, close to a resonance. So this is a picture from this paper of the anomalous transverse piezo-drag effect, where indeed, if you have a negative group delay, the light comes out displaced opposite the direction of propagation of the fluid. So I think these are two completely different kinds of experiments, but that both suggest to us we should start thinking of these negative times, like those negative group delays, as having more physical meaning than I had realized before. We should just take them more seriously. So with that, I'll just leave you with these conclusions and some references. I don't think I need to read the conclusions to you, but I'm open for questions. Thanks for your attention.
I'll open the session for questions.
Yeah, thanks a lot for the very interesting talk. And on the first part related to the tunneling time, my question was, can you use, say, a double well type system and potential and then look at the tunneling time that way? And is it similar to what you did, or is there a difference?
Yeah, that's a different time. I mean, it could be interesting to redo our experiment with double barriers or double wells or things like that. The double well is different in that it's a closed system, so you really just have oscillation back and forth between the two wells.
Yep.
And it was something that Büdeker and Landauer pointed out early on. There's a difference between how long it takes the average atom to get from this well to this well and how long it actually spends inside the barrier in the middle. And we really want to address that second question. So to us, it's important to have a well-defined start, so to have a wave packet in the continuum hitting a barrier once so that all of the time it spends in the barrier is on that one attempt, and it doesn't get to bounce back and forth in its well 100 times, hitting the barrier over and over again. So in my mind, that's also a little bit of a difference with the Atto clock, where you've got something that's already started trapped inside an atom and then gets ripped out.
Okay, thank you.
Yep.
Are there other questions from the audience?
Continuing that part of the experiment, so why the BEC is needed for that experiment?
Sorry, that's a great question. So it has nothing to do with Bose condensation, nothing to do with that kind of coherence. We just need an atom laser, basically. We need a long coherence length, that 4-micron coherence length I meant. So the only reason we use the BEC is to get that long coherence. And in fact, the BEC isn't enough. We need to use delta K cooling to cool by an extra factor of 100 and so forth. For the other experiments, where we looked at reflection and we begin seeing these spin-spin interactions, then statistics begin to become important. So it's a really interesting question. How does that change in the condensed or non-condensed phases?
I see. So that later part that there's a spin textures might comes from those kind of interactions in the BEC.
The funny thing is, it's actually the other way around. The conventional wisdom in the cold atoms community was this thing called the identical spin rotation effect could occur in systems like rubidium, where the interaction is spin independent, because of the exchange term, basically because of bunching that occurred in the thermal regime that occurred when you weren't condensed. And the argument was once you condensed, there's no more bunching. And in the coherent state, you wouldn't get this. So people were quite surprised that we saw this effect at all. And we now sort of argue that it doesn't need to be thermal. What's important is that there are multiple momentum and spin modes coexisting. But we certainly haven't been able to repeat that experiment in the thermal regime. It would be interesting.
Okay, thanks.
Thanks for the nice talk. And your talk really inspires me a lot. And actually, yeah, in your talk, you mentioned about drag effect and slow light, and also some paper about the fast light case. And what about the epsilon zero case? Can you give some
Oh, I haven't
comment
thought
on
about that at all. That's a really interesting question. Next time I see Bob, I'll have to ask him. I was about to say, I think for this, all that really matters is the group delay, so I wasn't sure anything new would occur in epsilon equal to or near zero. That's not exactly true. There's always a term that I neglect because it's smaller, but it does show up in the equations. And I bet in the epsilon near zero case, you'd have to think carefully about this other term that I always forget. So I just don't know the answer to your question. It's a great one.
Okay, are there other questions from the audience? If not, I think we can thank Professor Steinberg once more.
Thank you.
Okay, and the very last speaker for today's session is Professor Jae-wook An from KAIST. As he's setting up his laptop, I can go over his biography. Professor An did his PhD work at the University of Michigan in the group of Philip Boxbaum. I guess that's before he moved to Stanford. Actually, as a PhD student, Professor An was already one of the experts of Rydberg atoms. But then after joining KAIST as a faculty member, he also extended his research interests to ultra-fast physics. Currently, Professor An is one of the leading researchers in the field of Rydberg atom tweezer arrays. Let's have a warm welcome for Professor An.
Thank you very much, 박재우 교수님. So I haven't changed my field. I always have been working with control of laser field. So today's my discussion is quantum simulation of single atom array, which is prepared by optical tweezers. Okay, so. For example, here, this is a summary of main results. So in this case, there are 6 atom chain, and this magnol, which is a quasi-particle spin excitation. In this case, it's a Rydberg atom, is prepared here and here, and these 2 atoms are bound, making a magnon complex, and they move coherently here or there together. So they can be seen by this correlate measurement as a function of time, or bound, or unbound, frozen. So do not move. In this case, you can make this bound magnons with the next nearest neighbor, not the nearest neighbor, but next nearest neighbor, and they can move together to coherently this way, that way. So experiment, we can observe these ones. So to explain this, I need some introduction to Rydberg atom many-body system. We call this a Rydberg atom quantum computer, but this particular presentation, this is a Rydberg atom many-body system. It has many advantages, like massive scalability. You can scale like very easily by using high-power lasers. And also, it can make a qubit graph, so atom graph. So, for example, the one shown here is a kind of graph where this vertex represents atom, and this edge represents strong interaction between atom. Then they can not only make an array, but also they can make mathematically more general graph. And also, it can be coupled with atom clock technology. Actually, this platform is this currently developing next generation atomic clock. So it's soon to expect to have a high fidelity. Okay, so Rydberg atoms are very big, so it can size can go like into the second power, easily go to a micrometer size. And if vacuum allows, you can go to even bigger. Not only that, but this radiative lifetime goes into the third power. So in this range of like n equals 70, already we go to something like a quarter of a millisecond. And this interaction between two Rydberg atoms at a distance of a few micrometer scales with n to the 11th power, so easily go to some megahertz level very easily. So that goes really beyond the laser bandwidth, which is on the level of sub-megahertz. So typically, we use the transition from S to S state through a two-photon transition. So I'll go back to that later. So then easily we can make, because of this strong interaction, certain kinds of entangled state. For two atoms, it's Bell state, and three atoms, W state. Depending upon the graph configuration, you can make all kinds of entangled state. Also, we can move using the optical tweezers to relocate the atoms. So initially, the atoms are just gathered with a sort of random array. So we can move these atoms to make a completely complete like some wanted atom, like zero entropy array. So these optical tweezers are therefore using to hold or guide. Actually, one of the latest work in our work is we now can use optical tweezers to draw atoms and recatch. Or even we can use optical tweezer as a whip to further accelerate the atom of traveling atom. So all kinds of some classical treatment of like a mechanical treatment of these atom motion and positions. Okay. So these particular kinds of method can be used to make a three-dimensional, but also you can use this atom, some part of the arrangement of atoms as a kind of another purpose, which is a wiring. So then, for example, if this is a graph, and if you use some of the atoms as a sort of auxiliary atoms to be treated as a quantum wire, then actually some of the calculations or many-body ground states of this atom can be used to calculate or obtain the many-body ground state of certain different kinds of graph, which is difficult to implement, for example. So in a mathematical theorem done by Grotowski, if any planar graph, which is two-dimensional implementable by this optical tweezer system, graph is implementable, plus two different kinds of subgraphs, K5, which is this is non-planar, which means that this one you cannot implement this with a two-dimensional plane. Also K33, the same thing. So basically, these two graphs are particularly special. So these three things, planar graph capability, and K5 and K33, if you combine them, then you can make all kinds of non-planar graphs, all possible graphs. Okay, so that's why this is useful. So in a sense, is that this optical tweezer system arranging this atom can make a hypergeometrical all possible graph in principle. Okay. So system is not special. So let me go back. So this, let's come back to the main discussion today is like a Magnum bound state dynamics using this Rydberg atom system. So actually, when I was talking in a meeting, in a conference in Europe, and then Dr. Fan Yang was approaching me and discussed that he suggested that this experiment we can do. Yeah, basically. I was not that clear, so I asked to my students here, and he said, it's a doable experiment. That's why we did the experiment together. And actually, this is just based on by probably his PhD work in Tsinghua. And then done with this theoretician, we were able to actually get the result very easily and do the analysis also very reasonably in time. So quantum simulation is basically using spin model Hamiltonian of qubits, or in this case atom, to probe many-body state or dynamics, right? And there are many quantum simulation results nowadays. There are like really many. In this particular simulation, we are using this XY model of hopping and bound. Okay. So in this, before we go to there, Rydberg atom system, for example, for a 4-atom system, it can represent this type of graph, which is star graph. If you pull the center atom, then we can stretch this one to deform it to a different graph, complete graph. And also, if you take this one apart and then take it out, then you can make a cyclic graph. Also, by stretching it, we can make a diamond graph. This type of structure deformation can change from one topology to another, different kinds of graphs, right? So you can observe this type of thing is how nicely they can be done by doing some time domain spectroscopy. You can turn on this Ising type Hamiltonian and then turn off, and as by varying the time and measure their certain state. For example, in this case, the projection to the 0, 0, 0, 0 state. So P0 is the basically average ground state population. Then if you see this oscillation, then this is typical kinds of experiment that I was doing when I was doing ultra fast laser experiment. Okay, so if you do the Fourier transform, then you can resolve their energies. Actually, in this case, the energy difference, and you can compare that. Their energy structures are quite differently changed from one structure to the other. We can also see the dimer-dimer interaction by varying trimer-trimer interaction by varying their distances. So isolated two trimers and completely mixed it formed to a different kinds of graph, which is I think S6. So also do these kinds of experiment. So now this Rydberg atom system has Hamiltonian look like this. This one is the Rabi frequency part, which goes like changing from ground state to the excited state. And this is the laser detuning part. So this is actually sigma g, but you can make it to n1 by multiply by 2 and minus 1. So this n is the excitation number operator. So it counts. So this n equals 1 if the atom is a Rydberg state. If n equals 0 if the atom is in the ground state. Okay. And this is the interaction. In our experimental range, this is a van der Waals interaction, which scales with 1 over r to the 6th power. So this V is very much tunable, starting from like, let's say, 3 micrometer separation to like a 15 micrometer separation, factor of 5, then this V can go like 5 to the 6th power. Okay, so very much tunable. And like I said, this is 2 photon transitions. The ground is down spin, Rydberg atom is up spin. Then we can do this experiment like this. For example, you arrange atom by about 5 to 10 micrometer separations. And then use 780 nanometer light here, 480 nanometer light here to cancel this Doppler shift a little bit. And then use this optical tweezer here. These optical tweezers, on certain cases, we use them as a kind of the local addressing. So you can just shine this one in the presence of this Rydberg excitation, then it can selectively off detune. So we can have a sort of like anti-addressing beam. These are anti-addressing beams, basically. So then this part here is a driving term, and this part is the diagonal Hamiltonian. So this Hamiltonian part can be sort of like divided. We can divide this one into it. For example, two atom case here. Down, down, that's the ground state. And one state is up, down, up. There are two energy degenerate, one particle excitation sector. And there's a 2 atom excited, so n equals 2 sector. Basically, we can divide it with 3 sectors, right? And this arrow represents the Rabi frequency. So this resonant condition is here and here. And once this interaction, this energy gap between this n equals 1 sector and 2 sector is well separated. Likewise, n equals 1 sector and n equals well separated. These two are basically fragmented in a sense, right? These are isolated. So in this case, this is approximately exchange between this and this. So starting from here, then if you shine this Rydberg Hamiltonian, then actually this excitation here goes back in here. So this is initial state, and as the quenching evolves, it comes back and then switches back. So it's exchange. It's two-body spin exchange. Likewise, we can also do, and in this case, the coupling J is given by this way, based on this paper. They analyzed this one. So one particular interesting thing is that this is the function of delta and delta minus V. So that's the energy, this energy and that energy. That's right. And three-atom chain case, you can do a similar kinds of analysis, and then this is three-body exchange where this hops this way. I will go back to that a little bit more. So first, spin exchange dynamics of two atoms. So this was the case. The way we do the experiment is this. For example, we trap two atoms, and then we use the addressing beam, which makes the anti-addressing. Yeah? So only one is excited to Rydberg state, and then do the Rydberg excitation with a certain Rabi frequency and detuning. Then that will evolve, and then we turn off and measure, basically. As a function of time, then this one, we can measure this sort of Rabi oscillation between these two exchange. This is 0, 1, down up state. This is up down state. But there are some remaining, because this is approximation. This remains below something like 20%. So this stays up, and down. These are there. But these are, because we can measure each measurement, each atom-based measurement, we can select out. So in a sense, we can post-select only this one Rydberg atom excitation sector only. Okay. By varying the V, or distance, and delta and omega, we can do all kinds of measurement to scale this coupling, spin exchange coupling constant, and with certain normalization. Then we observe two different things, one and here, as, depending upon the sign of delta, negative or positive. So this all agrees well with that. But there's a singular point here. It deviates a little bit, but actually, as a matter of fact, in these cases, the approximation breaks down. So it will excite this double excitation factors. We call this like a double excitation facilitation. So it can leak to the double excited state more often, anti-blockade state. Okay, so let's try some quantum random walk using 7-atom chain, for example, starting from here. So only this one was excited, but because of this coherent magnetic hopping, they'll hop. From here, it will hop to the nearest neighbor, and then hop another to next nearest neighbor. But in that cases, actually they hop back, so this is the quantum random walk. Okay, quantum walk. And those are experimentally you can measure. It's clear. So particularly this bright, dark region here is clearly says that this is the coherent evolution of this involved with quantum walk. And also we can method if it's ballistic, it's supposed to be this way, but it's quite completely deviated from ballistic, and this is a quantum random behavior, and it nicely matches with the numerical simulation based on this model here. And the major error here is basically this finite time decay. So this is also done by it's about 5 microseconds. So 5 microseconds of coherent evolution we can observe. We were able to observe. So now it comes back to the dynamics of Magnum bound state, right? So this is a Magnum bound state. So starting from two tightly bound nearest neighbor Magnum can propagate using this hopping term and this Magnum interaction. So this Q, the coefficient of hopping coefficient, and the U, the interaction coefficient, will have a ratio to give us the dynamics governing this dynamic behavior. There were two previous experiments, actually, in the optical lattice system and also trapped ion system. But the main difference of using Rydberg atom is the Rydberg atom is quite tunable. That's why if you see this isotropy, which is a ratio between this interaction, density interaction part, and this hopping part, which is about more than 100. So it's actually, in our typical number, it goes like 500. But these experiments were sort of like 5. So that's the basically main difference. So, okay. Okay, so let's see that. First, we can calculate to expect what kinds of bound states are there in this typical experimental region of anisotropy and detuning and omega radio frequency. Then clearly there are many levels here. This is the 2 extension spectrum, and this scattering zone. It is a bound mode here. This one is a loosely bound mode, which has a very delocalized. It's localized, but it's less localized state. And this one particular one, this is a tightly bound state. This is nearest neighbor bound state, 2 meganon state. This one is a 2 meganon state, but still it's a loosely bound. It's the next nearest neighbor plane. So if you analyze this one, then this hopping induces this third, the Rydberg atom in the third place will go to the right, having this double extron dimer will hop to the right-hand side, or this one on the fourth side will go hop to the left and then move to the left. So it is coherently evolved this way. Also, loosely bound state, if you do analysis, actually they move together, either on the right-hand side or left-hand side. Okay, first, tightly bound state, we did the experiment on purpose of about 35, and then we changed the Q value from about 0.13 megahertz and then about 1/10 of that. And then these two experiment regimes, this hopping is dominant, and clearly see this time version correlator will evolves. And also, once this Q is small, then hopping is so small, so we can also see the frozen. So frozen, there's no dynamics, so it's expected to come for comparison. Likewise, we can also do the loosely bound state. In this case, chi1, which is the ratio between anisotropy of the nearest neighbor bound state, and the chi2 is the next nearest neighbor one. So in that case, these cases we compare the large anisotropy, next nearest neighbor anisotropy, and the small anisotropy, right? Then these cases hopping, so by 2 times of nearest neighbor hopping, and this case is because this is so small, so the bound state overlap is so small, so this is sort of hopping is still the same, but the U is small. U is small, so this unbound state. So it's sort of like they pulled apart. Okay. So in conclusion, so this Rydberg atom Hamiltonian is a highly anisotropic Heisenberg magnets, and clearly we were able to observe and see this bound state dynamics, either tightly bound with the nearest neighbor or weakly bound with the next nearest neighbor bound state. And there are some outlooks, and if you have questions, we can discuss that. I think because now time is a little bit left, so I just left for the sort of a second discussion. Okay, so this Rydberg atom quantum manifold system is it can do many kinds of things like quantum simulation, like the one here, but also it can do many quantum computing type of to deal with the classical problems. So let me very briefly with 2 slides summarize some of them. 3 slides actually. So the question is how this graph will play in this quantum computing, right? That's the kind of the concept. How we use this graph nature instead of the array nature of qubits for quantum computing. So for example, if this is a graph with 126 atoms, so sort of randomly arranged in a square lattice, then if you do Rydberg excitation, then crossing this edge or line, this Rydberg blockade is applied. That's a constraint. When this constraint is applied to this about 126 vertex graph, then it's a solution. So basically, it's a many-body ground state. It's a superposition of certain configurations of atoms, either ground state or ground state or Rydberg state that satisfies so-called maximum independent set. Okay. So and because this Rydberg ground state is a superposition of those solutions that satisfies that constraint, which forces this system to go to maximum independent set solution. So by measuring it once will give us the result, one of those many superpositions. So all of them are solutions of this classical problem, but any of them is also solution. So this particular type of experiment can be done in one experiment, like 1 second, although it has a lot of noises. So these noises can be treated with a certain method here. So for example, this type of problem is sort of like belongs to a certain computational complexity, which is difficult for a classical computation because of polynomial exponential time complexity. I think that probably the audience is about the same as yesterday, right? That's why. So this one does not surprise you because the forum I was introduced this one before. Maybe that I will stop here and then answer your questions or comments probably. Time is almost up, so anyway.
Thank you for the nice talk, and I would like to ask a simple question about site, number of site.
Number of site. In this case, we have done like a 7 atom chain experiment up to.
I wonder which one decide the number of site available.
Laser power first. In our experimental setup, the laser power allows up to something around 140 sites. But second, depending upon the way we measure, for example, if you can have a snapshot measurement, then of course we can utilize 140 site of atoms. But if you want to have a certain evolutions which requires all possible configurations of the state, then up to something like a 7 atom we can observe for some Fourier transform, time domain spectroscopy kind of things. So often it depends. For example, if your final state is 1 out of 2, for example, like anti-ferromagnetic state or plus and minus, then your result is your final state is only 2. So although like a 10 atom can have like a 2 to the 10 microscopic configurations, if you expect final state is only 2, then you can utilize like as many as like about few thousand atoms. But if the final result is scattered all over the places, then your measurement has to be limited quite significantly. Yeah.
Thank you very much.
Are there other questions from the audience?
You were there, actually. I was showing you your results.
But I'm not going to ask that. I was wondering, yeah, thanks for the nice talk. I was wondering on the optimization problems, this NP-hard, but this is an NP-hard problem, right? For the maximum independent set.
NP-hard, yes.
Yes, but then there's really no evidence that quantum computers will be able to solve these problems better. No, as far as I know.
That part is. Continue, please continue.
No, so the question is that's why I'm wondering always. I'm very skeptical towards the application and optimization problems because there's really at least from a computer science, the computer scientists tell us that at least for this type of problems, the mathematical structure is such that we cannot not expect any advantage for a quantum computer. There might be instances where there could be an advantage, but that would be coincidental incidences.
So there are many issues to be involved. First of all, the scaling discussions like this this is basically drawn with a kind of sketch of what is satisfied at the infinite scale. So which is based on, for example, like an exponential function is always bigger than any polynomial functions. That's the assumption of drawing this kind of picture. So if you plot this in a particular finite size, this picture makes it completely different, right? So this should be understood as a kind of concept only. So the better way is the benchmark test. For example, we compare this one with the resource estimation scaling and the time estimation scaling, and compare that with the classical. Basically, so lately there was a benchmark. There was one experiment from Harvard group claimed that this type of experiment in compare with the classical counterpart, which is a simulated annealing kind of result, we'll have this one can solve a harder problem.
But the problem there is, of course, if you choose an algorithm, classical algorithm, which is not optimal, then of course you can always be better than that classical algorithm. But you should choose the best classical algorithm for that problem, no?
No, it used a certain optimization of variation method.
I didn't think they used the optimum one for the problem. I mean, this always comes down to which algorithm, classical algorithm you compare to. Okay, we can discuss later.
So that was basically to make a fair comparison. Your target, your classical algorithm to be compared has to be specified, and they specified this. So they said that it has a quantum speed up over certain algorithm. So that was basically that was okay. So another kinds of direction of people was using general classical algorithm to compare it, and that they also claim that the benchmark limit is something few thousand. So based on this type of thing, up to few thousand atom array can be easily calculated with classical algorithm. So that also has a kind of the problem there. If this algorithm if this graph is something like this, so this is a very simple graph. It's a planar graph and sort of irregular. So there are classical algorithms which is sort of optimized for this type of thing. Actually, the way it calculates is moving one plane from left to the right. So basically, that sort of accelerates the calculation. If this graph becomes a little bit twisted by wiring it, it makes that kind of algorithm not useful. So you can think of it rough estimation other than this coherence time issue. This one have a certain upper limit of few thousand for this type of regular graph, like a square lattice or like this type of simple graph, and it can be a few hundred for general graph, like a graph, for example, a complex graph. So the computational time and resources quite dependent on not the number of atoms, but the connectivity of the atoms. Okay. That answers your question or not? Yeah.
Okay, last question.
I have a question about addressing process of atoms. How do you project anti-addressing beam and anti-addressing beam at the same time?
No. We are only use anti-addressing beam in this case.
Yeah.
We can also do the different kind of scenario like a addressing beam experiment. By using addressed beam can make the experiment resonant, for example. But that's not good because this laser itself is sort of like has a noise. So by making anti-address them to out of the excitation atoms, that is much better.
Thank you.
Okay, let's thank all the speakers once more.
Thank you very much.
That was the end of the talk for today, and we all hope to see you all tomorrow. Thank you.
Okay, I have some announcements. So the dinner for the invited speakers and the plenary speaker, we will gather at the lobby 6:30 p.m. and gonna get the bus and go to the Gyeongju area. And it will take like 40 minutes driving, and we can enjoy tens of minutes there for this authentic Korean traditional house like Hanok, and also have a great meal there. And tomorrow we're gonna have like a somewhat a more like specialized like conference on, especially on the quantum material, our site will be changed to the smaller one that is next to, in the same floor, but it's on the on that side. Okay, you're gonna find out. It's not gonna be this place. Okay, all right. So see you tomorrow or see you this dinner. Okay, thank you.